Hey there, and welcome to our exciting Spring Boot 3 course. Get ready to unlock the power of building robust web applications and microservices. Throughout this course, you'll dive into the creation of RESTful APIs, manage your app's security with OAuth 2, and monitor your application's performance using observability tech. Hey there, and welcome to our exciting Spring Boot 3 course. Get ready to unlock the power of building robust web applications and microservices. Throughout this course, you'll dive into the creation of RESTful APIs, manage your app's security with OAuth 2, and monitor your application's performance using observability techniques. Plus, we have hands-on coding exercises that will really solidify your knowledge. Don't forget to check the description for a link to our GitHub repository, where you'll find all the code and resources. And be sure to stick around for the final project at the end, which is designed to test everything you've learned. Now, let's get started. Creating a RESTful API is a fundamental skill for any developer. It enables software components to communicate over the internet efficiently. In this session, we're going to dive deep into the principles of REST. Don't worry if you're new to this, I'll walk you through it step by step, and we'll learn how to design a RESTful API. Plus, we'll implement it using Spring Boot, which, by the way, is a fantastic framework for building Java applications. So, first things first, let's break down what REST is all about. REST stands for Representational State Transfer, and it's an architectural style that uses standard HTTP methods like GET, POST, PUT, and DELETE to interact with resources. But what does that mean in practice? Simply put, it allows different systems to request and exchange. Creating a RESTful API is a fundamental skill for any developer. It enables software components to communicate over the internet efficiently. In this session, we're going to dive deep into the principles of REST. Don't worry if you're new to this, I'll walk you through it step by step, and we'll learn how to design a RESTful API. Plus, we'll implement it using Spring Boot, which, by the way, is a fantastic framework for building Java applications. So, first things first, let's break down what REST is all about. REST stands for Representational State Transfer, and it's an architectural style that uses standard HTTP methods like GET, POST, PUT, and DELETE to interact with resources. But what does that mean in practice? Simply put, it allows different systems to request and exchange data seamlessly over the web. Now, let's get into the nitty-gritty of designing our API. Start by defining your resources. Think of them as the data you want to expose. For instance, if you're building a library system, your resources might be books and authors. Each of these resources will have a unique identifier, usually an ID, that helps in accessing them specifically. Once we've mapped out our resources, we can move on to defining the endpoints for our API. Each endpoint corresponds to a resource action. For example, to get all books, you'd use a GET request at the /books endpoint. Similarly, to add a new book, you would send a POST request to the same endpoint. Okay, now let's talk about how to implement this using Spring Boot. First, you'll want to create a new Spring Boot project. Open your IDE and either use Spring Initializr or your preferred method to set up the project structure. Make sure to include necessary dependencies like Spring Web and Spring Data JPA, which makes working with databases easier. Now, after setting up, let's create a model class for our resource. For the book example, create a class called Book with attributes like ID, title, and author. Then, we'll need to create a repository interface to handle database operations. Just extend JPA repository and voila, you're ready to interact with your database. Next, we create a controller class that will manage our HTTP requests. In the controller, you'll define methods annotated with GET mapping, POST mapping, and so on to handle different operations. Don't forget to include proper response statuses for each method, providing clear feedback for the users of your API. Now, once you've got all this in place, simply run your application and you'll have a fully functional RESTful API ready to serve requests. Pretty cool, right? So there you have it. We've covered the essentials of creating a RESTful API using Spring Boot. There's a lot more to explore, like authentication and error handling, but that's for another session. For now, go ahead and experiment with what you've learned today. Let's start by discussing what REST actually is. REST stands for Representational State Transfer, an architectural style that defines a set of constraints for creating web services. Imagine you're ordering a pizza from your favorite pizzeria, right? You have several options. You can call them up, visit them in person, or even use an app. Using an API is somewhat similar. You send requests and receive responses just like when you're ordering your pizza. These requests utilize HTTP methods such as GET, POST, PUT, and DELETE to communicate with the server, much like the various ways you might choose to communicate your pizza order. Each method has its own purpose, folks. For example, when you want to get details about your pizza, you'd use GET, right? And to place an order, you'd go with POST. So as we dive deeper into this topic, just remember, APIs are the bridges that connect your applications with the web services out there, allowing them to interact seamlessly. We'll begin by adding the essential Spring Boot Starter Web, which, simplifies the setup for building web applications, especially if you're looking to create RESTful services. This starter brings in necessary libraries like Spring MVC, which helps us handle HTTP requests and enables various web functionalities. Next, we'll include Spring Boot Starter Data JPA, which seamlessly integrates Spring Data JPA, allowing us to perform database operations without needing lots of boilerplate code. To facilitate our in-memory database interactions, we'll also add the H2 database dependency with a runtime scope. This is really handy because it lets us store data temporarily while we're developing our application, making it super convenient to test our API's functionality without needing an external database setup. Each of these dependencies plays a critical role, ensuring our application is well equipped to handle web requests and effectively manipulate data. So this configuration, it sets a solid foundation for building our RESTful API using Spring Boot. Next, we're diving into the implementation of the book model, which represents the data structure for our API. So, the book class is annotated with @entity, which means it is a JPA entity that will be linked to a database table. Within this class, we define the key attributes of a book: ID, title, author, and ISBN. Now, the ID attribute, marked with the @ID annotation, serves as the primary key for the entity, while the @generated_value annotation ensures that the ID is automatically generated by the database. This is super important for keeping unique identifiers for our books. Okay, let's add some getters and setters for these attributes, right? They're essential for easily accessing and modifying the properties of our book entity. This encapsulation makes data manipulation a breeze. Next up, we will create the book repository, which is an interface that extends JPA repository. This integration lets us take advantage of built-in CRUD operations, such as saving, finding, and deleting books, without needing to write additional boilerplate code. This really streamlines our interactions with the database and enhances overall development efficiency. Now, let's implement the book controller, which will serve as the backbone of our API, handling various HTTP requests for book management. We begin by annotating the class with @RESTController, which allows it to respond to web requests with JSON data. The @request mapping /API/books annotation sets the base URL for all endpoints in this controller. Next, we inject the book repository using @AutoWired, enabling us to easily interact with our database. The first method, getAllBooks, is mapped to a GET request and retrieves all book entries, returning them as a list. For adding new books, the createBook method accepts a JSON representation of the book, saves it to the database, and returns the created book along with a 201 status code. Now, to update existing books, we have the updateBook method, which extracts the book ID from the URL and updates its details based on the provided JSON data. Lastly, bookDelete allows us to remove a book by ID, confirming the deletion with a 204 status code. Through these methods, we facilitate full CRUD functionality, effectively managing our book resources. We begin by creating the ResourceNotFound exception class, which extends runtime exception. This custom exception will allow us to provide specific feedback when a resource, like a book, cannot be found. By annotating the class with @responseStatus http status.notFound, we instruct Spring to return a 404 not found response whenever this exception is thrown. This is crucial for user experience because generic error messages, they can really be confusing. Instead, our custom message will inform clients about the specific resource that was not found, thereby improving the clarity of our API's responses. Now, the constructor takes a string message as an argument, which allows us to pass detailed information regarding the error. This level of specificity helps developers understand what went wrong during their interaction with the API. Overall, this implementation aids in effective communication between the client and server, significantly enriching the usability of our RESTful services. By employing this approach to error handling, we ensure that our responses are both informative and user-friendly. Now that our RESTful API structure is established, let's see how we can implement functionality to add a new book. We're going to set up a post endpoint, which is super important for handling incoming requests to create a new book entry in our database. First up, we'll define the createBook method within the book controller class. This method is mapped to the post HTTP method, so our API can accept data in JSON format. Next, we'll utilize the @requestBody annotation to bind the body of the request, which contains the book data, to a book object. Once we receive that object, we'll call the save method from the book repository. This method interacts with the database to persist the new book. When the book is successfully created, we return a response that includes the saved book's details, along with an HTTP status code of 201, which indicates that everything went smoothly and the resource has been successfully created. Now, don't worry, we've also set up a method called getAllBooks, which is mapped to the getHTTP method. This method retrieves and returns a list of all the books stored in the database, neatly formatted in JSON. By implementing these functionalities, we're enabling critical actions like creating and retrieving books, which are absolutely essential for our API's usability and efficiency. So, there you have it, a fantastic way to enhance our API.
Next, we will implement a configuration class to enable CORS for our API. This is crucial when your front-end runs on a different domain or port, as it allows the front-end to interact with the back-end without running into cross-origin issues. Here, we define a class annotated with @configuration to specify that it provides Spring configuration. By implementing Web MVC Configurer, we gain the ability to customize the Spring MVC configuration. Now, let's take a look at the method addCorsMappings. Within this method, we use CORS registry to specify which endpoints should allow cross-origin requests. In this example, we target all API routes by using the mapping pattern /API//, and we enable CORS requests specifically from HTTP localhost 3000, which could be adjusted to your frontend's URL. Additionally, we allow standard HTTP methods get, post, put, and delete, ensuring that our API can handle all necessary interactions with the client. By adding this configuration, we ensure seamless communication between our front-end and back-end during development, preventing potential errors and enhancing user experience.
First things first, we add the SpringFox Bootstarter dependency to your pom.xml. What this does is enable the automatic generation of interactive API documentation, which is pretty awesome for developers who will interact with your API. All right, moving on. Next, we need to create a configuration class to set up Swagger. This class will have the @configuration annotation, which tells the Spring container that it's got some configurations to process. Then, we toss in the @enableSwagger2 annotation to activate Swagger support, allowing us to tap into its features. Now, let's define a docket bean. This is where we specify all the important details for generating our API documentation. Using requesthandlerselectors.base package, we'll designate the package where our API controllers live, making sure that Swagger only documents the relevant endpoints. And don't forget about the paths method, which lets us select all paths, ensuring our entire API is included in the documentation. Once everything's configured, just run the application and voila! You'll expose the Swagger UI endpoint at http://localhost:8080/swaggerui/.
From there, you can visually explore all API endpoints, test requests, and view expected responses directly in your browser. This makes it so much easier to understand and interact with the API. Pretty neat, huh?
In conclusion, creating a RESTful API with Spring Boot is really about setting up your project first. You'll define your models, repositories, and controllers. Then you can handle errors effectively. Don't forget to configure cores and add some documentation along the way. It's a straightforward yet powerful approach, like building blocks that enable communication between different software components over HTTP. Now you've got a solid foundation to build upon and customize according to your application's requirements. So keep experimenting. Each time you build an API, it's a fantastic chance to enhance your skills and broaden your knowledge. Happy coding!
Now, let's take a moment to dive into implementing the getBookById method in our book controller. This method is designed to respond to a GET request for a specific book, identified by its unique ID. We begin by using the @getMapping annotation to set up the route for this request, where /id indicates that we expect a book ID to be passed through the URL. The @pathVariable annotation is what allows us to extract that ID from the URL and then use it as a method parameter. Within the method itself, we leverage the book repository to locate the book by its ID, which returns an optional of book. So if a book with that ID exists, we then wrap it in a response entity, returning it along with an HTTP status of 200 OK. Now, the beauty of Spring Boot is that this response is automatically converted to JSON format, which ensures that our client has a clear view of all the fields available in the response. In cases where the book isn't found, we throw a custom resource not found exception, which results in an appropriate 404 error. This approach keeps our API not only user-friendly, but also very informative, allowing clients to respond in a suitable manner when accessing resources.
In this method, we're going to use the @getting annotation along with a path variable, which will help us handle GET requests for a specific book identified by its ID. This way, we effectively map the incoming request to our method, making our API much more intuitive for users. So inside the method, we first try to retrieve the book using the book repository's findById method. And hey, if the book just isn't there, we throw a custom exception called resource not found exception. This is super important because it allows us to manage errors properly and return a fitting 404 status code to the client. It gives clear feedback when a requested resource isn't available. Now, when we find the book, we wrap it in a response entity and send it back with an HTTP 200 OK status. The cool thing is, Spring Boot will automatically handle the conversion of the book object into JSON format for us. This ensures that our response is neatly structured and quite friendly for the clients to consume. So this approach not only simplifies how clients interact with our API, but also sticks to RESTful principles by providing meaningful HTTP responses based on the outcome of the request. It's all about creating a smooth and user-centric experience.
Next, we'll implement a simple data transfer object, or DTO, to really enhance our API's data model. This involves creating the book DTO class, which acts as a bridge between our book entity and the data we present to clients. In this class, we'll define 3 private fields: ID, title, and author. These are the essential attributes we want to share. Now, you'll notice we've intentionally left out the ISBN field. That's because it could be considered sensitive or just unnecessary for certain consumers. This selective exposure helps maximize both security and efficiency, leading to smaller payloads and, you guessed it, faster responses. The constructor for book DTO initializes these fields, making it super easy to create instances of our DTO with the required data. Plus, we provide getter methods for each attribute, which ensures that clients can access the data without modifying it themselves. This encapsulation is a core principle of object-oriented programming. It promotes a clear separation between the data structure and how it's presented. With this DTO established, we're in a great position to enhance our API responses and have better control over the data we share with our users.
So,
First up, we start with the @GetRequest annotation, which is a neat way to map HTTP GET requests to a specific URL pattern. This lets clients request a book based on its ID. Pretty cool, right? The method takes a long ID as a parameter, and we extract this from the URL using the @path variable annotation. Now, inside this method, we first try to retrieve the book entity from the book repository. If, by chance, the book with the specified ID doesn't exist, a resource not found exception is thrown. This gives us a clear error response for the client. Okay, once we find that book, we create a new book DTO instance. Now, this book DTO is like a simplified version of the book entity, only holding the essential bits, like ID, title, and author. This approach not only keeps things tidy, but also enhances security by preventing sensitive data from being exposed. Finally, we return a response entity that contains our book DTO, ensuring that the client receives a well-structured JSON response that effectively communicates all the relevant book information in a concise manner.
The figure titled Distribution of HTTP Status Codes in RESTful APIs displays a pie chart with labeled slices for 200 OK, 201 created, 204 no content, 400 bad request, 404 not found, and 500 internal server error, along with a legend mapping each color to its corresponding status code. Now, if we take a closer look, the largest slice, 200 OK, occupies about 63 to 64% of the chart, which shows that the vast majority of responses are successful, full content responses. Next, we see the second largest piece, 201 created, at roughly 16%. This highlights that a significant portion of requests successfully leads to resource creation. It really underscores the importance of returning the proper location headers and adhering to 201 semantics for those create endpoints. Moving on, the 204 no content slice accounts for around 9 to 10%, indicating scenarios where actions complete successfully but with no body to return, which is particularly useful for deletions or update acknowledgements. Now, let's talk about the client errors, namely 400 and 404. These together make up another 9 to 10% of responses. This suggests that input validation and clear error messaging remain critical to minimize those failed client requests. Now, the 500 internal server error slice is the smallest, at about 1 to 2%. Indicating that while server-side failures are comparatively rare, they still exist and should definitely be monitored and logged. So overall, when we look at this chart, it emphasizes that successful responses are the norm, but there's also noteworthy activity in create operations and a measurable rate of client-side errors, which should inform our priorities for handling status codes, crafting meaningful error responses, and proactive monitoring. Let's dive into how we can implement the method for creating a new book in our API. The method we're working with is annotated with @postmapping, which means it handles HTTP post requests directed at the defined endpoint. In the createBook method, we're going to take a book object directly from the request body, which lets clients send new book information formatted in JSON. All right, so inside the method, we use our book repository to save that book to the database. This is super important because it returns the saved book instance. Why is that? Because we need to obtain any new properties that the repository has assigned, like the generated ID. Next, we create a book DTO object from that saved book, which includes only the fields we want to share with the client, like ID, title, and author. Now let's wrap it up. The method culminates in returning a response using responseEntity.created, which sets the HTTP status to 201 created. This response not only includes the URI of the newly created resource, allowing clients to access it directly, but also wraps our book DTO in the response body. This way, we ensure that our clients receive a clear representation of the created book, keeping in line with the best practices for API design. First, we'll annotate our method with @getMapping, which is how we tell our application to handle GET requests at the /API/books endpoint. Inside this method, we'll use the book repository to grab all the book entries, and this will return us a list of book objects. Now, moving on, we need to transform that list of book entities into book DTO objects using Java streams. This step is crucial.
DTOs help us tailor the data specifically for our clients, ensuring that only the relevant fields are visible. Each book gets mapped to a book DTO, capturing essential attributes like ID, title, and author. Finally, we construct our response using responseentity.ok, which indicates a successful response. In that same response, we'll add a custom header named xTotalCount, which gives clients a heads up on the total number of books returned. This is super handy for clients who may want to implement pagination, since it helps them gauge the total size of the dataset. The method then closes by sending back that list of book DTOs in the response body.
Now, let's take a closer look at how we can implement versioning in our API. By adding the @request mapping/API/v1/books annotation to our controller, we're clearly setting the base endpoint for all requests related to book resources while specifying the API version. This practice is super important, as it allows our clients to stick to a specific version of the API, which is crucial for maintaining stability as we make changes or improvements down the road. For instance, if we decide to introduce new features or modify some existing ones, we can easily create a new controller for version 2, like /API/v2/books, and this way we won't disturb users who are still relying on version 1. This versioning strategy not only adds more flexibility to the API, but also promotes a smoother transition for our clients, making sure that their applications remain functional during updates. By using versioning, we really set a solid foundation for the growth of our API while being responsive to user needs, all the while safeguarding those existing client integrations.
Now, let's take a look at how we can test our getBookById method to ensure its functionality. We start by setting up a test class that's annotated with @runWith springrunner.class and @webviewTest bookcontroller.class, which specifically loads the components we need to test the book controller. Next, we automatically wire in a mock MVC instance that allows us to simulate HTTP requests to our API endpoints. To keep our controller isolated from the underlying data layer during testing, we make use of the @mockbean annotation to create a mock instance of the book repository. This gives us the flexibility to define the behaviors for our data interactions without relying on a real database. Now, in our test method, getBookById returns book, we create a new book object with some predefined attributes. We utilize Mockito's when method to instruct our mock repository to return this book when we're asking for a specific ID. Finally, we simulate a GET request to our API endpoint and assert that the response status is 200 OK. With JSON path, we can also verify that the returned JSON contains the expected title and author. This structure reassures us that our endpoint behaves correctly and returns the right data.
We've gone over how to define responses and refine the data model accessed via our API using DTOs. We highlighted the importance of having structured responses, handling HTTP status codes, adding metadata, and implementing version control effectively. We also delved into writing tests to ensure our API behaves as we expect it to. With these concepts in mind, you're now equipped to create a robust and user-friendly API that truly meets the needs of your clients. Thank you for following along, and keep coding. It's not just about sending back error messages when things go wrong. It's about providing meaningful information so that clients can respond appropriately. In this lesson, we're going to cover how to effectively manage errors in your Spring Boot RESTful API, including defining custom exceptions, creating global exception handlers, and ensuring that your clients receive clear, actionable feedback. So far, we've learned about the essential components of building a RESTful API using Spring Boot, such as creating endpoints, implementing error handling, and configuring cores. We discussed the importance of structured JSON responses and how to use data transfer objects, or DTOs, to control the data exposed to clients. The significance of HTTP status codes, adding metadata, and versioning APIs were also highlighted to enhance usability. Lastly, we touched on testing API endpoints to ensure they function as expected. Now, we will dive into error management, discussing best practices to enhance your API's reliability. We'll begin by defining resource not found exception, which extends runtime exception, allowing us to effectively leverage exception handling within our Spring Boot application. The @response_status HTTP not found annotation is absolutely crucial here. It instructs Spring to return an HTTP 404 status code whenever this exception is thrown. This means that any time a resource that a client is trying to access doesn't exist, our API can communicate this clearly with a standardized response. When creating the constructor, we'll pass in a message that can be used to provide additional context to the client. This customization allows us to enhance the error feedback, making it more informative. By using this custom exception, we improve our error management strategy, ensuring clients understand precisely what went wrong when they attempt to access a resource that's unavailable. This approach not only enhances usability, but also aligns with RESTful principles by providing meaningful and actionable feedback to API consumers.
Here, the annotation maps the HTTP GET request for the specified path, allowing clients to retrieve a book by its unique identifier. As we define our method, we take a long ID parameter from the path, which represents the book's ID. To fetch the book from the database, we use the bookrepository.findID. We throw a resource not found exception. This custom exception provides clarity by including a descriptive message that incorporates the ID, allowing the client to understand precisely what went wrong. Once the book is retrieved successfully, we create a book DTO object with the book's ID, title, and author for a cleaner data transfer. Finally, we respond with an HTTP 200 status and the book's information encapsulated in the book DTO, ensuring that clients receive a clear and structured response when retrieving book data.
Now, let's talk about implementing a global exception handler using the @controller advice annotation in our Spring Boot application. This technique will help us manage exceptions more effectively, ensuring that we can keep error handling centralized and avoid writing repetitive code in each controller. Within the Global Exception Handler class, we'll define two key methods for exception handling. The first one, Handle Resource Not Found Exception, is activated when a Resource Not Found exception is thrown. Here, we create a response map that captures the error message and then wrap it in a response entity with a 404 status code. This way, whenever a resource is not found, our clients will receive a clear and consistent error message. Now, the second method, called Handle Generic Exception, is designed to handle any unforeseen exceptions that might arise. It provides a generic error response by capturing all unhandled exceptions and sending back a 500 status code, signifying an internal server error. This setup ensures that clients have a uniform experience when they encounter issues, as they'll receive a well-structured JSON response no matter what type of error comes up. By implementing this global handler, we enhance the robustness of our API, ensuring that we communicate meaningful feedback to clients whenever errors occur. But wait, there's more to effective error management. You also need to provide meaningful HTTP status codes that accurately indicate the type of error you're dealing with. Think about the different client interactions you might encounter. These can lead to various issues. For instance, you might get a 400 for a bad request, a 401 for unauthorized access, or a 403 for forbidden access, and so forth. It's crucial that we differentiate these in our global exception handler. By doing this, you not only provide clearer feedback to users, but also make debugging easier for yourself and your team. The horizontal bar chart titled Frequency of HTTP Status Codes in Error Management presents the observed counts for 6 status codes along the y-axis, with the x-axis labeled Number of Occurrences. Now, as we look from top to bottom, the chart lists these important status codes: 200 OK, 201 created, 204 no content, 400 bad request, 404 not found, and 500 internal server error. Next to each bar, you'll find the annotated counts. 200 OK has 150, 201 created shows 80, 204 no content at 30, 400 bad request at 60, 404 not found at 50, and finally 500 internal server error at just 20. The horizontal layout, along with the grid lines on the x-axis, makes it super easy to compare these frequencies. Now, if we focus on the data, successful responses like 200 and 201 really dominate the chart. On the flip side,
we see client-side errors like 400 and 404 combining for a total of 110, which definitely warrants our attention. While server-side failures, represented by 500, are comparatively rare. Those labeled counts next to each bar confirm the exact magnitudes and will help support our prioritization decisions. So, it's clear. Our first focus should be on reducing client errors through better validation and clearer client guidance, especially with 400 and 404 responses. Next, we'll want to monitor and log those less frequent server errors to prevent any escalations. And let's not forget the prevalence of those successful responses. We can use that to fine-tune our alert thresholds and testing priorities. So, let's embrace this data. It's like a roadmap guiding us to improve our error management strategy.
Now, let's see how we can enhance our global exceptional handler to manage validation errors specifically. We begin by implementing a method that intercepts method argument not valid exception, which is thrown when a DTO fails validation, like when a user submits invalid data. Inside this method, we'll create a map to hold those error messages. This is where each field that failed validation gets paired with its corresponding error message. We achieve this by iterating over the field errors retrieved from the exception. So for each field error, we populate the errors map. This step is really important because it allows us to return detailed, user-friendly feedback to the client. Finally, we send this structured map back as a JSON response, along with an HTTP status of 400 bad request. This approach is crucial for effective error management because it empowers clients to understand exactly what went wrong and how they can fix their input before making another request. By providing meaningful validation feedback, we really improve the overall user experience and ensure our API is more robust and easier to use.
Now, let's implement error logging into our global exception handler. This class is crucial for centralizing how we handle exceptions across all the controllers in our application. So, first things first, we'll need to import the SLF4J logger and logger factory, which will allow us to enable logging functionality. By defining a static final logger instance linked to the global exception handler, we're setting the stage to capture error messages whenever an exception occurs. Now, let's shift our focus to handling generic exceptions. When something unexpected happens, the handle generic exception method kicks in. It logs an error message, including the details of the exception, which is super helpful for troubleshooting and monitoring the health of our application. By including the exception message in the log, we gain visibility into what went wrong, making our future debugging efforts a whole lot easier. So, in summary, integrating logging into our global exception handler not only empowers us to maintain a high level of awareness regarding application errors, but also leaves behind a trail of logs. This trail can tremendously help us trace issues, understand how clients interact with our system, and ultimately improve the reliability and performance of our application. Remember, this practice is fundamental for maintaining robust APIs in production environments.
We begin by defining a class called API error, which will encapsulate essential information about the error, like a descriptive message, the HTTP status code, and a timestamp to indicate when the error occurred. The constructor takes in a message and a status, setting the corresponding fields and initializing the timestamp with the current system time. All right, next we're going to modify our existing global exception handler, to utilize this uniform structure for our error responses. For example, when handling a resource not found exception, we create an instance of API error, passing in the specific exception message and the HTTP status code for not found. This way, when a resource isn't found, the response will be structured in a manner that API clients can easily parse. By returning an API error instance within a response entity, we ensure consistency across our error responses, making them not only more predictable, but also easier for API consumers to handle programmatically. This consistency truly enhances the overall user experience.
Now, let's dive into how we can implement a test to verify the error handling in our getBookById method, especially when a requested book doesn't exist. So, to kick things off, we're going to use Mockito to mock our book repository. We'll specifically configure it to return an empty optional when we search for a book with an ID of 99. This effectively simulates the situation where the book is not found in the database, which is a common scenario, right? Next, we'll utilize mock-MVC to perform an HTTP GET request to the API/books/99 endpoint. After we've made that request, we can assert that the response status we expect is 404, indicating that the book wasn't found. But that's not all. We should also check the JSON response body to ensure it contains the correct message, confirming that no book was found with the given ID. This really aligns perfectly with our structured error responses, allowing the client to understand precisely what happened. By implementing this test, we're ensuring that our API's error handling functionality behaves just as we intend, which ultimately contributes not only to the reliability of the application, but also enhances the user experience when errors arise. As we wrap up our discussion on managing errors in a RESTful API, it's crucial to remember that good error management practices really enhance both the developer and user experience. Providing meaningful errors not only helps users interact with your API more effectively, but it also gives valuable insights into what might be going wrong during those development and maintenance stages. Now, implementing custom exceptions, along with a global exception handler, meaningful HTTP status codes, effective error logging, and standardized error responses creates a robust error handling mechanism. This setup lets developers focus on building features instead of constantly troubleshooting. So, next time you're building a RESTful API, keep these best practices in mind. With them, you can construct a more resilient and user-friendly API that thrives, even in the face of errors. Happy coding, and see you in the next lesson. In this lesson, we're going to dive into consuming a RESTful API from another Spring Boot application using Feignclient. We'll create a Spring Boot application that consumes the football RESTful API, which we built earlier, and along the way, we'll learn how Feignclient simplifies the process of making REST calls. Now, just to refresh our memories, so far, we've talked about effective error management in a Spring Boot RESTful API, stressing the importance of custom exceptions and global exception handlers for structured error responses. We've covered how to implement meaningful HTTP status codes and highlighted the significance of logging errors to enhance oversight of our applications. Plus, we discussed the necessity of having a uniform JSON error response structure to improve client interaction with the API. Now, as we look ahead, in our next lesson, we'll focus on testing our error handling mechanisms to ensure they perform correctly under various scenarios.
Now, let's implement the necessary dependencies in our Maven pom.xml file for a Spring Boot application that uses Feignclient. We start by defining the required dependencies under the Dependencies section. This includes the Spring Boot Starter Web for building web applications and the Spring Cloud Starter Open Feign to enable Feign in our project. And don't forget the Spring Boot Starter DevTools. This one is great for enhancing our development experience with those nifty live reload capabilities. Now, keep in mind, the Spring Boot Starter DevTools is marked as optional and is only needed in the runtime scope, so you won't always have to stress about it. Next, we have to ensure that the Spring Cloud dependencies are available. To do that, we'll add a repository section where we specify the Spring Cloud repository URL. This step is pretty crucial because it allows Maven to fetch the necessary artifacts for the Spring Cloud components used alongside Spring Boot, ensuring we get that smooth integration we're looking for. By setting up these dependencies correctly, we're paving the way for utilizing Feignclient in the later sections of our application. It's going to significantly simplify our interaction with the football RESTful API, you know? This is a crucial step that lays the foundation for a seamless API consumption experience.
We start by importing the necessary Spring Boot libraries, including Spring Application, Spring Boot Application, and Enable Feignclients. The @Spring Boot Application annotation signifies that this class is the entry point of the Spring Boot application, while the @Enable Feignclients annotation activates Feignclients.
This means our application will automatically scan for interfaces annotated with Feignclient, allowing us to easily define and communicate with RESTful services without all that boilerplate code. Now, inside the class, we have the main method, which serves as the standard entry point for Java applications. This method calls springApplication.run to launch our application. By using this setup, we are laying the groundwork for interacting with the Football RESTful API we intend to consume. Next, we're ready to create a Feignclient that will facilitate our communication with the API, streamlining our ability to fetch data such as match information from the Football API in a structured way.
Now, let's implement a Feignclient to interact with our Football RESTful API. Here, we create an interface named Football API Client and annotate it with @Feignclient. This annotation registers the interface as a Feignclient, where the name attribute specifies the client's identifier, while the URL attribute points to the API's base URL. Now, we need to define the API call we want to make. By using the @getMapping annotation, we specify that we want to fetch a list of match details from the endpoint /matches. The method getMatches is declared to return a list of match DTO objects, which will serve as our data transfer object to capture the details of these thrilling football matches. Next, we're going to create the matchDTO class. This class will consist of properties including ID, home team, away team, and score. It encapsulates the match information we wish to retrieve from the API. Each property has its corresponding getters and setters to facilitate data access and manipulation. With this setup, we are poised to interact with our Football API and effectively retrieve match details in our Spring Boot application.
This service is marked with the Football Service annotation, indicating that it's a Spring-managed component responsible for business logic. Within this class, we'll declare a private final field for the Football API client, allowing us to utilize its methods for making API calls. Next, we will define a constructor for Football Service, where we'll use @autoed to inject an instance of Football API client. This dependency injection ensures that our service has access to the necessary client without needing to create it manually, promoting good design practices and vastly improving testability. Now, let's create a method called fetchMatches. This method will be responsible for invoking the getMatches method from the Football API client, which communicates with the external Football API. It returns a list of match DTO objects, a data transfer object that encapsulates all match details. By structuring our code this way, we maintain a clean separation of concerns, allowing our controller to focus solely on handling incoming requests while delegating the data fetching logic to the service layer. This is done by creating a class named FootballController, which we'll annotate with @RestController. This annotation signifies that our controller will handle RESTful responses. Next, we're going to define a private variable for the Football service that we'll use to fetch match data. To enable dependency injection for the service, we'll utilize the @AutoWired annotation in the constructor. This way, when our controller is instantiated, an instance of Football service is automatically provided to it. Now, the main functionality resides in the getMatches method. By supporting HTTP GET requests at the /API/matches endpoint, this method calls the fetchMatches method from our service layer. It expects to receive a list of match DTO objects, which represent the details of the football matches. And by returning this list directly, we leverage Spring's ability to automatically convert the data into JSON format for the client. This simplicity in returning structured data is one of the key benefits of using Spring Boot's REST capabilities. At this stage, we are not only fetching data from the service, but also simplifying the communication process between our application and external APIs, all while keeping our code clean and efficient. Let's dive into implementing an effective global exception handler to manage errors across our application. We're going to focus on the Global Exception Handler class, which we've annotated with @controllerAdvice. What this means is, it's set up to handle exceptions thrown by any controller throughout the application globally.
This design choice really helps us centralize our error handling logic, which leads to much cleaner and more maintainable code. Now, within this class, we're going to define a method that's annotated with @exceptionHandler, and it specifically targets exception.class. So any exception that bubbles up, like a pesky little balloon, will be intercepted by this method. When an exception occurs, this method constructs a response entity. It includes an error message along with the appropriate HTTP status code. In our case, we're setting that to 500, indicating an internal server error. By returning a user-friendly message that incorporates the actual exceptions message, we're enhancing our client's understanding about what went wrong, rather than, allowing the application to crash ungracefully. This implementation is smart. It not only guards against unexpected breaks, but also creates a coherent way to inform clients about errors, all while integrating seamlessly with the overall structure of our Spring Boot application.
As we wrap up, consuming a RESTful API using Feignclient in a Spring Boot application is, a really powerful approach. The integration is seamless. It allows developers to really focus on writing business logic instead of getting bogged down by boilerplate code. With just a few simple annotations and interfaces, we made a call to an external API and returned data to our users. So, in this lesson, we journeyed from setting up dependencies to creating a working application that fetches data from an external source, all while implementing basic error handling along the way. So, if you're looking to interact with any RESTful services, just remember that Feignclient is your best friend. In our next lesson, we'll venture into testing our error handling mechanisms to make sure everything works as expected. Thank you for joining me today, and I look forward to our next session together.
In today's lesson, we're diving into a very exciting topic, using Openapi to document our Restful API. Openapi enables us to create intuitive documentation and support for our APIs, which is an absolute game changer for developers. Let's get started. So far, we learned about consuming a Restful API using Feignclient in a Spring Boot application, emphasizing the setup of dependencies, and creating a client interface to fetch football match data. We also discussed implementing a service and a controller to handle requests and responses, along with basic error handling through a global exception handler. This streamlined approach allows developers to focus on business logic while minimizing boilerplate code. Now we will talk about how to add Openapi support to our application and learn how to document our Restful API efficiently. Now let's see how we can add the necessary dependency to our Spring Boot application to enable Openapi documentation. We will include the Spring.Openapi UI library in our POM XML. This library simplifies the integration process by automatically generating API documentation from our controllers and models. The dependency includes information about the group, artifact, and specific version, which in this case is 159. By adding this snippet, we ensure that our project can pull in all the required classes and resources from the library, allowing us to leverage its features without any hassle. Once we have added this dependency and built our project, the library will work its magic to expose API endpoints that we later define in our controllers. This makes API documentation generation easy and efficient, paving the way for a user-friendly experience when accessing our API documentation through Swagger UI. It is a crucial first step in ensuring that users and developers can quickly understand and interact with our API, setting the foundation for appropriate and helpful documentation. After adding that dependency, let's run our application. Once it's up and running, we can navigate to the /v3/API docs endpoint in our browser to see the generated Openapi documentation in JSON format. It's like peeking behind the scenes of your API. Everything you need to know is laid out for you. But that's not all. We can also visualize this documentation using Swagger UI by navigating to Swagger UI HTML. When you go to http://localhost 8080/Swagger UI HTML, you should see a web interface displaying all the endpoints exposed by your API. It not only describes the endpoints, but also provides options to test them out directly from the browser. This is how we create not just documentation, but interactive documentation that enhances the user experience. Now let's see how we can implement a simple controller to handle user data in our Spring Boot application. We start by importing the necessary classes, at getMapping for defining the endpoint, RestController to define the controller, and Openapi annotations for documentation. The user controller class is annotated with @RestController, signaling that it will serve ResTful requests. Within this controller, we define a method getAllUsers, which is mapped to the user's endpoint using the @getMapping annotation. This indicates that it responds to HTTP GET requests aimed at retrieving user data. To enhance the Openapi documentation, we utilize the @operation annotation, providing a summary that succinctly describes the purpose of this endpoint as getAllUsers, and a description that elaborates on its functionality, specifically that it retrieves a list of all users in the system. Ultimately, this setup not only specifies the endpoint's behavior, but also ensures that anyone reading the generated Openapi documentation can clearly understand what the endpoint does and how to use it effectively. Thus, it integrates well into our efforts to generate informative API documentation. Now let's implement the endpoint for creating a new user in our ResTful API. First, we use the @post mapping annotation on our method to specify that this endpoint will handle HTTP post requests to the user's path. This is appropriate since we are adding a new user to the system. Next, we annotate the method with @operation to provide a summary and description, which aids in generating clear API documentation. In the method signature, we include a @requestBody annotation on the user parameter. This annotation indicates that the method accepts a user object in the request body, which must contain the details necessary to create a user. By marking the request body as required, we ensure that the API consumers know they must include this information. The description further clarifies what is expected, which promotes better integration practices. Finally, the method returns a response entity user, allowing us to respond appropriately with the created user object and a status code. This structure not only facilitates user creation, but also enhances the clarity and usability of our API documentation for developers. Now let's implement the following annotations to enhance the documentation for our create user operation. By utilizing the @operation annotation, we define both a summary and a description for the endpoint, which clarifies its purpose to users. The summary provides a brief overview that captures the essence of the operation, while the description gives more detailed insights into the expected input and output. Next, we incorporate the @API response annotations within the responses attribute to specify what clients can expect based on different scenarios. Each @API response annotation takes a response code and a description, allowing us to clearly communicate the outcome of a user creation attempt. For instance, when the user is created successfully, a response code of 200 is returned with a description indicating success. Conversely, if the provided data is invalid, we indicate this with a 400 response code, specifying that it signifies an error due to bad input. This structured response documentation not only aids in user understanding, but also plays a crucial role in debugging and error handling, making it invaluable for efficient API consumption. Now let's implement the following configuration in our application, YAML file to customize our Openapi documentation. This setup plays a crucial role in defining how our API is presented in the Swagger UI. In this code, we specify the base path for accessing the API documentation as /v3/API-docs, which is where the generated Openapi specification in JSON format will be available. Additionally, we configure the path for Swagger UI to be accessible on Swagger UI HTML, allowing users to interactively explore and test the API endpoints directly from their browsers. Furthermore, we define key metadata about our API, such as the title, which is set to my API, along with a brief description, API for managing users and their data, and the version labeled as 100. This global information enriches the user experience by providing context and clarity on what the API does, making it easier for developers to understand its overall purpose and capabilities. Ultimately, this configuration not only enhances the presentation of the API, but also adds a professional touch to its documentation. Now let's see how we can implement versioning in our API to ensure that we maintain backward compatibility as we introduce new features. In the code, we have two distinct controllers representing different versions of our user management API. The user_v controller is dedicated to version 1 of the API, and it's mapped to the endpoint /API/v1/users. This controller will handle requests specific to the first iteration of the user management feature. By clearly defining this endpoint, we ensure that consumers who rely on the original API can continue to operate without disruption. Next, we will write the user-v controller, which is intended for version 2 of the API and is mapped to /API/v2/users. This version can introduce new features or modifications without affecting the existing functionality provided by version 1. Each controller can have its own set of endpoints, enabling us to tailor responses and features specifically to the version being utilized. Having separate controllers for different API versions helps consumers choose the version that best suits their needs, ensuring flexibility and a smoother transition when significant changes are made. This approach is crucial for API evolution and user satisfaction. Now let's implement the following configuration to customize our Swagger UI. This YAML structure allows us to define various properties that tailor the appearance and information displayed in the API documentation. In this configuration, we can set the title of the Swagger UI to custom Swagger UI title, giving our API documentation a more personalized identifier. Additionally, we can provide a custom description, which helps clarify the purpose of the API to the users. The version property indicates to consumers what version of the API documentation they are reviewing, and it's essential for maintaining clarity as we release new updates or features. Moreover, we have the ability to add a logo by specifying the path to our image file with the logo property. This customization aligns the UI with our branding, creating a cohesive user experience. Finally, we can change the primary color of the interface using the style property, which enhances visual appeal and can further reinforce our brand identity. By adjusting these settings, we ensure that our Swagger UI is not only functional, but also aesthetically in line with our branding, resulting in a professional and user-friendly experience. Now let's implement a basic security configuration using Spring Security to protect our API documentation and endpoints. The configuration class, annotated with @configuration and @enable web security, extends web security configurer adapter, allowing us to override security settings easily. In the configure method, we begin by defining the HTTP security configuration. We use the authorize requests method to specify which endpoints should be accessible. Here, we permit all requests to the /v3/API-docs/* and /swaggerui HTML paths. This means that while anyone can access our Openapi documentation and Swagger UI without authentication, any other API endpoints will require users to be authenticated. This distinction is crucial to secure sensitive data while still providing developers with the necessary tools to interact with the API. This setup strikes a balance between security and accessibility, promoting good practices in API development. With this configuration in place, you're ensuring that your API's documentation is publicly available for testing, while other functionalities remain protected, enhancing the overall integrity of your application. In summary, we have journeyed through creating Openapi documentation for your REST-TFL API using Spring Boot. We covered everything from the basics of setting up dependencies to enhancing our documentation with detailed descriptions, versioning, customizations, and security configurations. Remember, clear, well-structured documentation is vital for your API consumers, enabling them to integrate with your services seamlessly. I hope you found this lesson engaging and informative. As always, play around with the concepts we covered and tweak things to suit your specific needs. Don't hesitate to reach out with questions or thoughts because learning is a community effort. Until next time, happy coding. Now that we've set the foundation for our application, let's implement the necessary dependency for Feignclient in our POM XML file. This XML snippet adds a crucial library that enables us to create Feignclients effortlessly. By including the Spring Cloud Starter Open Feign dependency, we gain access to all the utilities needed for seamless API consumption, allowing us to manage API calls with less boilerplate code while focusing on our application's business logic. Next, we will write the main application class to enable Feign in our Spring Boot application. This class is crucial as it serves as the entry point for our application. By adding the @enable Feignclients annotation, we instruct Spring to scan for and auto-configure Feignclients, ensuring that any interfaces annotated with @Feignclient are recognized and managed. This streamlined approach dramatically simplifies our development workflow. Now let's take a look at how to define our Feignclient interface. The Football API client will serve as a contract for interacting with the Football Match API. Through the Feignclient annotation, we specify the client's name and the base URL of the API. By mapping HTTP methods to Java methods via annotations like @getMapping, we ensure that we can easily fetch match details with minimal configuration, promoting a clean and efficient way to handle API interactions in our application. The horizontal bar chart titled Importance of Feignclient Features in API Consumption lists 5 features: authentication, load balancing, error handling, data transformation, and security on the vertical axis, and shows their importance as percentages on the horizontal axis. Data transformation at 90%, authentication at 85%, error handling at 80%, load balancing at 75%, and security at 70%. Each bar is labeled with its exact percentage at the bar's end, making direct comparison straightforward. The dominant pattern is that data transformation is prioritized highest, which implies payload mapping, format conversion, and DTO handling are the most critical concerns when integrating with external APIs via Feign. Authentication and error handling are also highly valued and close in importance, reinforcing the need for the authentication interceptor and custom error decoder described elsewhere in this lesson. Load balancing and security, while still important, register moderately lower percentages, suggesting that after implementing robust transformation and reliability mechanisms, efforts can be allocated to optimizing request distribution and additional security hardening. Overall, these values guide implementation priorities. Focus first on transformation and reliability features, then on scalable request routing and supplementary security measures. Next, we will implement the Match Service class, which plays a crucial role in bridging the controller in our Feignclient. This class is marked with the @service annotation, indicating that it's a Spring-managed component. Inside, we define a Football API client field that is instantiated via constructor injection, ensuring that our service is always initialized with a valid Feignclient. Now let's explore the methods in Match Service. The getMatchById method accepts a match ID as a parameter and uses the Feignclient to retrieve match details, effectively encapsulating the API call within a business logic layer. Similarly, the getAllMatches method returns a list of matches by delegating the call to the Feignclient. This separation of concerns not only enhances maintainability, but also allows us to potentially transform the data before exposing it to the controller. Now that we have established the service, we will move on to the match controller, which is our entry point for handling incoming HTTP requests. The controller is annotated with @RestController, designating it as a controller for REST-TFL applications, and is mapped to the /API/matches path. Here we define 2 endpoints, one for fetching a match by its ID and another for retrieving all matches. Each method utilizes the respective service methods, showcasing how the controller seamlessly interacts with business logic while keeping the API clean and efficient. Now let's see how we can implement a custom error decoder in Feign to handle errors more gracefully when interacting with external APIs. The custom error decoder class implements the error decoder interface, which allows us to define our own logic for processing responses based on their HTTP status codes. In this implementation, we check for specific status codes, such as 404 and 500, and return meaningful runtime exceptions with descriptive messages, such as match not found or internal server error. This custom handling ensures that clients of our API receive informative feedback rather than generic error messages. Next, we will configure our Feignclient to utilize this custom error decoder by defining it as a Spring Bean in the Feign configuration class. By annotating the class with @configuration, we inform Spring that it should manage the beans defined within it. The error decoder method creates and returns an instance of our custom error decoder, allowing Spring to use it automatically in the background whenever an error occurs during API consumption. With this robust error handling mechanism, we enhance the reliability of our application, ensuring that it can effectively manage various error scenarios encountered while consuming external APIs. Now let's implement an auth request interceptor to enhance our Feignclient by adding an authorization header to each request. This interceptor will be annotated with @component, allowing Spring to recognize and manage it. Within the class, we will override the apply method from the request interceptor interface. This method will provide direct access to the outgoing request template, enabling us to modify it as needed. In this case, we will add an authorization header, which is crucial for APIs requiring authentication tokens. The header will include a bearer token retrieved from a method we will define within the class. It's important to note that in a real-world application, the getAccessToken method should implement logic to dynamically obtain the token, possibly using OAuth2 or another authentication method. By incorporating this interceptor, every time the Feignclient sends a request, it will automatically include the necessary authorization header, ensuring secure and authenticated communication with the API. This is a vital feature that simplifies repetitive tasks and improves security in API consumption. Now let's implement the circuit breaker pattern within our match service to enhance resilience when consuming external APIs. We begin by injecting the resilience4j circuit breaker alongside our football API client. This allows us to define circuit breaker behavior directly in our service methods. For instance, in the getMatchById method, we wrap the Feignclient call with the @circuitBreaker annotation, enabling it to gracefully handle any failures that occur during the API request. Within the circuit breaker functionality, we specify fallback logic that the application executes if the API call fails. For example, if fetching a match by ID results in an error, we return a new match object as a default response to avoid causing further disruptions in our application flow. Similarly, the getAllMatches method applies the same circuit breaker approach, returning an empty list in the event of a failure. This design improves the overall robustness of our application, while ensuring that it continues to provide a response even amid API outages or slowness, thereby enhancing the user experience significantly. As we wrap up the discussion on using Feignclient, remember to always test your integration thoroughly. Use tools like Postman or CURL to verify that your API calls are being made successfully and that the data returned matches your expectations. Additionally, consider monitoring and logging API interactions to catch any potential issues before they escalate. Thank you for joining me on this exciting journey into consuming APIs using Feignclient in Spring Boot. I hope you found this tutorial informative and engaging. Don't hesitate to experiment with the code and enhance your applications further. Happy coding, and see you in the next lesson. Now let's take a look at how we can structure our REST API consumer service. First, we create a configuration class where we define a REST template bean. This makes it easier for us to manage HTTP requests throughout our application since the REST template acts as the principal component for making such requests. By annotating the class with @configuration, we indicate to Spring that this class provides beans for the application context. Next, we implement the match service, which utilizes the REST template to interact with the external football match API. We store the API's URL in a constant and define a method to fetch all matches. This method employs the getForObject function of REST template, converting the response directly into an array of match objects. We also handle potential null responses gracefully by returning an empty array. Now let's implement a REST controller using matchController to expose our API's endpoints. By mapping the /API/matches endpoint, we can use the @getMapping annotation to make a GET request that retrieves all match data by leveraging our match service. This demonstrates a clear separation of concerns, where our controller focuses on handling requests and delegating logic to the service layer for fetching data. The displayed horizontal bar chart titled Key Concepts in Consuming APIs with Restclient in Spring Boot ranks 5 core topics by importance. Simplified HTTP requests 90%, fluent API design 85%, error handling 80%, token management 75%, and dependency management 70%. The ordering and percentages reveal a clear prioritization. Making HTTP interactions simple and using a fluent API are the top concerns, together accounting for the highest importance scores and suggesting that developer productivity and readable, chainable calls are primary benefits to emphasize when adopting Restclient. Error handling sits close behind, indicating reliability and robust exception management are nearly as critical and should be integrated from the start, for example, mapping Restclient exception handling and global handlers. Token management 75% highlights the need to plan authentication and token lifecycle support. Practical implications include adding interceptors or request customizers to attach and refresh tokens. Finally, dependency management at 70% shows that while keeping dependencies tidy and compatible is slightly less urgent than runtime behavior and security, it remains an important operational concern, implying that using the appropriate Spring Boot starter and managing versions should not be neglected. The relatively narrow spread from 90% down to 70% indicates all listed concepts are significant. Therefore, a balanced implementation that prioritizes HTTP simplicity and fluent APIs while embedding error handling and token strategies and maintaining disciplined dependency control is the recommended takeaway. Next, we will implement the configuration class required to set up our Restclient. This class is marked with the @configuration annotation, indicating that it contains Spring Bean definitions. Within the class, we will define a method annotated with that bean that returns a new instance of REST template. This method allows Spring to manage the lifecycle of the REST template bean, enabling us to easily inject it into other components of our application where needed. With this bean configured, we can now seamlessly perform HTTP requests in a more efficient manner. Now let's take a look at how we can create a service class that uses our configured REST template. This service, annotated with @service, will handle fetching data from an external football match API. We will use the @autowired annotation to inject the REST template instance into our services constructor, ensuring it is available for use in our API calls. In this service class, we will define a method aimed at retrieving match details. Specifically, this method will execute a GET request to the API URL, converting the response into an array of match objects. To handle potential null responses gracefully, we ensure that if no matches are found, an empty array is returned to avoid any null pointer exceptions. This approach emphasizes clean error handling while maintaining the usability of the service. Now let's take a look at how we can define the match class, which serves as our data model for the match objects we will work with. In this class, we use annotations from the Jackson library, specifically JSON property, to indicate how the fields in our class should map to the corresponding properties in the incoming JSON data returned from the API. This mapping is essential for Jackson to properly deserialize the JSON into Java objects. Each property, such as ID, home team, away team, and score, is defined with private access, and we provide public getters and setters for each field. This ensures that Spring can interact with our fields effectively, enabling smooth data access and manipulation. Next, we'll implement the Match Controller class, which is designed to handle HTTP requests related to match data. By using the @REST controller and @REQUEST mapping annotations, we specify that this controller will respond to requests made to the /API/matches endpoint. The controller has a dependency on the match service, which we inject through the constructor, ensuring that our controller remains decoupled from the service logic. In the getAllMatches method, which is linked to HTTP GET-requests, it calls the service method to fetch all matches, effectively delegating the data fetching responsibility. This design keeps our application modular and enhances maintainability. Now let's implement a custom exception to handle specific errors we might encounter while interacting with external APIs. We start by creating a match service exception, which extends runtime exception. This custom exception allows us to throw meaningful error messages whenever there's an issue fetching match data, improving debugging and error reporting. Next, we will enhance the getAllMatches method in our match service. To handle errors during the API call, we wrap the call to REST template get4object in a try-catch block. If a Restclient exception occurs due to network issues or an invalid response, we throw our match service exception with a clear message, indicating the nature of the failure. This structured approach ensures that any issues are communicated back to the controller gracefully, maintaining organized error management. Now let's take a look at how to create a global exception handler using the @controller_advice annotation. We define a global exception handler that listens for match service exception instances. When one is caught, it returns a standardized error response with a 500 status code. This global handler ensures that all service errors are dealt with uniformly, simplifying client-side error handling across the application. Now that we have set up our match service, let's implement the functionality to create a new match in our application. First, we define a createMatch method that utilizes the post4object function of the REST template. This method takes a match object as an argument and sends it as part of a post request to the specified API URL. The Restful API will then process this data, create a new match record, and return the result, which we expect to be a match object that represents the newly created resource. Next, let's see how we can implement an endpoint in our match controller to expose this functionality to clients. We annotate the createMatch method with @PostMapping, indicating that it will handle HTTP POST requests. By using the @RequestBody annotation, we can map the incoming JSON payload directly to a match object. This setup ensures that clients can create new matches by sending the appropriate JSON data in the request body, thus leveraging the CRUD capabilities of our application. Through this implementation, we provide a clear and accessible way for applications to interact with the Football Match API and manage match records efficiently. Next, we will write the method to update an existing match by sending a PUT request to our API. The updateMatch method uses the REST template's put function, which allows us to send an updated match object to the specified endpoint constructed from the base API URL and the match ID. It's important that the match already exists on the server to successfully update it, so ensure the API is set up to handle such requests properly. Now let's see how we can implement the endpoint in our controller to facilitate this update operation. By utilizing the @PutMapping annotation, we can map the incoming PUT request to our updateMatch method. Here, we extract the match ID from the URI using @path variable and the updated match data through the @RequestBody annotation, which indicates that the data will be provided in the body of the request. Finally, we will implement the method to delete a match, marking a thoughtful approach to API design that supports full CRUD functionality. The deleteMatch method in the service uses the delete method of REST template to remove a match from the server, while the controller captures delete requests similarly with the @deleteMapping annotation. This neat setup allows our application to effectively manage match data throughout its lifecycle. In conclusion, consuming APIs from another Spring Boot application using Restclient offers an intuitive and clean way to handle HTTP requests, providing you with the tools to interact effectively with external services. From setting up your dependencies to implementing CRUD operations, you are now equipped to build robust applications that leverage external data. As you proceed, I encourage you to explore more advanced features such as customizing request headers, adding authentication, and configuring interceptors for logging or additional processing. With Restclient, you're not limited to just basic requests. The opportunities are vast. So that wraps up our exploration of consuming APIs with Restclient in Spring Boot. Remember, ensure you validate your inputs, handle errors gracefully, and keep the user experience at the forefront of your designs. Keep experimenting and happy coding. In today's lesson, we will explore a crucial topic in software development, mocking a Restful API. This technique enables us to test client applications without relying on the availability of external services. So far, we learned about the new Restclient component in Spring Boot 3.2, which simplifies API consumption compared to older methods. We covered setting up dependencies, creating service classes, and defining REST controllers for interacting with a football match API. Additionally, we discussed implementing error handling, performing CRUD operations, and the benefits of using a fluent API design. Now, we will cover how to effectively mock a Restful API to streamline our testing processes and improve application stability. Imagine you're developing a Spring Boot application that needs to make HTTP calls to an external service. When it comes to testing your functions, however, relying on that external service can be a real headache. Not only could it be down or slow, but you also risk getting inconsistent data. That's where mocking comes to the rescue. By creating a mock of the Restful API, you can control the responses it returns during testing. This leads to faster, more reliable tests. To implement mocking within our Spring Boot application, we can leverage frameworks like Mockito for unit tests, or using libraries like WireMock for more advanced scenarios. First, let's begin with a basic example of how to use Mockito along with JUnit to mock dependencies in our service class that calls an external API. Next, we will write the necessary dependencies for Mockito and JUnit in our POM XML, which will allow us to perform unit testing in our Spring Boot application. We need to include the Mockito dependency for mocking purposes and the Spring Boot starter test dependency to leverage Spring's testing support. Both dependencies are scoped for testing, which means they won't be included in the production build of our application. Now let's take a look at the test class matchServiceTest, where we implement unit tests for our match service. We begin by importing the necessary Mockito and JUnit classes. The @mock annotation is used to create a mock instance of REST template, which is a crucial component for making REST API calls. This mock will simulate the behavior of an actual REST template instance without hitting any external endpoints. The @injectMocks annotation initializes the match service, allowing it to use the mocked REST template. In the setup method, we utilize Mockito annotations, openMocks this, to initialize our mocks before each test is executed. Within the test method test_getAllMatches, we define how the mocked REST template should behave when the getForObject method is called, instructing it to return our mock data. Finally, we assert that the returned matches are not null and validate that we received the expected number of matches, fostering reliable and isolated tests. Now let's see how we can implement WireMock in our integration tests for the match service. First, we add the WireMock dependency to our POM XML, which allows us to start a mock server that mimics the behavior of an external API. This is crucial for ensuring our tests do not depend on the actual external service being available. Next, we create a test class for our integration test, annotating it to indicate it will use Spring's testing framework. Within this class, we define a WireMock rule that configures the mock server to run on a specified port, in this case, port 8080. This setup ensures that our match service will interact with the WireMock server during testing, rather than making real HTTP calls. In the setup method, we initialize our match service and start the WireMock server. This allows us to configure the expected behavior of our mock server before each test runs. We use the stub_for function to indicate what response should be served when a request is made to the /API/matches endpoint, including setting the response's HTTP status and content type. Finally, we call the service method and validate the results to ensure that our implementation behaves as expected when interacting with the mock server. Now that we've looked at mocking with both Mockito and WireMock, let's talk about some best practices when mocking APIs. First and foremost, it's essential to keep your tests fast and reliable. That means avoiding dependencies on real network calls whenever possible. It's often more efficient to create mocks that return predictable responses. Another best practice is to handle different scenarios. For instance, when testing error cases, your mock should return 404, 500, or other HTTP response codes as appropriate. This helps verify that your application handles such cases gracefully rather than just assuming every request will succeed. Also, don't forget to include assertions in your tests to validate that your application reacts correctly to both successful and unsuccessful responses. This can include checking the correctness of the data returned or ensuring that specific exceptions are thrown in response to error states. Additionally, consider organizing your test cases to cover various scenarios systematically. You can use JUnit parameterized tests or similar frameworks to handle this without duplicating code. Aim for clarity and maintainability in your test suite as it grows, which will help you catch potential issues early on. Finally, remember to keep the mocking framework updated. Whether you're using Mockito, WireMock, or any other library, ensure that you stay current with new releases. Libraries evolve, and newer versions often bring enhanced features and bug fixes that can make your testing more effective. As we conclude, mocking a Restful API is an essential technique that empowers us to create robust, reliable tests for our applications. By using tools like Mockito and WireMock, we can simulate various scenarios, control responses, and ultimately make our software more resilient to changes and failures in external services. In our journey so far with Spring Boot, we've learned how to consume APIs elegantly through the Restclient, implement service classes, and handle errors. Moving forward, being proficient in mocking will enhance our capabilities in developing and testing applications that truly stand the test of time. Keep practicing these techniques and don't hesitate to create mock scenarios tailored to your specific application needs. Happy coding! In today's lesson, we'll dive into enhancing API responses using standard codes. This is an essential part of developing robust and user-friendly applications. So far, we learned about the importance of mocking a Restful API in software development to enhance the reliability of tests without depending on external services. We explored the use of the new Restclient component in Spring Boot 3.2 for easier API consumption and discussed implementing error handling and CRUD operations. Through hands-on examples, we covered using Mockito for unit tests and WireMock for more complex integration testing scenarios. Now, we will cover how to implement standard HTTP status codes in our responses to ensure clear communication between our API and its consumers. Standard HTTP status codes serve as a universal language between clients and servers. They inform users about the outcome of their requests, everything from successful responses to various error types. Let's begin by discussing the most common status codes and how to return them in our Spring Boot application. The most frequently used codes include 200 for success, 201 for resource creation, 204 for no content, 400 for client errors, and 500 for server errors. By adhering to these conventions, we can create a more intuitive and predictable API experience. The displayed chart titled HTTP Status Code Distribution shows concrete counts for these common response categories and reinforces why standard codes are meaningful. The bar heights and data labels indicate absolute occurrences. 200 OK equals 150, 201 created equals 100, 204 no content, 70, 400 bad request equals 50, and 500 internal server error equals 30, summing to 400 total responses. Interpreting these numbers, successful responses 200 and 201 account for 62.5% of outcomes, 150 plus 100 equals 250, with 200 OK alone representing 37.5% and 201 created 25%. Responses that signal no content are 17.5%, while client errors 400 and server errors 500 represent 12.5% and 7.5% respectively. The overlaid dashed trend line, fitted across the 5 categories, slopes downward, reflecting a clear decline in occurrence as status codes move from routine success toward error conditions. From these patterns, we can conclude the system is predominantly returning successful outcomes, creation events are common, and error rates, though lower, are non-negligible. This suggests prioritizing monitoring and mitigation for 400 series issues to improve client request validation, and keeping a close eye on 500 series counts to catch and resolve server-side faults early. Now let's implement the following code for our product management API, focusing on how we create a new product. In our product controller class, we define an endpoint for handling post requests to the /API/products URL. By annotating the class with @RestController, we indicate that this class will manage res-tful requests and responses. Here, the @post mapping annotation on the createProduct method signifies that this method will process incoming post requests. It accepts a product object in the request body, which we expect to contain the details for the new product. Inside the method, we invoke the SaveProduct method from our product service, which handles the business logic of saving the product. If the product is saved successfully, we utilize the ResponseEntity class to construct a response that includes the created product and the HTTP status code, HTTP status created. This approach clearly communicates to the client that their request was processed successfully, and a new resource has been created, providing clarity and enhancing the overall experience for API consumers. Now let's see how we can implement error handling in our product creation process. The code checks if critical fields like product name and price are present in the incoming request. Before attempting to save the product, it validates these fields to ensure they aren't null, which is essential for maintaining data integrity. If either the name or the price is missing, we return a response entity with a 400 bad request status. This response acts like a helpful reminder to the client, indicating that the request lacks necessary information. By handling validations this way, we not only inform the client about the specific error, but we also minimize confusion and streamline their experience with the API. If all required fields are present, we proceed to save the product using the product service. Upon successful creation, we respond with a response entity containing the newly created product along with a 201 created status. This clear feedback loop ensures that the client understands their request has been successfully processed, fostering a more trustworthy interaction with the API. Through this implementation, we enhance both functionality and user experience in our application. Next, we will implement exception handling for server errors in our application. In this example, we define a method to retrieve a product by its ID using the @getMapping annotation. The method takes a product ID as a path variable and attempts to fetch the product through the product service. Now let's see how we handle potential errors during this process. We wrap the retrieval logic in a try-catch block, which allows us to gracefully manage any exceptions that might occur. If the product is found, we check if it is null. If it is, we return a response with a 404 not found status, indicating that the specified resource doesn't exist. However, if an unexpected exception occurs during the retrieval, perhaps due to a database issue, we catch that exception and respond with a 500 internal server error status. This approach is crucial for maintaining user trust. By handling errors appropriately, we ensure that the client receives clear feedback instead of a confusing or uninformative message. This not only enhances the robustness of our API, but also significantly improves the overall user experience when interacting with our application. Now let's see how we can enhance our API responses when validation errors occur. In this implementation of the createProduct method, we're introducing a mechanism to check whether the required fields in the request are properly populated. Here, if the product's name is missing, we construct a JSON object that contains a clear and helpful error message. Product name is required. Next, we return this JSON error response along with a bad request status code, specifically 400. This allows the client to easily understand what went wrong with their request, improving their experience and making it easier for them to correct their submission. By providing detailed error messages in the response body, we enhance transparency and user feedback. This practice aligns with our overall goal of creating a more intuitive API, as it not only communicates the status of the request, but also guides developers on what adjustments they need to make. It's an effective way to ensure clarity and facilitate a smoother development experience when interacting with our API. Now let's implement the following method to enhance the product retrieval process. We will create a getProductById method that receives a product ID as a path variable. Inside this method, we invoke our product service to find the product matching the given ID. To improve the response, we check if the product is found. If it is, we will return a successful response with an HTTP status of 200 OK, along with the product data. Importantly, we add a custom header called xCustomHeader for additional context in the response. This practice not only provides more information to the client, but also demonstrates how headers can be effectively used to enrich API interactions without compromising the data structure. If the product is not found, however, we return a 404 not found status, ensuring that clients receive clear feedback regarding the absence of the requested resource. This method illustrates how to combine status codes and headers in our API responses, thereby making the API more informative and user-friendly. Now let's implement a global exception handling mechanism using Spring's @controller advice annotation to manage our application's errors effectively. This approach will allow us to centralize error handling, making our controllers cleaner and more focused on their primary responsibilities. In our global exception handler class, we start by annotating it with @controller advice, which indicates that this class will handle exceptions across all controllers. Next, we define a method specifically for handling resource not found exception. This method listens for any instance of resource not found exception that occurs within our application. When this exception is thrown, the handle resource not found method will be triggered. Inside this method, we create a hash map to store the error message, which will detail why the resource was not found by calling xGetMessage. This error message is then used to construct a new response entity, which combines our error response with an HTTP status code of NOT_found. This structure not only captures the error effectively, but also enhances the clarity of the responses sent to clients, allowing them to understand and address issues efficiently. Additionally, we can easily add more exception handler methods for different types of exceptions in this same class, making our error handling strategy comprehensive and organized. As we wrap up this section, let's take one more look at our product API. We've covered how to respond with standard HTTP codes for successful operations and various error scenarios. By implementing these conventions, we create a robust and friendly API. Understanding how to enhance your API responses goes beyond merely adding status codes. It involves creating a seamless user experience. A well-structured API encourages developers to integrate your service into their applications without a hitch. So in this lesson, we've explored how to enhance API responses using standard codes, from success indicators to error messages. We have also covered several key practices for ensuring clear communication and a positive developer experience. As you move forward with your API development, always prioritize clarity and consistency in your responses. Until next time, happy coding. Now that we have established our Restful API, the next logical step in our development journey is to enhance our API's documentation using Openapi. Documentation is a critical aspect of API development as it provides clarity and guidance to users who consume your API. In this lesson, we will discuss how to utilize Openapi to create comprehensive documentation for our Spring Boot application. So far, we learned about enhancing API responses using standard HTTP status codes to ensure clear communication between clients and servers. We discussed the importance of mocking a Restful API and explored the use of Spring Boot's Restclient for error handling and CRUD operations. Additionally, we covered implementing validation checks for requests and how to handle errors gracefully while providing meaningful feedback to API consumers. Lastly, we emphasized the significance of using global exception handling to maintain a clean and efficient approach to managing errors across the application. To kick things off, let's define what Openapi actually is. Openapi, formerly known as Swagger, is a specification for building APIs that focuses primarily on the documentation aspect. It allows developers to define the structure of their APIs in a standard format, making it easier for consumers to understand how to interact with the API. With Openapi, you can describe your endpoints, the request and response structures, authentication methods, and much more. The beauty of using Openapi lies in its ability to generate interactive documentation that serves as a living reference point for your API, making life easier for both developers and consumers. Now let's see how we can enhance our Spring Boot application with the necessary dependency to integrate Openapi documentation seamlessly. To accomplish this, we will add the SpringDoc dependency to our project's POM XML. This is essential as the SpringDoc library allows for the straightforward inclusion of Openapi functionality, requiring minimal configuration on our part. This dependency will enable us to leverage SpringDoc's capabilities to automatically generate API documentation and provide interactive examples for consumers. The dependency section includes the group ID org SpringDoc, the artifact ID SpringDoc Openapi, and the specified version 1614. By including this in your POM XML file and refreshing your Maven project, you set the foundation for exposing your API documentation through URLs that are typically /v3/API docs for the Openapi specification and Swagger UI HTML for the interactive documentation interface. This setup is critical because it allows users to access a live documentation of your API directly through their browser, providing them with clear insights into the available endpoints and options for interacting with your application. Now let's take a look at how we can implement our product controller, which serves as the backbone of our API for managing products. This controller is annotated with @RESTController, signifying that it will handle incoming HTTP requests and return JSON responses. We use @request mapping to define the base path for our endpoints, in this case, /API/products. Next, we inject the product service using @AutoWired, allowing us to leverage its methods for handling product data seamlessly. The core of our functionality is the getProductById method, which is decorated with @getMapping/ID to specify that it responds to GET requests targeting the product ID. Within this method, we utilize @operation to provide a summary and description of its purpose, ensuring the API documentation is clear. The method is also annotated with @API response to denote potential responses, including a success scenario, HTTP 200, when the product is found, and an error scenario, HTTP 404, when the product does not exist. Ultimately, this implementation not only facilitates clear interaction with our API, but also enriches our documentation, enhancing the overall consumer experience. The displayed chart titled Key Aspects of API Development and Documentation presents 5 aspects with explicit importance levels. OpenAPI 30, HTTP codes 25, API documentation 20, error handling 15, and validation checks 10. Each aspect is shown as a horizontal bar with a numeric label at the end of the bar indicating its importance value. The clear pattern is that OpenAPI receives the highest emphasis, followed closely by HTTP status codes, while API documentation itself is a strong but slightly lower priority, and error handling and validation checks are comparatively lower on the scale. From this distribution, we can conclude that, in the context represented, investing effort first in formalizing API structure with OpenAPI and in standardizing HTTP response codes will yield the largest documentation and communication benefits. Nevertheless, the presence of non-zero values for error handling and validation checks highlights that robustness and input validation remain necessary foundations, even if they are lower priority items in this particular prioritization. The distinct colors for each bar separate the concerns visually, and the numeric labels make it straightforward to compare the relative weights and to justify allocating development and documentation time according to these ranked priorities. In this snippet, we set up our product controller to expose a GET endpoint for retrieving products. By using the @OpenAPI definition annotation, we define the title, version, and description of our API. Each endpoint inside the controller can further be documented using @operation and @API response annotations, which explain what the endpoint does and what responses to expect. This not only makes your code cleaner, but also ensures that consumers of your API have a clear understanding of its functionality. Now let's dive into the implementation of our product model, which plays a key role in defining the structure for our requests and responses. To establish our product object, we utilize several annotations that enhance the clarity and functionality of our code. The data annotation from Lombok automatically generates boilerplate code such as getters, setters, and toString methods, making our class concise and readable. We also add @noArgs constructor and @allargs constructor, which create constructors that facilitate the creation of product instances with or without parameters. This ensures we can easily manipulate our products in various contexts. To make our API self-describing, we employ the @schema annotation from OpenAPI, which helps us document the model effectively. Each field within the product class is annotated with @schema, providing details about the data types and examples. For instance, the ID, name, and price fields are clearly defined, allowing API consumers to understand what data to expect. By implementing these features, we enhance both the visibility and usability of our API, ensuring that developers have a clear understanding of how to use the product model effectively. Next, we will write the following code to implement a post endpoint for creating a new product in our inventory. This method is annotated with @postMapping, indicating that it will handle HTTP post requests. We have also added @operation annotations to provide a summary and description of the endpoint, which helps consumers understand its purpose. The @API response annotations clarify the possible outcomes, specifically a successful creation with a 201 status code and a 400 status code for invalid input. Now let's take a look at the method's signature. It accepts an object of type product, which is supplied in the request body and validated using the @valid annotation. This integration of validation ensures that incoming data adheres to the defined model requirements, enhancing the robustness of our API. When the method is invoked, it calls the saveProduct method from the product service, which handles the logic for storing the product. Finally, upon successful creation, we return a response entity containing the created product and an HTTP status of 201, signifying a successful operation. This approach provides clear communication about what is required and what consumers can expect in response. After we have enabled OpenAPI and documented our endpoints, you can start the application and navigate to Swagger UI HTML in your browser. This interface will provide you with an interactive documentation experience. You will be able to see all your documented endpoints, the expected request parameters, response types, and even execute calls to your API directly from the browser. How cool is that? It's like having a live demo of your API right at your fingertips. Additionally, OpenAPI supports versioning, which allows you to maintain different versions of your API documentation as your application evolves. This is particularly useful in ensuring backward compatibility for applications that might rely on an older version of your API. To handle this, you can specify different versions in the @OpenAPI definition annotation, ensuring consumers know which version they are interacting with. Now let's see how we can enhance our API documentation by integrating security definitions using OpenAPI annotations. In the code, we begin by defining the overall API characteristics with the @OpenAPI definition annotation. Here, we specify the API title, version, and description, which collectively inform consumers about the purpose and scope of our API. Additionally, the security requirement is outlined, indicating that all requests to this API need to be authenticated with a bearer token, specifically employing JWT, JSON web tokens. Next, we implement the @security scheme annotation, where we define the specifics of the security mechanism. The name bearerauth identifies the scheme used, while the type is set to HTTP, and the scheme is designated as bearer. Moreover, the bearer format is designated as JWT, providing a clear template of the authentication expected from users. By incorporating these annotations, we create transparency regarding the authentication process, allowing API consumers to understand how they should authenticate their requests and what security measures are in place, thereby reinforcing the professionalism and reliability of our API documentation. Now let's take a look at how we can enhance our API documentation by specifying the expected responses using the @API response annotation. This annotation allows us to define not only the HTTP status codes, but also the structure of the responses, creating a clearer communication channel for API consumers regarding what they can expect. In our example, we define two responses for a product creation endpoint. The first one indicates a successful operation with a 201 status code, describing that the product was created successfully. Here, we also specify the content type as application/JSON and point to the product class schema, helping users understand the expected structure of the successful response. On the flip side, we also handle potential errors by documenting the 400 status code, which signifies invalid input. Again, we provide a response structure consisting of an error response model, which contains the message, status, and timestamp, ensuring that any relevant feedback regarding errors is clear to the client. This approach not only enhances the user experience, but also reduces confusion during integration, allowing developers to pinpoint issues easily. Finally, it's important to remember that documenting your API using OpenAPI is not a one-time task. As your application evolves, you should continuously update your documentation. Automated tools can help with this. For example, integrating a pre-commit hook can ensure your OpenAPI documentation stays up to date with your code base. This means the documentation is always current, which enhances reliability for users relying on your API. In conclusion, utilizing OpenAPI for documenting your Spring Boot APIs is an effective way to provide clarity and usability to your application. It helps ensure that both you and the consumers of your API are on the same page, making it easier to develop, debug, and expand your API in the future. The combination of detailed documentation, interactive capabilities, and clear communication through annotations makes OpenAPI a powerful asset in your development toolkit. As you move forward in your development endeavors, remember always to prioritize documentation alongside functionality. It not only serves your users, but also guides you as you iterate on your code. With that said, I hope you're excited to start integrating OpenAPI into your projects, and I can't wait to see how well documented your APIs will become. Happy coding! Now that we have our Restful API properly documented, it's time to create a consumer application that can interact with it. In today's lesson, we will focus on implementing an API client using Feign, a declarative web service client that makes writing HTTP clients easier. So far, we learned about enhancing our API documentation using OpenAPI, ensuring effective communication between developers and API users. Now we will cover how to set up a Feign client to consume our API services seamlessly. Now let's take a look at how to enable Feign clients in our Spring Boot application. We accomplish this by adding the @enable Feign clients annotation to our main application class. This annotation instructs Spring to scan for interfaces annotated with @Feignclient, thus enabling the application to recognize and utilize our Feign clients throughout the app. By doing this, we set the groundwork for seamless communication with our existing Restful API, allowing us to focus more on the application's functionality rather than getting bogged down in HTTP client complexity. Next, we will write the interface for our Feignclient. In this case, we will be defining a product client interface, which will declare methods for interacting with our product-related API endpoints. This interface will be annotated with @Feignclient, specifying the name of the client and the base URL for the API. Each method within this interface will map to the corresponding API operation, utilizing annotations like @getMapping for retrieval and @postMapping for creation. These annotations make it clear and convenient to define the expected interactions with our API. Thus, through this interface, we effectively eliminate boilerplate code while retaining the expressiveness needed to define HTTP requests. Displayed figure is a group bar chart titled Importance of Key Features in API Client Implementation that ranks 5 API client features along the x-axis with corresponding importance levels on the y-axis percentages. The features and their displayed importance values are simplified HTTP calls 30%, error handling 25%, documentation 20%, dependency management 15%, and performance monitoring 10%. The bars are ordered by feature labels on the x-axis, and each bar has its exact percentage shown above it, making the relative differences immediately apparent. Key patterns visible in the chart are a clear descending priority from left to right. The chart emphasizes that simplified HTTP calls and error handling together account for the majority of perceived importance, 55%. Documentation holds a significant but smaller share, 20%, and dependency management and performance monitoring are lower priorities, 15% and 10% respectively. From these values, we can conclude that, when implementing an API client, practitioners tend to prioritize making HTTP interactions straightforward and resilient first, then ensuring clear documentation, while treating dependency handling and runtime performance as important but secondary concerns. Next, we will implement the main application class for our Spring Boot application. To enable Feignclients, we need to use the @enable Feignclients annotation alongside the @Spring Boot application annotation. The @Spring Boot application annotation serves as the entry point for our Spring Boot application, signaling to the framework that this is where the application should start. By including @enable Feignclients, we instruct Spring to scan for any interfaces annotated with @Feignclient, enabling them for dependency injection. Now let's see how we can do this effectively. We begin by creating a new Java class which we'll name MyApplication. This class will contain our main method where we invoke Spring Application Run, passing in the current class and any command line arguments. This setup is crucial as it kickstarts the Spring framework, initializing all components, including our Feignclients. As we lay this groundwork, we're preparing our application to seamlessly communicate with the Restful API, enhancing our ability to consume services without manually handling HTTP operations. This structured approach sets a solid foundation for further development in our API client implementation. Now let's implement the Feignclient to interact with our Restful API for product details. The code begins with an interface, product client, which is annotated with @Feignclient. This annotation specifies the client name, product service, and provides a base URL fetched from the application's properties, allowing for flexible API endpoint management across different environments. Within this interface, we define a method, getProductById, which utilizes the @getMapping annotation. This maps the method to an HTTP GET request directed at the specified endpoint, /API/product/ID. Here, we use @path variable to indicate that the method requires a dynamic product ID as input. Next, we need to configure the base URL for our API by adding it to the application properties, or application, YAML file, ensuring that our application can correctly reach the API service during development. This setup not only automates the process of calling the API, but also abstracts away the cumbersome boilerplate code typically involved in making HTTP requests. With our product client defined, we can seamlessly fetch product details by invoking the getProductById method, streamlining our interaction with the underlying Restful service. Now let's implement the product service class, which will serve as an intermediary between our application and the Feignclient. In this class, we use the @service annotation to mark it as a Spring-managed component. By injecting the product client into product service with the @autowired annotation, we enable seamless interaction with our Feignclient, allowing us to access its methods without creating instances ourselves. Next, we will define a method called FindProductById, which takes a product ID as an argument. This method utilizes the injected product client to call the getProductById method from the Feignclient interface, effectively translating the method call into an HTTP GET request to our API to retrieve product details. This cleanly abstracts the complexity of making HTTP requests and keeps our service layer focused on business logic. When FindProductById is executed, it provides a straightforward way to interact with our Restful API, ensuring that the necessary product information is retrieved efficiently and without unnecessary boilerplate code. Now let's see how we can extend our product client interface to support product creation. We begin by adding a new method that sends a post request to our REST API, enabling us to create new products directly through our Feignclient. This method is annotated with @postmapping/API/products, indicating the endpoint where the request will be directed. The method accepts a product object as its parameter, wrapped inside a @request_body annotation, which tells Spring to serialize the product into JSON for transmission. Next, we incorporate this new method into our existing product client interface. By integrating both the GET method for retrieving products and our newly defined post method, we set up a comprehensive API client that can both fetch and create products with minimal boilerplate code. This design emphasizes clarity and maintainability, allowing developers to interact with the API seamlessly. The benefits of this approach become apparent as it simplifies CRUD operations within your application, facilitating easier integration with the underlying Restful API and enhancing your overall coding experience. Now let's see how we can implement the addProduct method within our product service. This method serves as a vital part of the service layer, enabling us to interact with the API for creating new products. In this implementation, we accept a product object as an argument and utilize the product client to send that object to our Restful API using the createProduct method. This process efficiently handles the transformation of our product object into JSON format, thanks to Spring's integration with Jackson, which takes care of serialization automatically. The return value of this method is crucial. It provides us with the created product, which allows for further processing or verification if necessary. This seamless exchange between our service and the API enables us to add new products without the need to manually handle HTTP requests, effectively streamlining our workflow. By encapsulating this logic within the addProduct method, we maintain a clean and organized code structure, ensuring that our focus remains on business logic while the underlying interactions with the API are efficiently managed. Now let's implement our fallback mechanism to handle errors gracefully in our Feignclient. First, we'll create a new class called ProductClientFallback, which implements the product client interface. Within this class, we'll need to override the methods defined in the interface. For instance, in the getProductById method, we can return a null value, indicating that no product is found, or we could throw a custom exception to provide more informative feedback. Similarly, in the createProduct method, returning null can help signify that the product creation failed, allowing us to gracefully handle such scenarios within our application. Next, we must integrate this fallback into our product client definition. By adding the fallback attribute in the @Feignclient annotation, we specify our fallback implementation class. This means that when the underlying service encounters issues, be it due to downtime or an error response, our fallback methods will take over. This mechanism ensures that our application remains robust and continues to function smoothly, allowing for the return of default values and management of exceptions when external services are temporarily unavailable. Now that we have set up our Feignclient and service, let's implement our test class to ensure our application behaves as expected. We start by annotating our test class with @SpringBootTest, which sets up the Spring application context for our tests. Within this context, we use the @mockBean annotation to create a mock of the product client. This allows us to define controlled behaviors for its methods without relying on the actual implementation. Next, we auto-wire the product service, which will use our mocked product client in place of the real one. In our test method, we will simulate the response of the getProductById method of the mocked client. Here, we create a mock product with an ID, name, and price. By using the when method from Mockito, we dictate that whenever getProductById is called with an ID of 1, it should return our mock product. Finally, we invoke the findProductById method on the product service and assert that the returned product's name matches our mock product's name. This validation ensures that our service behaves correctly when interacting with the Feignclient. As we wrap this lesson up, it's important to take a step back and appreciate the simplicity and power of using Feign within our Spring Boot applications. By abstracting away the complexities of HTTP communications, we've made our lives easier and our code cleaner. Using Feignclients allows us to focus on the business logic while still benefiting from powerful HTTP features without crafting verbose client code. Whether you're creating single-page applications or microservices, integrating Feign can drastically boost your productivity and code maintainability. In summary, today we dove into implementing an API client with Feign in Spring Boot. We learned about setting up the Feignclient, making HTTP requests using Java interfaces, handling errors, and even the basics of testing our client. As you progress in your Spring Boot journey, remember that effective communication with external systems is key, and tools like Feign make that a breeze. Happy coding! In today's lesson, we're going to explore a crucial aspect of working with remote services in Spring Boot applications, mocking remote services for testing. One of the main drawbacks of using a remote service, as we discussed previously, is that you need the remote service up and running during the testing phase of your client application. This can lead to complications, particularly if that remote service is unavailable or unstable during your tests. By mocking these remote service calls, we can isolate our tests from external dependencies, ensuring that they are fast, reliable, and repeatable. So far, we learned about creating a consumer application that interacts with a RESTful API using Feign, a declarative web service client. We enhanced our API documentation with Openapi, set up the Feignclient in a Spring Boot application, and developed methods for making HTTP requests to retrieve and create products. Additionally, we discussed implementing error handling with fallback mechanisms and testing the client using a mocking framework. This lesson will dive deeper into the benefits of mocking and how to effectively implement it using popular libraries in the Spring Boot ecosystem. Let's begin by addressing the importance of mocking in testing. As developers, our primary goal is to write robust applications. However, when our application interacts with external APIs, it becomes susceptible to issues like network latency, downtime, and unexpected changes in the API. These external factors can lead to unreliable tests, which is something we definitely want to avoid. By mocking remote services, we create a controlled environment for our tests, allowing us to focus on the functionality of our application while eliminating these external variables. Mocking means creating a simulated version of an object that mimics the behavior of the real object without relying on the actual implementation. For our case, this means we can simulate the behavior of our remote services when testing our Feign clients. By doing so, we can ensure that our client calls work as intended regardless of the availability of the external service. The displayed pie chart titled Benefits of Mocking Remote Services for Testing quantifies 5 distinct benefits and their relative contributions. Faster tests 30%, isolated testing 25%, stable environment 20%, no network dependency 15%, and reliable outcomes 10%. The key pattern is that the largest shares are focused on test execution speed and isolation. The two largest slices together sum to 55%, indicating that the primary advantage teams expect from mocking is faster, more focused unit tests that do not depend on external systems. The next largest slice, stable environment, 20%, together with no network dependency, 15%, emphasizes that mocking substantially reduces variability caused by external service state or connectivity. These two together account for 35% and highlight reliability gains beyond purely execution speed. Finally, reliable outcomes at 10% shows that while correctness and repeatability are valued, they are represented as a smaller but still meaningful part of the overall benefit profile. From this distribution, we can conclude that practitioners prioritize speed and isolation when adopting mocking strategies, while stability and independence from network conditions are also important supporting benefits, and consistent test outcomes are a complementary advantage. Now let's see how we can implement our test class for the product service using Mockito. We begin by importing necessary classes from the testing framework in Mockito library, including test, @mock, @inject mocks, and several Mockito static methods. Within our test class, we declare a mock instance of product client using the @mock annotation, which tells Mockito to create a virtual version of this component for our tests. To facilitate testing and ensure correct dependencies are injected, we also use the @inject mocks annotation on product service. This will automatically inject our mock product client into product service so that when we call methods on product service, it uses the mocked client. Inside the constructor of our test class, we invoke Mockito annotations, open mocks this, to initialize the mocks and make sure they are ready for use. Next, we implement our test method, test find product by id. In this method, we set up the mock to return a predefined product object when the getProductById method is called with an ID of 1L. After invoking the findProductById method on our service, we check that the product name returned matches our expectation and verify that the getProductById method was indeed called once, ensuring that our test confirms the correct interactions. Now let's implement the following test to handle a scenario where the remote service fails, showcasing Mockito's ability to simulate exceptions. We begin by using the when, then throw method to set up our mock product client, specifying that when the getProductById method is called with the ID 1, it should throw a runtime exception with the message service not available. This step allows us to rigorously test how our product service handles failures from remote services, ensuring that our application can respond gracefully. We invoke the findProductById method of our product service within an assertion that expects a runtime exception to be thrown. This is done using assert throws, which helps confirm that our service's error handling mechanism is robust. Finally, we assert that the exception message matches our predetermined expectation, ensuring that the integrity of our application is maintained even in the face of external failures. This approach not only enhances our test coverage, but also validates our application's fault tolerance, critical in production scenarios where remote services can be unreliable. This is how we can ensure that our application responds appropriately to service disruptions, maintaining a high level of reliability. Now that we've covered the basics of mocking with Mockito, let's take a moment to discuss the annotations and their significance. The @mock annotation creates a mock instance, allowing you to define how that mock should behave. The @inject mocks annotation is particularly useful as it automatically injects our mock instances into our service or component, enabling a clean setup for testing. The Mockito annotations, open mocks this, call initializes those mocks. It's essential to include this step unless you want to see your tests mysteriously fail because the mocks are null. Additionally, you can also utilize @before each methods to set up more complex test scenarios if necessary. This flexibility means you can create complex mocks or shared setup logic that applies to multiple test cases without duplicating code. Now let's take a look at how we can verify interactions with our mocked product client using Mockito. In the provided code, we are using the verify method, which is a core feature of Mockito that allows us to confirm that specific methods were called on our mock objects. Here, we are asserting that the getProductById method of the product client was invoked with any long value as an argument. This is accomplished using the anyLong argument matcher, which provides flexibility in our assertions. Instead of checking for a specific product ID, we can verify that the method was called regardless of the actual ID passed. This is particularly useful in tests where the specific parameter is not important, we only care about the interaction itself. Utilizing argument matchers in this way allows us to write more resilient tests that can accommodate varying inputs without compromising the validation of crucial interactions within the application. By employing such techniques, we ensure our tests remain robust and maintainable as the code base evolves. Now let's implement the following stubbing for our product client's method, which will allow us to define specific responses for different product ID requests. In this case, when we call getProductById on our product client with an ID of 1L, it will return mockProduct1, and if we request a product with an ID of 2L, it will return mockProduct2. This approach is particularly useful when your test requires multiple calls to the same method, but with different parameters. By setting up the mocks this way, we can efficiently simulate various scenarios our application may encounter without relying on an active remote service. It helps ensure that our tests remain isolated, predictable, and faster, as we eliminate the need for actual service calls. This chaining mechanism for stubbing allows us to achieve sequential returns based on specific calls, making our testing strategy more versatile and our test cases cleaner and easier to maintain. Understanding how to use stubbing effectively will save us time and contribute to writing more efficient unit tests as we continue developing robust applications. As good practice, consider wrapping your service logic in a transaction boundary if it's interacting with other components, particularly in integration tests. This way, you can revert any changes to the state after tests run, ensuring your application remains consistent. Finally, always remember that while mocking is powerful, it's equally important to balance it with integration tests. An integration test can validate your application's behavior when interfacing with real remote services, confirming that the interactions truly work as expected. This is especially crucial when you're preparing for production environments. In conclusion, mocking remote services is a vital strategy for writing robust and reliable tests in your Spring Boot applications. By isolating your tests from external factors, leveraging Mockito for effective mock creation, and mastering the use of argument matchers, stubbing, and interaction verifications, you can ensure that your tests are both dependable and maintainable. So the next time you work with external services in your application, remember that you have powerful tools at your disposal to create a seamless testing experience. With this knowledge, you can ramp up your testing capabilities and ensure that your Spring Boot applications are resilient, efficient, and ready for whatever the remote service world throws at you. Happy coding! Testing and validating a Restful API is essential to ensure that our applications perform as expected. In this session, we will dive deep into creating unit tests for the Restful API built in our previous lessons. This process is critical not just for fixing bugs, but also to confirm that new features don't disrupt existing functionality. So far, we learned about the significance of mocking remote services in Spring Boot applications for efficient and reliable testing. We discussed the benefits of mocking, such as faster tests and reduced external dependencies, and explored how to implement this using the Mockito framework. Additionally, we covered creating mock instances, handling exceptions, and utilizing advanced features like argument matchers for flexible test assertions. This knowledge equips us to enhance our testing strategies while maintaining robust application performance in the face of external service interactions. Now, we're going to cover unit testing for Restful APIs to ensure our endpoints are functioning correctly. Next, we will implement the user controller, which serves as the central point for managing user-related operations in our Restful API. This controller is annotated with @RestController, indicating that it handles HTTP requests and converts the responses directly into JSON format. The @request mapping annotation specifies that all endpoints will be prefixed with users, allowing us to group related functionalities. We then inject the user service using @AutoWired, which facilitates access to business logic related to user management. The createUser method handles POST requests to create a new user. It accepts a user object in the request body, processes it through the user service, and returns the created user with a status of 201 created. For retrieving user data, the getUser method listens for GET requests with a specified user ID. It checks if the user exists and returns either the user details with a status of 200 OK or a 404 not found if the user does not exist. The updateUser method is responsible for updating user information, requiring both the user ID and the updated details. It ensures that the user is updated correctly, also returning appropriate success or failure statuses. Finally, the deleteUser method closes the loop by handling delete requests for user records. It invokes the service to remove a user by ID and confirms successful deletion with a 204 no content status. These functionalities collectively enable complete user management within our application. Now let's implement the unit tests for the user controller using Spring Boot's testing framework. We start by setting up a test class named userControllerTest, where we leverage annotations like @runWith and @SpringBootTest to facilitate the injection of the testing context. The mock MVC instance is initialized within the setup method, allowing us to simulate HTTP requests to our controller without launching the full application. Next, we employ the @mockbean annotation to create a mock instance of user service, which isolates our controller from its dependencies and enables us to define specific behaviors for our tests. In our first test, createUser, we mock the behavior of the user service to return a predefined user object when the service is invoked. By using mock-MVC perform, we simulate a post request to the user's endpoint with user data in JSON format. Following the request, we assert that the response status is 201 created and ensure that the returned JSON matches our expectations for name and email. Finally, we verify that the createUser method was called on the user service, confirming the interaction between our controller and its service layer. With this setup, we ensure that our API behaves correctly for creating new users. Now let's take a look at the unit tests for the getUser method in our user controller. We have two tests, test getUserFound and test getUserNotFound, which assess scenarios for retrieving a user based on their ID. In test getUserFound, we simulate the service layer using Mockito by returning a predefined user when the method getUserById is called with the ID 1. This allows us to verify that the controller correctly performs an HTTP GET request to the user's one endpoint and returns a 200 OK status. Furthermore, we assert that the JSON response contains the expected user attributes, namely the name and email, demonstrating how to validate the contents returned by our API. Next, we implement test getUserNotFound, where we instruct the mock service to return null when searching for a user with the same ID. Here, we anticipate a 404 not found response, showcasing the controller's ability to handle cases when a user does not exist. This structured approach ensures that our endpoint effectively manages expected outcomes and possible errors during user retrieval. Now let's delve into the unit tests for the updateUser method of our user controller. This method requires both a user ID as a path variable and user data in the request body for updating a user. First, we'll define a test case called testUpdateUser, where we create a sample user object representing the updated user. We will use Mockito to mock the response of the user service updateUser method, ensuring it returns our updated user when called with the correct ID. Next, we simulate an HTTP put request to the user's one endpoint, setting the content type to JSON and including the user data in the request body. After performing the request, we verify that the status is 200 OK and confirm the username in the response to ensure accuracy. Now let's take a look at how we handle cases when a user does not exist through the testUpdateUserNotFound. In this test, we mock the service to return null when trying to update a non-existent user, simulating the scenario and checking that the API correctly responds with a 404 not found status. This approach demonstrates the API's responsiveness to different client requests while maintaining clarity on how updates should be executed and verified. Now let's see how we can implement the unit tests for the deleteUser method in our user controller. The testDeleteUser method validates the successful deletion scenario. Here, we use Mockito's doNothing to prevent any exceptions while calling deleteUser on our mocked user service. The mock-MVC perform method simulates an HTTP delete request to the user's one endpoint, and we expect the status to return 204 no content, confirming that the deletion was successful. Afterward, we verify that the deleteUser method was indeed invoked on the service layer with the correct user ID. Next, we will write the testDeleteUserNotFound method, which handles the case when attempting to delete a non-existent user. In this scenario, we use doThrow to simulate an EntityNotFound exception, indicating that the user doesn't exist. This simulation allows us to test how our API responds when an invalid ID is specified. We perform another delete request to the same endpoint and expect to receive a 404 not found status, demonstrating that the API appropriately handles the request for a user that cannot be found. With our tests in place, we can now be confident that our Restful API behaves correctly under various conditions. Running these tests is as simple as executing the test suite, and with each successful test, you'll gain confidence that your API will respond correctly to client requests after any changes. To summarize, we covered defining unit tests for a Restful API in Spring Boot, specifically the user controller, which included testing methods for creating, retrieving, updating, and deleting users. By mocking our service layer, we could isolate our controller and ensure its behavior through various scenarios, resulting in a robust suite of tests. As you implement your own API tests, remember that thorough testing will save you time and headaches down the line. Embrace the freedom that comes with a comprehensive testing strategy and invest your efforts in writing meaningful, concise tests that capture the behavior of your application. This concludes our session on testing and validating a RESTful API. The methods discussed here are foundational to crafting reliable applications that serve their purpose efficiently. Keep practicing these concepts, and soon you'll find yourself adept at ensuring that code behaves exactly as intended. Happy coding! Let's dive into enhancing API communication with the new Restclient component introduced in Spring Framework 6.1 and available in Spring Boot since version 3.2. This exciting new feature allows developers to simplify and strengthen their RESTful API interaction. So far, we learned about the importance of testing and validating a RESTful API to ensure proper functionality and to prevent new features from breaking existing ones. We discussed how to implement unit tests for our user management API using Spring Boot, JUnit, and Mockito, focusing on testing the create, retrieve, update, and delete operations. Additionally, we explored the significance of mocking services during testing to isolate our controller and facilitate effective verification of its behavior across different scenarios. This foundational knowledge will help us build robust applications with reliable APIs. Now, we will explore how to enhance API communication with the Restclient component, making our interactions with APIs more seamless and efficient. Now let's take a look at how to set up the necessary dependencies for our Restclient configuration. The inclusion of the Spring Boot Starter web dependency in our POM XML file is essential, as it brings in all the required libraries needed for building web applications using Spring. This dependency allows us to easily work with RESTful services, enhancing the overall functionality of our application. Next, we will implement the Restclient configuration by writing a class decorated with the @configuration annotation. This tells Spring that the class will provide bean definitions for the application context. Inside this class, we will create a method annotated with @bean that returns a new instance of REST template. The REST template is a central class for client-side HTTP access in Spring, allowing us to handle all HTTP operations easier. By defining it as a bean, we promote better organization and modularity, ensuring that our application can easily manage HTTP requests and responses in a maintainable way. Now let's implement a service class that will leverage the previously configured REST template to perform API calls. In this user service class, we begin by injecting the REST template instance, promoting loose coupling and allowing us to use the predefined configuration for our API interactions. We define a base URL, which points to the hypothetical remote user API, enabling easy access to user data. Next, we create a method called getUserById, which accepts a user ID as a parameter. This method utilizes the REST template to send a GET request to the external API by constructing the full URL dynamically. The response is then automatically deserialized into a user object, allowing us to work with the user data seamlessly, as the Java class directly represents the underlying JSON structure. Now let's take a look at how we define the user class, which serves as the data model for our user entity. This class includes essential fields like ID, name, and email, along with their respective getters and setters. This straightforward approach enables efficient mapping of API responses to Java objects, simplifying data manipulation within our application. Now let's implement error handling in our user service to manage API response issues effectively. We start by replacing the previous getForObject method with getForEntity, which provides a more comprehensive way to access the HTTP response. This allows us to inspect the status code and decide how to handle various outcomes. In our implementation, we first check if the response indicates a successful operation using *20successful. If the response is successful, we return the user data from the body. However, if the API returns a non-2xx status, we throw a runtime exception, giving clear feedback about the failure. This is a crucial addition because it helps diagnose issues that could arise from the API side. Furthermore, we wrap the entire call in a try-catch block to catch any Restclient exception, which may occur during communication or while mapping the response. If such an exception is caught, we throw another runtime exception, including the error details. This layered approach to error handling ensures that we can more easily debug and maintain our application. Now let's see how we can implement a user creation method using the REST template. The createUser method takes a user object as a parameter and utilizes the post4object method to send a post request to the remote API. In this call, the base URL along with the new user object is sent, and the API is expected to return the created user details, which are automatically mapped back to our user model. Next, it's essential to acknowledge that server communication can often encounter issues. Therefore, let's enhance the error handling by wrapping the post4object call in a try-catch block. This improvement allows us to catch any Restclient exception that may arise during the API interaction. If an exception occurs, we throw a new runtime exception with a descriptive message, ensuring that developers can trace and understand the issue while maintaining a smooth user experience. This addition not only safeguards our application, but also provides valuable feedback for troubleshooting when user creation fails due to various reasons like invalid data or server errors. Now let's take a look at how we can implement custom headers in our API requests using the REST template. In our createUser method, we begin by creating an instance of HTTP headers, allowing us to define the headers needed for our requests. Here, we set the authorization header, which typically contains a bearer token for authentication, and we also specify the content type as application/JSON to indicate the format of our data. Next, we encapsulate both the user data and the defined headers within an HTTP entity object. This is crucial as it combines the body of our post request, the new user we want to create, with the necessary headers. By doing this, we maintain compliance with the API's requirements for authentication and data handling. Finally, we use REST template post4object to send our request to the specified base URL. This line not only executes the API call, but also maps the response back into our user model. In case of any issues during this process, we catch Restclient exception and throw a runtime exception with a helpful message. This approach ensures that we've established both functionality and error management in our API interactions. Now let's implement the updateUser method to allow for updating user information. In this method, we construct a URL that points to the specific user we want to update, appending the user ID to the base URL. This ensures that we are targeting the correct resource in our API call. Next, we utilize the REST template put method to send the updated user data to the designated endpoint. By passing in the URL and the updated user object, we initiate the update operation, effectively replacing the existing user data with the new information provided. It's important to note that, similar to our previous methods, we can enhance this operation with error handling to catch any potential issues that might arise during the update process. This approach allows developers to ensure that they receive clear feedback if something goes wrong, which can help facilitate troubleshooting and improve the overall user experience in managing user data. Now let's take a look at how to delete a user using the delete method. We define a deleteUser method that accepts a user ID as a parameter. Inside this method, we construct the appropriate URL by appending the user ID to a predefined base URL, which points to our user API endpoint. This creates a direct link to the specific user we want to remove. Next, we utilize the REST template delete method, passing in the constructed URL. This straightforward approach sends a delete request to the external API, effectively removing the user from the system. The method emphasizes simplicity, allowing developers to handle user deletions without unnecessary complications. While this implementation is effective, it's essential to consider adding error handling to this operation. By introducing proper exception management, users can be notified if the deletion fails, which mirrors the error handling strategy used in our earlier methods. This small addition enhances the robustness of the application, ensuring that developers can maintain user experience even in the face of errors during API interactions. As we explore these various capabilities of the Restclient in Spring Boot, remember that how you structure your code and manage your API interactions can significantly impact the maintainability and robustness of your application. It's always good practice to centralize your API communications through dedicated service classes, ensuring clean separation of concerns in your application architecture. With the Restclient component, the interaction with REST-TFL APIs becomes far more manageable. It provides a wide array of functionalities, including error handling, custom headers, and interaction support for all CRUD operations, allowing developers to maintain a clear focus on business logic rather than the intricacies of HTTP. In this lesson, we covered the basics of the Restclient component by implementing a simple user service, managing interactions like creating, retrieving, updating, and deleting user information, while dealing with common pitfalls like errors and custom headers. By leveraging these tools and practices, you'll be able to enhance your application's API communication capabilities, resulting in a more reliable and efficient integration with external services. So as you forge ahead with your Spring Boot journey, keep these newly learned concepts in your toolbox and watch as your API interactions transform into a breeze. Happy coding! In today's lesson, we will delve deeper into the world of testing by focusing on the crucial concept of mocking dependencies. The ability to mock a remote server is essential, especially when testing our applications that rely on external systems or services. Mocking allows us to simulate interactions with these external dependencies, making our tests more reliable and efficient. So far, we have learned about enhancing API communication with the Restclient component in Spring Framework 6.1. We covered the importance of organizing code for REST-TFL API interactions, implementing a user service, and handling various operations like creating, retrieving, updating, and deleting user information. Additionally, we discussed effective error management and the inclusion of custom headers in API requests. This foundational knowledge equips us to create more robust applications with seamless API integrations. Now, we will cover how to effectively mock dependencies for testing purposes. Now let's implement the Mockito dependency in our project. To get started, you need to add the Mockito library to your POM XML file. This dependency is essential as it provides the necessary tools to create mock objects for your tests. The dependency tag includes important details like the groupid, artifacted, and version of Mockito, specifying that this dependency should be scoped for testing. By declaring it with the scope set to test, you ensure that Mockito is included only during the testing phase, which helps keep your production environment clean and efficient. Once you have this dependency in place, you can begin to utilize Mockito's powerful features for mocking your services. This foundational setup allows you to simulate interactions with the external user API, giving you control over the responses you receive during testing. By leveraging Mockito, you're enabling a focused environment for your tests, free from the unpredictability of real network calls, thus ensuring your tests are more stable and reliable. This is a crucial step in enhancing the robustness of your application testing process. Now let's implement the testing code for our user controller. In this setup, we leverage JUnit and Mockito to create a mock environment for testing. Initially, we import the necessary JUnit and Mockito classes to enable the testing framework and facilitate the creation of mock objects. Next, we declare a mock instance of user service using the @mock annotation, which allows us to simulate the behavior of user service without relying on the actual implementation. Then we use the @inject_mocks annotation on user controller, instructing Mockito to inject our mock user service into the controller during testing. This configuration sets us up to test user controller in isolation from the actual service layer. Within the setup method, we initialize the mocks, ensuring they are ready for use in our test scenarios. Moving to our test case, test getUserById, we define a mock user object and instruct Mockito on how to behave when the mocked method is called, specifically returning our mock user when user service getUserById1L is invoked. This approach allows us to verify the interaction with the service and assert the properties of the returned user to confirm our controller's logic works properly. Now let's see how we can implement a method in our user service to retrieve user data by their ID. The method getUserById utilizes a REST template to make a call to a remote API, fetching user details based on the provided user ID. This is crucial for our application, as it facilitates communication with external services to obtain user-specific information. Next, we will write the getUserById method in the user controller class, which maps to the HTTP GET request at the endpoint /users/ID. Inside this method, we invoke the user service to get the user and then check if the returned user object is null. If the user is found, we send a successful response with the user details. If not, we return a 404 not found status. This effective handling of both successful and unsuccessful requests contributes to a more resilient API. Now let's implement a test for the case when a user is not found. In this test method, we mock the behavior of the user service to return null when a specific user ID is requested. Finally, we assert that the controller correctly responds with a not found status if the user does not exist, showcasing our commitment to handling errors gracefully in our application. Next, we'll implement exception handling in our user service and user controller to ensure the application can gracefully manage scenarios where exceptions may occur during API calls. In the user service class, we encapsulate the API call within a try-catch block. If the REST template getForObject method throws a Restclient exception, we catch it and throw a runtime exception with a descriptive message. This way, we indicate that fetching user data from the remote API has failed, which helps developers understand the problem when troubleshooting. Now let's take a look at how this is reflected in the user controller. Here, we also wrap the call to getUserById inside a try-catch block. If a runtime exception arises due to an error in the service layer, the controller handles it by returning a response with an HTTP status, internal server error. This response structure allows the client to understand that something went wrong while attempting to retrieve the requested user. Next, we will test this exception handling behavior by simulating a failure scenario with Mockito, ensuring that our controller responds correctly under these circumstances. By doing so, we confirm that our application can effectively handle unexpected situations without crashing. With these examples, you can see the power of mocking dependencies with Mockito in your Spring Boot applications. It allows you to create isolated unit tests that do not rely on external services, making your test suite faster and more reliable. When it comes to writing effective unit tests, always strive to cover various scenarios, including successful service interactions, not found conditions, and exceptional use cases. This will ensure you have a robust setup capable of handling real-world situations. Before we wrap up, let me emphasize that mocking is not just a technique to fake functionality. It allows for cleaner tests and helps identify issues in your logic without involving the external components that could lead to flaky tests. Now that we've covered how to mock dependencies for testing considerably, think of the power you have with this knowledge. You can build more robust applications that withstand the test of time and variances in external APIs. In our journey through Spring Boot and its ecosystem, remember that tests are just as essential as the application code itself. They ensure your application behaves as expected and protects against regressions when you make changes. Always evolve your tests alongside the application, ensuring that as features grow, your testing suite grows too and continues to provide reliable feedback. Happy coding and mocking. In today's lesson, we will focus on enhancing error handling in REST-TFL APIs using Spring Boot, focusing heavily on creating unit tests to ensure our APIs handle various errors gracefully. This is a crucial aspect of building robust applications, as it ensures that your API can communicate effectively with clients even when things go wrong. So far, we learned about the importance of mocking dependencies in testing to improve reliability and efficiency. We explored how to use Mockito in conjunction with JUnit to create mock objects and simulate interactions with external services, particularly focusing on a user service that interacts with an external API. Additionally, we covered various scenarios in our tests, including successful responses, handling not found conditions, and managing exceptions. This foundational knowledge equips us to create robust applications while ensuring our tests remain reliable and effective. Now we will talk about enhancing error handling in our REST-TFL APIs. The displayed figure titled Error Handling Scenarios in REST-TFL APIs is a vertical bar chart showing the relative frequency in percentage of 5 outcome categories: successful response 65%, resource not found 10%, bad request 15%, internal server error 5%, and validation error 5%. Each category is drawn as a distinct colored bar: green for successful response, red for resource not found, blue for bad request, amber for internal server error, and pink for validation error, and the y-axis is scaled from 0 to 70 with grid lines at 10% intervals to emphasize the magnitude differences. Error bars are shown for each category: plus or minus 5% for successful response, plus or minus 3% for resource not found, plus or minus 4% for bad request, plus or minus 2% for internal server error, and plus or minus 1% for validation error, indicating variability or uncertainty around those frequencies. From the chart, we can conclude that the majority of API interactions are successful, approximately 2/3 at 65%, while client-related issues collectively represent a significant minority, resource not found 10%, bad request 15%, and validation error 5% combined to about 30% of outcomes, with bad request being the largest single client error after not found. Server-side failures, internal server error, are relatively rare at about 5% but still present. The relatively larger error bars for successful response and bad request imply greater variability in those outcomes, suggesting tests should especially exercise success paths and client error conditions to capture that spread. Overall, the visualization reinforces prioritizing robust client validation and clear 404 handling while keeping attention on preventing and catching the less frequent but impactful server errors. Now let's see how we can define a custom exception to be used in our Restful API. We create a class named ResourceNotFoundException that extends runtime exception. By doing this, we can easily throw this exception without needing to declare it in method signatures. It takes a string message as a parameter, which is passed to the superclass constructor. This message will provide context about why the resource was not found, making it easier for the consumer of our API to understand the issue. Next, we want to implement a global exception handler using the @controllerAdvice annotation, which allows us to intercept exceptions thrown anywhere in our application. In our handler class, we define a method that listens specifically for ResourceNotFoundException. When this exception occurs, we respond with an HTTP 404 status and the error message, ensuring that our API delivers meaningful feedback whenever requested resource is unavailable. This separation of error handling logic enhances the maintainability of our controller code and improves the overall robustness of our application. Now let's implement a global exception handler using @controllerAdvice in our Spring Boot application. This handler will allow us to intercept exceptions, particularly the resource not found exception, and return a structured response to the client. We start by creating a class named Global Exception Handler, annotated with @controllerAdvice, which makes it globally accessible across all controllers in the application. Inside this class, we define a method that listens for the resource not found exception. This method is annotated with @exceptionHandler, indicating that it will handle instances of this specific exception. When a resource not found exception is thrown, our handler will respond with a 404 not found status code and include the exception message in the response body. This modular approach not only centralizes our error handling, but also keeps the controller code streamlined and focused on business logic rather than error management. By utilizing this pattern, we can ensure that our API behaves predictably in error scenarios, providing meaningful feedback to clients while adhering to Restful principles. This is a critical step in building resilient and user-friendly APIs. Now let's take a look at the implementation of our user controller, which is responsible for handling user-related HTTP requests. This controller is annotated with @RestController and mapped to the /API/users endpoint, allowing it to manage user resources effectively through various HTTP methods. Next, we will define a method called getUserById, which fetches a user by their unique identifier. The method accepts a long type parameter that represents the user's ID. Within this method, we utilize our user service to find the user based on the provided ID. The service's findById method returns an optional user, and if the user is not found, we throw our custom ResourceNotFoundException. This exception is designed to explicitly signal that the resource could not be located, making error handling more precise and user-friendly. With this structure, we ensure that when a user tries to access a non-existent ID, they will receive a clear, informative response, enhancing the overall user experience and maintaining Restful practices. Now let's see how we can implement unit testing for our user controller. This test leverages the Mock MVC framework to simulate HTTP requests to our user endpoint, which is vital for testing our Restful API's behavior without needing to deploy the application. In the test method test_getUserByIdNotFound, we begin by defining a user ID to test, specifically choosing an ID that doesn't correspond to any existing user to trigger a not found scenario. Next, we utilize Mockito to set up our user service mock. By calling when on the mocked user service with the specified user ID, we instruct it to return an empty optional, which simulates the condition where the user is not found in the database. Then we proceed to perform a GET request using mock MVC, perform, targeting the specific user endpoint. We specify the content type as JSON in the request and check the response with various assertions. We expect the response status to be not found 404 and also verify that the response body contains the exact error message indicating the user was not found, providing useful feedback for the client. This structured approach ensures our API correctly handles not found scenarios, reinforcing our error handling strategy. Now let's implement a simple user model to handle validation constraints in our API. This model includes two fields, username and email. To ensure the integrity of the data received, we use validation annotations. The @not_blank annotation on the username field ensures that this value cannot be empty, providing a clear message if the constraint is violated. Similarly, the @email annotation on the email field checks that the provided email address adheres to a proper format, helping to prevent issues stemming from incorrect email submissions. Next, we need to incorporate this model into our controller. When we define the createUser method in the controller, we will use the @valid annotation on the user parameter. This ensures that Spring will automatically validate the incoming data against the constraints we've defined. If any validation fails, a method argument not valid exception will be thrown, enabling us to handle these errors gracefully later in our global exception handler. This design enhances the robustness of our ResTful API by ensuring that only valid data is processed, thus preventing potential errors further down the line. Now let's see how we can enhance our controller to handle validation effectively. We begin by modifying the createUser method to include the @valid annotation, which triggers validation checks on the incoming user data based on constraints defined in the user class. If a client submits invalid data, Spring will automatically throw a method argument not valid exception. To appropriately handle such validation errors, we extend our global exception handler. We implement a new method that captures method argument not valid exception and processes the validation errors. This method gathers all validation issues into a list format, making it easier for the client to understand what went wrong. The method then returns this list within a 400 bad request response, clearly indicating the errors for each invalid field. Through these enhancements, our API not only provides robust data validation, but also communicates precisely which aspects of the client's input failed, improving the overall client experience. This process ensures that users receive informative feedback, thereby facilitating smoother interactions with our API. Now let's implement the following unit test for validating the user creation process when invalid data is submitted. This test simulates a POST request to the API with a JSON payload containing an empty username and an improperly formatted email address. We are using mock MVC to perform this request, which allows us to test our API endpoints in a lightweight manner. Next, we assert that the response status returned from the API is a bad request 400, as the validation rules we set up in our user model should trigger this response when constraints are violated. Specifically, we expect the API to return error messages that correspond to the validation failures, such as username must not be empty for the username field and email should be valid for the email field. By checking these error messages, we ensure that the API is not only enforcing the validation rules correctly, but also providing meaningful feedback to the client about what went wrong. This is crucial for enhancing user experience and debugging during development. Through this test, we reaffirm that the API's error handling around data validation is functioning as intended. Next, we will add a method to our global exception handler class. This method will serve as a generic error handler to capture all unhandled exceptions in our application. By using the @exception_handler annotation with exception class, we ensure that this method will intercept any unexpected errors that occur during the execution of our API. When an unhandled exception is caught, the method responds with a standard HTTP status code of 500 to signify an internal server error. It returns a response entity containing a message with the error details, which helps in understanding what went wrong. This approach creates a unified error response structure for clients, making debugging easier and ensuring a consistent experience across different error scenarios. Now let's implement this by adding the method to our global exception handler. By doing so, we enhance our error handling strategy, which is crucial for building resilient REST-TFL APIs, allowing us to manage server-side issues gracefully while maintaining clear communication with clients. Now let's take a look at how we can implement a test for our global exception handler. The test simulates a scenario where an unexpected error occurs, specifically when a request is made for a user ID that is unlikely to exist, such as the ID 9999. This ID is assumed to trigger an exception in the application. Using Mock MVC, we perform a GET request to the API endpoint for users with this invalid ID. The intention behind this test is to ensure that our global exception handler accurately captures this unhandled situation and responds correctly. We expect the response to return a status code of 500, indicating an internal server error. Additionally, we want to verify that the response body contains an appropriate error message stating that an unexpected error has occurred. This test not only confirms that our global error handling is functioning as intended, but also reinforces the importance of having robust mechanisms in place to deal with exceptional scenarios, ensuring that clients receive meaningful feedback even when errors arise. By writing comprehensive tests like this, we can improve the resilience of our API against unforeseen issues. So far, we've covered a lot, including custom exceptions, validation errors, and handling unhandled exceptions. We've built a robust framework to ensure our REST-TFL API can gracefully handle various error scenarios while providing meaningful feedback to the client. As we wrap up, remember that well-implemented error handling not only improves the developer experience by providing clear feedback during development, but it can also greatly enhance the user experience by delivering informative error messages in the event of issues. Next time, we will dive deeper into logging and monitoring strategies for maintaining our REST-TFL APIs in production environments. Thank you for following along, and I hope you're as excited as I am to take these concepts into practical application. In this lesson, we'll dive into implementing testing strategies for REST-TFL APIs using Spring Boot and WireMock to simulate a remote football service. This will help us ensure that our tests run smoothly without relying on the actual external service. So far, we learned about enhancing error handling in REST-TFL APIs using Spring Boot, focusing on custom exceptions and validation mechanisms. We explored how to implement a global exception handler with @controller advice to provide meaningful responses for both resource not found and validation errors. Furthermore, we discussed unit testing for our error handling logic to ensure reliability and robustness in our API. Now we will cover how to effectively mock services using WireMock to test our API endpoints without needing to always access the real football service. Now let's see how we can implement our WireMock dependency in the project. By including the specified XML snippet in the POM XML file, we allow our Maven build tool to recognize WireMock as a test dependency. The group ID, artifact ID, and version fields are necessary for Maven to retrieve the correct library version from the central repository. Setting the scope to test indicates that WireMock will only be used during the testing phase and won't be included in the final production build. This is a crucial step for enabling our tests to simulate external HTTP calls without actually hitting a real server, thus ensuring that our tests remain fast and reliable. Next, we'll set up a simple test class to mock the football service. By initializing a WireMock rule, we start a WireMock server that listens on a designated port, in this case, port 8080. This allows us to intercept HTTP requests intended for the mocked football service. Inside our test method, we define a stub for a GET request to the football matches endpoint. When our application tries to access this endpoint, WireMock responds with a predefined JSON object representing a football match. This technique provides an isolated testing environment, ensuring that our application behaves correctly while interfacing with the mocked service. Now let's see how we can implement a simple test class to effectively mock our football service using WireMock. We start by importing the necessary classes, including WireMock rule for mocking and various Spring testing components. The @Spring Boot test and @auto-configure mock MVC annotations set up our test environment, enabling us to use mock MVC for simulating HTTP requests. Next, we define our test class and initialize a wire mock rule that listens on port 8080. This acts as our mocked service during tests. In the test-get-football-data method, we employ stub4 to define how the mock responds to incoming requests. Specifically, when a GET request is made to the football matches endpoint, wiremock sends back a predefined JSON response representing a football match. We then utilize mock MVC, performed to send a GET request to our application's API endpoint. This allows us to check how our application interacts with the mocked football service. Finally, we assert that the response status is 200 OK, ensuring that our application correctly processes the request and interacts as expected with the mock setup. This setup leads to reliable tests without external dependencies, guaranteeing a controlled testing environment. Now let's implement the following enhancement to our test-get-football-data method. We begin by setting up a stub for the wiremock server, which simulates the response from the mocked football service. Through the stub4 method, we specify that a GET request to the endpoint football matches will return a predefined JSON response containing an array of football match data complete with IDs and team names. Next, we perform a request to our application's endpoint /API/football/matches using the mock MVC perform method. After sending the request, we assert that the HTTP status returned is 200 OK with an expect status is OK, indicating that our application successfully processed the request. However, for a more comprehensive verification, we also parse the content of the response. We retrieve the JSON response string and utilize assertions to check for the presence of expected data fields such as the match ID, Team A, and Team B. By doing this, we validate that the data returned from the mocked service aligns with what we expect. This approach not only tests the status code, but also ensures our application correctly interprets the structure and values of the response, enhancing the reliability of our API integration. The figure titled Football Team Performance Statistics presents 3 metrics for 5 teams: Team A, Team B, Team C, Team D, Team E. Goals scored are shown as green bars on the primary y-axis with values 45, 30, 25, 18, 10 respectively. Yellow cards are shown as red bars on the secondary y-axis with values 12, 15, 8, 25. Red cards are plotted as blue circular scatter markers with counts 1, 0, 2, 4, 1. From the data visible, Team A leads in offensive output with 45 goals while maintaining a moderate number of yellow cards, 12, and a single red card, indicating high scoring efficiency with relatively controlled dismissals. Team B is the second highest scorer, 30 goals, but accumulates more yellow cards, 15, and no red cards, suggesting frequent cautions without send-offs. Team C has mid-level scoring, 25 goals with low yellow cards, 8, and 2 red cards, showing fewer cautions but some send-offs. Team D exhibits the worst disciplinary record, highest yellow cards, 20, and the highest red cards, 4, while scoring only 18 goals, highlighting a pattern where heavy disciplinary issues coincide with lower scoring. Team E records the fewest goals, 10, and the fewest yellow cards, 5, with 1 red card, indicating low offensive output and low cautioning. The color-coded legend and dual y-axes make clear the relative magnitudes. Goals dominate the primary axis scale, while yellow cards use the secondary scale, and red cards scatter emphasize incidents per team. Overall, the plot shows that higher goal totals do not necessarily correspond to higher disciplinary counts, e.g., Team A versus Team D, and it identifies Team A as the most productive scorer and Team D as the most discipline-challenged team among those displayed. Now let's see how we can implement a teardown method to reset our wiremock server after each test. We use the add-after annotation to designate a method that will run following each test case, ensuring that the wiremock server resets all previous stub mappings. This practice is crucial for maintaining test isolation, which prevents errors in one test from affecting the results of subsequent tests. Without this step, stale stubs could lead to unpredictable behaviors and unreliable test outcomes. Next, we will write a test to simulate an internal server error from our mocked football service. By using the @test annotation, we define a method that will perform an HTTP GET request to our application's endpoint. Inside the method, we configure wiremock to respond with a 500 internal server error status when a request is made to the football match's URL. This allows us to check if our application appropriately handles such unexpected responses. Finally, we validate the outcome by asserting that the status of the response is indeed 500, confirming that our error handling logic within the API is functional. This approach provides vital coverage for scenarios where external services may tip into failure. Now let's implement the @dirties context annotation in our football service test class. This annotation is crucial for maintaining the integrity of our tests by ensuring that the Spring application context is reloaded between test executions. By applying @dirties context at the class level or on specific test methods, we instruct the Spring testing framework to destroy the existing application context and recreate it afterward. This approach helps us avoid potential side effects from previous tests that might alter the state of the context, especially when using cached contexts. Although this may increase test startup time, the benefits of having a clean slate are invaluable in more complex testing scenarios where unintentional interactions could arise between tests. So now let's take a closer look at how we can effectively use this annotation in our tests to enhance reliability. By doing so, we can ensure that each test runs in its own isolated environment, allowing us to confidently test our application's functionality against a freshly instantiated context. This practice is invaluable when working with stateful beans or configuration changes that could impact subsequent tests. Now let's implement the following test to validate interactions with the actual football service endpoint. The code defines a JUnit test annotated with @test, which is crucial for identifying the method as a test case within the Spring framework. In this test, we utilize mock MVC, performed to simulate a GET request to our API endpoint /API/football/matches. By invoking an expect status is OK, we assert that a successful call to this endpoint should return a status of 200 OK. This simple yet essential test allows us to verify that our application can communicate correctly with the real football service. Although this method does not involve mocking, it serves to ensure that our application behaves as expected in a live environment, checking both connectivity and functional integrity with external dependencies. This dual approach, mocking with wiremock for quick and isolated tests, alongside this integration test, ensures that our application is both robust and reliable. So, as we continue to build out our testing strategy, it's essential to balance both mocked and real service integrations for comprehensive coverage. To wrap up, leveraging wiremock in your Spring Boot RESTful API testing strategy allows for efficient and reliable tests without the dependencies on external services. Mocking responses simplifies the testing process significantly, allowing you to focus on validating your application logic. By incorporating this alongside thorough integration testing, you ensure that your application is robust, maintainable, and ready to handle various scenarios in production. As you continue to develop your skills with Spring Boot, remember that every feature you implement should be backed by solid tests. It's not just about developing new features quickly, it's about ensuring they work correctly and reliably over time. Happy coding and good luck on your journey to mastering Spring Boot. Today, we will explore how to utilize the new Restclient component introduced in Spring Framework 6.1 and available in Spring Boot since version 3.2 for simplified API consumption. This will allow us to make HTTP requests more easily and effectively in our Spring Boot applications. So far, we learned about implementing testing strategies for RESTful APIs using Spring Boot and wiremock, focusing on enhancing error handling and creating isolated tests with mocked responses. We discussed how to set up wiremock and write tests to validate our API endpoints while simulating external dependencies. Additionally, we emphasized best practices such as resetting the wiremock server between tests and incorporating integration tests to validate real service interactions. Overall, the importance of solid testing as an essential part of the development process was highlighted. Now, we will cover how to leverage the Restclient for efficient API interactions in our applications. Now let's implement the necessary dependency to use the Restclient in our Spring Boot application. In your POM XML file, include the Spring Boot Starter for Web, which provides essential features for web development, including the Restclient. This dependency simplifies the integration of web capabilities and allows us to leverage the powerful features of the Spring ecosystem, thus reducing setup time and boilerplate code required for HTTP interactions. Next, we will create a configuration class to customize our Restclient settings. Here, we define a Restclient config class annotated with @configuration, which signals to Spring that this class provides configuration details. Within this class, we will write a method that returns a web client builder. The web client builder allows for custom configurations of web client instances, making it reusable across various components in our application. By setting a base URL and a default header to indicate that our requests will send and receive JSON data, we significantly streamline the process of making HTTP requests throughout our application. This setup enhances maintainability and reduces redundant configurations on a per-request basis. Now let's explore how we can implement a service class that leverages our configured web client to retrieve user details from the API. We begin by defining a user service class and annotating it with @service, indicating to Spring that this class will be a service component. Next, we inject the web client builder into our service, enabling us to create instances of web client tailored to our needs. In the getUserById method, we accept a userid parameter, which allows us to create a dynamic HTTP GET request targeted at retrieving user data by that ID. We formulate the request using the URI method, where we include the user ID as a path variable. Upon executing the request with retrieve, we expect the server's response to be wrapped in a mono user, representing the asynchronous nature of our operation. This means that while we wait for the API's response, our application can remain responsive, leveraging the capabilities of reactive programming. The ultimate goal here is to transparently handle user data retrieval while ensuring efficient resource utilization and error handling in the face of potential API failures. The displayed figure is a group bar chart titled API Consumption Scenarios that compares success rate % and error rate % across 5 API endpoints: get users, post users, GET orders, post orders, and delete users. Each category has 2 adjacent bars annotated with their exact percentages on top. Success bars are colored green and error bars red, with the y-axis scaled from 0 to 100 and a horizontal grid for reading values. Key patterns visible are: post orders shows the highest success rate at 90% and the lowest error at 5%, indicating it is the most reliable endpoint in this sample. Post users and get orders both have strong success rates 85% and 80%, respectively, with low error rates 10% each. GET users has a moderate success rate of 75% and a 15% error rate. Delete users exhibits the poorest performance with only 70% success and the highest error rate at 20%. From these values, we can conclude that post operations in this dataset outperform their GET counterparts, both post users versus GET users and post orders versus GET orders, and the delete users endpoint is a clear outlier that requires attention. Practically, this suggests prioritizing monitoring and remediation for delete users, adding retries or validation where appropriate, and investigating why get users lags behind comparable post endpoints despite similar responsibilities. Now let's implement the following user controller, which serves as the interface for client requests to access user information. In this controller, we use the @RestController annotation, indicating that this class handles web requests and automatically serializes responses to JSON. We inject the user service using Spring's @AutoWired annotation, ensuring our controller has access to the service methods for user retrieval. Next, we have the getUserById method, which maps to the HTTP GET request through the @getMapping annotation. This method accepts a user ID as a path variable, allowing clients to specify which user's data they wish to retrieve. Here we call the getUserById method on the user service, which returns a mono response entity user, representing a single asynchronous response. We handle the response elegantly by mapping the retrieved user to a response entity with an HTTP 200 status when a user is found. In cases where no user is found, we use default ifEmpty to return a 404 not found response. This implementation demonstrates a clean, reactive approach to API design, empowering developers to manage user data access effectively while ensuring proper HTTP response handling. Now let's implement error handling in our getUserById method within the user service. This enhanced version utilizes the onStatus method to specifically check for a 404 HTTP status when a user cannot be found. If this status is detected instead of proceeding normally, we return a mono that encapsulates an error, throwing a custom user not found exception with the message user not found. This approach directly ties error handling to the HTTP response status, making it clearer and more intuitive for further processing in the reactive chain. By incorporating this mechanism, we ensure that any logic that depends on the existence of a user can handle the absence gracefully down the line, rather than crashing or producing unexpected behavior. This also allows for easier debugging and error management, as the error context is more closely linked to the API's response. With this structure in place, our application becomes more robust against issues originating from external services, ensuring that users receive meaningful feedback if problems occur during their requests. Now let's see how we can implement extended error handling in our getUserById method using the Restclient. In this code snippet, we build upon the basic functionality by using the onStatus method to identify and handle various error responses from the API. We check if the status indicates an error through the statusError condition. If an error occurs, we retrieve the response body as a string to capture any specific error message returned by the API. This is crucial because it allows us to provide more informative error messages to the client and aids in debugging. By flattening the response into a mono error, we can propagate the error up the reactive chain, enabling better handling at higher levels of our application. This approach not only enhances user experience by delivering meaningful feedback, but also ensures that we can respond appropriately to different types of HTTP errors, such as 400 or 500 status codes. In summary, adding this error handling logic significantly enriches our API interaction, making our application more robust and user-friendly. Now let's take a look at how we can configure custom timeouts in our REST client. In this code, we define a web client builder bean within a Spring configuration class. Here, we utilize the web client builder method to create a base configuration for our API client, specifying the base URL and default headers for our requests. Next, we incorporate a Reactor client HTTP connector, which allows us to customize the HTTP client settings. By setting the connect timeout MILLIS to 5,000 milliseconds, we establish a limit on how long we will wait to establish a connection to the server. Additionally, the response timeout is specified, which indicates the maximum duration we are prepared to wait for a response from the API before considering the request to have failed. These timeout configurations are essential for ensuring that our application remains responsive, particularly when dealing with potentially slow or unresponsive APIs. If an API call exceeds these timeouts, it will fail gracefully, enabling our application to handle the situation without hanging indefinitely. This approach enhances the robustness of our application and is an important aspect of implementing effective API interactions. Finally, let's combine everything we've learned in a complete application demo. We have set up our REST client, built our service, created a controller, implemented error handling, and established timeout configurations. When you put this all together within a Spring Boot application context, you have a powerful tool for consuming REST-TFL APIs effectively. As a takeaway, utilizing REST client significantly reduces complexity in handling HTTP requests, making your code cleaner and more maintainable. Keep in mind to leverage reactive programming paradigms to ensure your applications remain responsive and performant. In conclusion, the shift towards utilizing Spring's REST client helps web developers focus more on application logic rather than getting bogged down by low-level HTTP details. So, as you explore this powerful tool, remember to implement sound error handling, timeout management, and maintain clean architecture in your services. Thank you for following along with this lesson. Dive in and start building your REST-TFL APIs more effectively with Spring Boot and the new REST client. Happy coding! Scalability is a critical aspect of API design that affects how well the API performs under varying load conditions. A well-designed API should gracefully handle an increasing number of requests without sacrificing performance or reliability. In our previous lessons, we explored the new REST client component in Spring Framework 6.1 that simplifies HTTP request handling, how to configure the REST client, create services for consuming REST APIs, and implement error handling and timeout settings. We also highlighted the importance of maintaining a clean architecture and utilizing reactive programming for responsiveness. Now we will dive deep into scalability considerations and how to effectively implement them in our API designs. The displayed figure titled Scalability Considerations for API Design presents a vertical bar chart comparing 5 scalability techniques by their hypothetical performance impact percentage. The x-axis lists the techniques in this order: vertical scaling green, horizontal scaling blue, caching amber, load balancing orange, and sharding indigo. Each bar is annotated with its numeric value at the top: vertical scaling 85%, horizontal scaling 90%, caching 75%, load balancing 80%, and sharding 70%. The y-axis ranges from 0 to 100, and the horizontal grid lines emphasize differences in impact. Key patterns visible in the figure are: horizontal scaling registers the highest single technique impact at 90%, closely followed by vertical scaling at 85%. Load balancing sits in the middle at 80%. Caching and sharding are lower at 75% and 70% respectively. From these values, we can conclude that while all 5 techniques contribute substantially, within a fairly tight 70–90% band, scaling strategies and load balancing show the largest individual effects on performance in this representation, and combining techniques, for example pairing caching with load balancing or horizontal scaling, is implied to be necessary to maximize overall system performance. First, let's define what scalability means in the context of API design. Scalability refers to the capability of an API to handle a growing amount of work or its potential to accommodate growth. It is generally classified into 2 types: vertical scaling and horizontal scaling. Vertical scaling involves upgrading the existing server hardware, like adding more CPU or RAM, allowing the system to handle more requests efficiently. On the other hand, horizontal scaling involves adding more machines or instances to handle the load, which can often be more cost-effective and flexible in cloud environments. For instance, if you're using a Spring Boot application, consider a simple REST API that may serve user profiles. The initial implementation may handle a small user base, but once your application grows, you may need to adjust to serve hundreds of thousands or millions of users. The challenge lies in designing the API to naturally scale to accommodate that growth. Now let's implement the following code to create a user profile retrieval endpoint using Spring Boot with caching enabled. We start by defining a user profile controller class and annotating it with @RestController, which designates this class as a res-tful controller that will handle incoming API requests. Next, we use the @request_mapping annotation to specify that all requests to this controller will be routed through the /API/users path. Within this controller, we have a private field, user profile service, which is automatically injected using @AutoWired. This service is responsible for handling the business logic of retrieving user profiles from the database. The key feature here is the @cacheable annotation applied to the getUserProfile method. This tells Spring to cache the result of this method based on the unique user ID provided as a path variable. When a client requests a user profile, if the data is already in the cache, it will be returned quickly without hitting the database, significantly improving response time and reducing server load for frequently accessed profiles. Thus, the implementation demonstrates an effective way to enhance performance by integrating caching within a res-tful API context. Now let's see how we can integrate Spring Cloud Load Balancer into our Spring Boot application by adding the necessary dependency in our POM XML. This dependency group ID org Spring Framework cloud/group ID artifact ID Spring Cloud Starter Load Balancer /artifact ID/dependency enables us to leverage Spring Cloud's capabilities for effectively distributing incoming traffic across multiple instances of our services. Next, we will configure the load balancer in our application properties file to optimize its performance. By setting the property Spring Cloud Load Balancer ribbon enabled equals false, we disable the default ribbon load balancer that comes with Spring Cloud, allowing our application to use the native Spring Cloud Load Balancer instead. This step is essential for ensuring that our application uses the most up-to-date load balancing features provided by Spring Cloud, leading to better distribution of requests among our service instances. With these configurations in place, our Spring Boot application is now set to efficiently handle scalable traffic, improving both responsiveness and redundancy across our service instances. This allows the system to manage loads adeptly, especially under high-demand conditions. Now let's see how we can implement database sharding to improve the scalability of our API. The code snippet defines a method called FindById, which retrieves a user profile based on a given user ID. The first step in this method is to determine the appropriate database shard for that user ID. This is accomplished by calling the helper method getShardNumber, which uses a simple modulo operation. Essentially, it takes the user ID, converts it to an integer, and divides it by the total number of shards. The result indicates which shard should handle the request, effectively distributing the load across multiple database instances. By ensuring that requests are directed to different shards, we minimize the risk of overloading a single database instance. This modular approach allows our application to handle a growing number of requests more efficiently. The next line in the findById method accesses the corresponding shard database using the computed shard number and retrieves the user profile through the findUserProfileById method. This structure not only enhances performance, but also lays the groundwork for a scalable database design that can adapt as user demand increases. Now let's implement the dependency for Spring Boot Actuator in our project. This is crucial for enabling production-ready features that provide insight into the application's performance and health. To include Actuator, you'll need to add a Maven dependency in your POM XML file, specifically the Spring Boot Starter Actuator. This dependency automatically configures all necessary actuator components and allows you to expose various management endpoints which you can use to monitor your application. Next, we will configure the application's properties to expose the actuator endpoints. By setting management endpoints web exposure include =*, we effectively configure our application to expose all available actuator endpoints. This includes endpoints that provide metrics about application performance, health checks, and other vital statistics. With these settings in place, you'll be able to make calls to endpoints such as actuator metrics to retrieve essential performance data. This information is instrumental in monitoring how your application behaves under load, helping you identify potential bottlenecks and optimize your system accordingly. To ensure that your API remains scalable, consider implementing the following best practices. 1. Statelessness ***. Design your APIs to be stateless. Keeping the server stateless allows it to handle requests without remembering session information, making it easier to scale horizontally. 2. API versioning ***. Plan for future growth by using API versioning. As you evolve your application, versioning helps ensure that clients can still access previous functionalities without breaking existing integrations. 3. Rate limiting ***. Protect your API from abuse by implementing rate limiting. This restricts the number of requests a client can make in a given timeframe, allowing you to manage traffic more effectively. 4. Asynchronous processing ***. For tasks that are resource-intensive, consider using asynchronous processing. Offloading these tasks into a messaging queue can help decouple the processing workload from your user-facing API endpoints. 5. Documentation. Keep your API well documented. Proper documentation helps clients understand how to use the API efficiently, reducing unnecessary load caused by misconfigured requests. Implementing these practices allows your API to scale elegantly, adapting to increasing loads without compromising on performance or usability. In conclusion, we have explored various dimensions of scalability in API design, focusing on caching, load balancing, sharding databases, monitoring, and best practices to maintain robust APIs. Understanding and incorporating these elements into your API design will set you on the path to creating scalable, maintainable, and performance-oriented applications in Spring Boot. Thank you for joining me in this lesson on scalability considerations for API design in Spring Boot. I hope you found the insights helpful and are excited to implement these techniques in your projects. Feel free to leave your questions or comments below, and I'll see you in the next video where we'll explore the world of API security. Ensuring the security of an API is paramount to protect sensitive data and prevent unauthorized access. In today's lesson, we will explore the essential security best practices for APIs, providing you with key strategies and techniques to safeguard your applications. So far, we learned about the critical aspect of scalability in API design, focusing on vertical and horizontal scaling, optimizing endpoint efficiency through caching, and the role of load balancing. We also discussed the importance of database sharding and monitoring performance metrics to maintain scalability. Best practices for scalable APIs include statelessness, API versioning, rate limiting, asynchronous processing, and proper documentation. Our journey through these concepts will help create robust and performant APIs in Spring Boot. Now we will cover how to secure these APIs and ensure that they are resilient against various threats. Next, we will write the necessary dependencies in our POM XML to enable JWT support in our Spring Boot application. This entails adding the JWT library, which is crucial for handling JSON web tokens. With this dependency in place, our application will be equipped to generate and validate JWTs efficiently. Now let's take a look at the utility class that manages our JWT operations. This class, annotated with @component, houses methods for token generation and validation. The generate token method creates a JWT based on the user's username. When a user logs in, we can easily call this method to issue a new token. The create token method constructs the JWT, specifying its claims, subject, issue date, and expiration time. It's important to note that the token will expire after a set duration, in this case, 10 hours. Next, we will examine the validation methods. The validate token method checks whether the token is still valid for the provided username and ensures it has not expired. Additionally, the extract username method facilitates retrieving the username from the token, while extract all claims enables fetching all claims embedded within it. Finally, we have is token expired, which straightforwardly checks if the token's expiration date has passed, ensuring robust security for our API. The displayed donut chart titled Importance of Security Best Practices for APIs breaks down 5 practices by importance. Authentication 95%, authorization 90%, HTTPS 88%, input validation 85%, and logging 80%. Authentication forms the largest slice at 95%, with authorization close behind at 90%, indicating that identity verification and access control are the top priorities when securing APIs. HTTPS 88% and input validation 85% occupy slightly smaller but still substantial portions, emphasizing the dual need to protect data in transit and to validate or sanitize incoming data to prevent injection and XSS-style attacks. Logging is shown at 80%, the smallest slice, but remains a significant element for detection and response. The relative sizes reveal that while all 5 practices are important, focusing first on robust authentication and authorization provides the greatest security coverage, with HTTPS and input validation as essential complementary layers and logging, enabling monitoring and incident analysis. This visual prioritization directly supports implementing strong JWT auth flows, role-based access controls, SSL configuration, input sanitization, and structured logging in your Spring Boot APIs. Now let's implement the following security configuration in our Spring Boot application to manage authorization effectively. We will use Spring Security's Web Security Configurer adapter to define how our API endpoints should be secured. First, we disable CSRF protection for simplicity, as we are using a stateless session to strengthen our API's security framework. Next, we specify our authorization rules by utilizing authorize requests. This allows us to clearly define which roles are permitted to access specific routes. For instance, only users with the role of admin will have access to any endpoints under /API/admin/**, ensuring that sensitive functionality is limited to authorized personnel only. Conversely, both users and admin roles can access the /API/users/** paths, enabling broader user interaction while safeguarding protected resources. Furthermore, the line any request, authenticated, ensures that any other requests reaching our API are authenticated, providing an additional layer of security. Finally, implementing a stateless session management policy enhances our API by ensuring that no session data is stored on the server, aligning with modern best practices for secure API design. This configuration sets the stage for a robust, secure application that can effectively manage user access based on defined roles. Next, we will write the following code to demonstrate how to mitigate potential XSS attacks by sanitizing user inputs. In our user controller, we define a post endpoint at /API/users that allows users to add new accounts. When a user sends a request with their username, we first pass that username to the sanitize method. This method employs a simple yet effective technique. It removes any angle brackets from the input string. This precaution is essential because angle brackets can be used to inject malicious scripts, leading to XSS vulnerabilities. After sanitizing the username, we set the cleaned username back to the user object. This example illustrates how to integrate input validation directly into your API logic, ensuring that potentially harmful data does not reach your database. Finally, the sanitized user object is returned, ready for further processing, such as saving it to the database. This approach not only protects your application from malicious input, but also reinforces the importance of input validation in any web application, maintaining a secure environment for user interactions. Now let's implement the CSRF protection feature in our Spring security configuration. The snippet begins with an override of the configure method from the Web Security Configurer adapter, which is central to customizing the HTTP security settings for our application. Within this method, we first call HTTP to begin the configuration chain. Here we enable CSRF protection by utilizing the CSRF method alongside a CSRF token repository. In this case, we use cookie CSRF token repository with HTTP only false, which allows the server to store the CSRF token within a cookie that is accessible via JavaScript. This is crucial for state-changing requests, as it generates a unique token that is provided to the client and must be sent back with any modifying actions like post, PUT, or delete. By doing this, we ensure that even if an attacker attempts to forge a request on behalf of an authenticated user, the server will reject it due to the absence or invalidity of the CSRF token. Finally, we chain authorize requests to stipulate that all requests need to be authenticated, thereby reinforcing the API's security against unauthorized access. With this setup, we've effectively integrated CSRF protection in our Spring Boot application. Now let's implement the following configuration in our application properties file to enable HTTPS for our Spring Boot application. We start by setting the server port to 8443, which indicates that our application will run on this secured port instead of the default HTTP port. Next, we specify the server SSL key store, pointing to the location of your key store file, which contains the SSL certificate required for HTTPS. In this example, we're using class path key store P12, which means the key store file should be present in the class path of your application. To ensure the key store can be accessed, we provide the server SSL key store password, where you should enter the password that protects your key store. Lastly, we define the server SSL key store type as PKCS12, indicating the format of the key store file. By making these configurations, we can establish a secure connection that encrypts the data transmitted between the client and server, safeguarding it against eavesdropping and man-in-the-middle attacks, while also building trust with our users as they interact with the API. Now let's implement logging in our Spring Boot application to enhance its API security. First, we import the necessary classes from the SLF4J logging framework and Spring's web annotations. We create a new class called API Controller, annotated with @RestController, which indicates that this class will handle web requests. Within this controller, we define a logger instance using Logger Factory, creating a static logger specific to API Controller. This logger will help us log messages easily throughout our code. Next, we set up a method called getData, which is mapped to the /API/data endpoint using the getMapping annotation. Whenever this endpoint is accessed, the method executes, and we log an informational message stating that the data endpoint was hit. This logging is crucial as it allows us to track API interactions effectively. By monitoring these logs, we can detect anomalous patterns in usage, thereby identifying potential threats or issues before they escalate. Overall, structured logging like this plays a vital role in maintaining the security and health of your API. To wrap up, let's summarize what we covered in this lesson about security best practices for APIs. We started with authentication mechanisms, particularly focusing on JWT and OAuth 2 for securing access. Next, we looked into authorization strategies, using Spring Security to define user roles and restrict access. We explored measures against common attacks like XSS and CSRF, and how to protect data in transit by enforcing HTTPS. Finally, we discussed the significance of logging and monitoring in tracking potential threats and vulnerabilities. Implementing these security practices will ensure that your Spring Boot APIs are resilient against a wide range of threats, providing a secure environment for your users' data. I hope you find these techniques valuable in your development journey, and I encourage you to keep security at the forefront of your API designs. As you continue building your applications, remember that a well-architected API considers not only performance and scalability, but also security as a top priority. Thank you for joining me in this lesson. Be sure to apply these principles in your projects, and let's keep exploring the exciting world of Spring Boot in our next session. Now let's take a look at how we implement our user entity and a corresponding user DTO to enhance performance. The user entity maps to a database table and contains various fields like ID, username, email, and password, the latter being sensitive data that we want to protect. This class is annotated with @entity, indicating to Spring that it's a JPA entity. Each field has appropriate annotations, like @id for the identifier and @generated_value to manage the ID's generation strategy. Next, we create a user DTO, or data transfer object, which simplifies our API's response by containing only the id and username. This minimalistic approach ensures we only transmit necessary data, thereby reducing the payload size when the API responds. Now, let's implement the repository that provides access to these entities. By extending JPA repository, we gain many built-in features. Additionally, we define a custom query using @query to fetch only the specific fields we need for the user DTO, which optimizes the data retrieval process while minimizing the load on memory and network resources. This strategy is crucial for enhancing response times and overall API performance. Now let's see how we can implement caching in our Spring Boot application to improve API performance. We begin by creating a service class called userService. In this class, we define a method getUserById, which takes a user's ID as a parameter. By using the @cacheable annotation, we instruct Spring to cache the results of this method. This means that the first call to this method will fetch the user details from the database, while any subsequent calls with the same ID will return the cached result, bypassing the database query altogether. The cache name users serves as an identifier for this cache, enabling efficient data retrieval. Next, to enable caching functionality across our application, we need to annotate our main application class with @enableCaching. This tells Spring to process caching annotations and to manage the cache lifecycle. By doing this, we leverage the benefits of caching to dramatically reduce database load and enhance response times for operations that frequently access user details. This technique is particularly valuable in scenarios with read-heavy workloads, where user information does not change often. The displayed figure is a horizontal bar chart titled Performance Optimization Techniques for APIs, with the x-axis labeled Performance Gain % and the y-axis listing 5 optimization techniques. Each bar is annotated with its exact percentage at the bar's end, and the x-axis scale runs from 0 to 40%, with dashed grid lines to emphasize relative magnitudes. The specific values shown are caching at 30%, asynchronous processing at 25%, database query management at 20%, pagination at 15%, and connection pooling at 10%. Visually, the longest bar corresponds to caching 30%, followed by asynchronous processing 25% and database query management 20%, indicating these three techniques contribute the largest single technique improvements. Pagination and connection pooling show smaller, but still meaningful, gains 15% and 10% respectively. From this distribution, we can conclude that prioritizing caching and asynchronous processing delivers the greatest immediate performance returns, while database query refinements are also important. Pagination and connection pooling present lower individual gains but remain valuable parts of a layered optimization strategy. The displayed values and ordering make it clear which techniques to evaluate and implement first when seeking the most impactful improvements. Now let's implement asynchronous processing in our Spring Boot application to enhance API performance. We begin by creating an email service class, which is annotated with @service to indicate that it's a Spring Service component. Within this class, we define a method called sendWelcomeEmail, and we use the @async annotation on this method. This annotation allows the method to execute in a separate thread, meaning that long-running tasks such as sending emails won't block the main thread. By employing this method, our API can quickly respond to user requests without delay. When the sendWelcomeEmail method is called, it initiates the email sending logic, and users receive their HTTP responses immediately, improving their experience significantly. Next, we need a configuration class to enable asynchronous processing. We annotate this class with @configuration and @enableAsync. This setup tells Spring Boot to look for @async methods in our application, allowing us to utilize asynchronous capabilities effectively. By implementing these components, we enhance the responsiveness of our API while offloading time-consuming operations to separate threads, a crucial aspect of optimizing performance in our application. Now let's implement pagination in our Spring Boot application to enhance API performance when handling large datasets. We start by modifying our repository interface to extend paging and sorting repository, which provides built-in methods for pagination and sorting functionalities. This setup allows us to manage data in smaller, manageable chunks rather than fetching all records at once, thereby reducing memory usage and improving response times. Next, in our service layer, we will create a method called getUsers, which accepts a pageable parameter. This method utilizes the user repository to fetch users paginated. The findAll method returns a page containing userdto objects, where each object maps the user's ID and username, effectively minimizing the payload sent to clients. Finally, let's configure our controller to define a specific endpoint for this paginated data retrieval. We'll accept page and size as request parameters, allowing clients to specify which set of records they want. By using page request of page size, we pass these parameters to our service method, facilitating a smooth and efficient way to retrieve user data while improving the overall application performance. Now let's implement connection pooling to enhance our API's performance when interacting with the database. First, we need to add Hikari CP as a dependency in our POM XML, which is a popular choice for connection pooling in Spring Boot applications. This dependency allows us to manage a pool of connections efficiently, reducing the overhead associated with creating new connections for every database request. Next, we will configure the connection pool settings in the application properties file. We can define the maximum pool size, which determines the maximum number of connections that can be active at any one time, and the minimum idle connections that should be maintained. Setting the idle timeout controls how long connections can remain idle before being reclaimed. Additionally, we configure the connection timeout to specify how long the application should wait for a connection from the pool before timing out. By establishing these configurations, we ensure that our application can efficiently manage database connections, allowing it to handle more requests simultaneously while minimizing latency and resource consumption. This results in improved overall responsiveness of the API, crucial for delivering a seamless user experience. Now let's see how we can optimize our API responses by implementing a data transfer object DTO using the userdto class. In this implementation, we leverage the @JSON ignore properties annotation from the Jackson library to indicate that certain fields, such as password and created date, should be excluded from the serialized JSON output. This practice is vital for enhancing data security and reducing payload size, especially when dealing with sensitive information. The userdto class contains only the necessary fields, id and username, along with their respective getters and setters. By isolating these essential attributes, we avoid transmitting unnecessary data, thus streamlining the API response. This approach not only optimizes performance but also simplifies the client-side processing since the response payload is more manageable. Next, we can utilize this userdto in our repository methods to ensure that API responses remain lightweight. By fetching only the information needed, we're enabling faster data transfer and improving the overall efficiency of our API, reinforcing the best practices of effective API design within our Spring Boot applications. Finally, make sure to consider utilizing content delivery networks, CDNs, for caching static assets if your API serves any static resources. CDNs can deliver assets like images, style sheets, and scripts closer to the user, which can drastically enhance loading times and reduce the load on your servers. This is particularly useful for APIs that serve content-heavy applications. Incorporating strategies such as these, effective database query management, caching, asynchronous processing, pagination, connection pooling, optimized API responses, and the use of CDNs, will undoubtedly improve the performance of your APIs. By adopting these techniques in your Spring Boot development, not only will you ensure faster response times and reduced latency, but you'll also provide a seamless experience for your users, therefore, helping you achieve your performance goals with competence. In summary, optimizing API performance involves a myriad of techniques ranging from effective data management to network optimizations. It's not just about making things fast, it's about optimizing your resources and providing a better user experience. I hope you find these performance optimization strategies insightful, and as you continue to build your applications, remember that a well-performing API is crucial in today's application landscape. Thank you for joining me for this deep dive into API performance optimization, and I look forward to seeing you in our next session. Now let's dive into advanced techniques for API design, focusing on enhancing the Restful API we developed previously. This session will equip you with knowledge and practical skills to refine your API, making it not only functional but also robust and efficient. So far, we learned about the importance of implementing performance optimization techniques for APIs, particularly using Spring Boot. We explored strategies to minimize latency, improve response times, and secure APIs through methods such as efficient database query management, caching, asynchronous processing, pagination, and connection pooling. Furthermore, we discussed how optimizing API responses and utilizing CDNs can significantly enhance performance. These techniques are essential for delivering a seamless user experience and achieving robust API performance. Now, we will cover advanced API design techniques to elevate your Restful API to the next level. The displayed figure compares three key API performance metrics before and after optimizations: throughput (RPS), connection acquire time (MS), and error rate %. From the bars, throughput increases from 987.5 RPS to 1,315 RPS, a relative improvement of roughly 33%, an absolute gain of 327.5 RPS, indicating a substantial rise in the system's capacity to handle concurrent requests. Connection acquire time drops from 4 ms to 1 ms, a 75% reduction, which directly points to faster resource allocation, likely the result of connection pooling or reduced contention in the I/O path. Error rate falls from 5% to 2%, a 60% relative decrease, showing improved stability and fewer failed requests under load. Taken together, these patterns indicate that the optimizations not only increased capacity, higher throughput, but also reduced latency in acquiring connections and improved reliability, lower error rate. This combination suggests that changes targeting resource management, concurrency handling, and error-prone code paths yielded both performance and correctness benefits, which will translate into better user experience and higher attainable request volumes for the same infrastructure. Now, let's see how we can implement API versioning in our Spring Boot application through separate controllers for each version of our user API. This approach allows us to maintain functionality for existing users while also introducing new features. In our first controller, named userv_controller, the API is mapped to the endpoint /API/v1/users. When a GET request is made to this endpoint, the getUsers method is invoked. This method interacts with the user service to retrieve the complete list of users specifically formatted for version 1. By isolating this logic, we ensure that any changes or enhancements specific to version 1 can occur without affecting other versions. Next, we have the userv_controller, which handles requests directed at the /API/v2/users endpoint. This controller contains its own getUsers method, which processes requests and returns user data structured for version 2. The distinction between versions allows for significant variations in response formats while still delivering continuity in service. This method of versioning through separate controllers not only upholds backward compatibility, but also enhances flexibility, enabling developers to evolve the API as user needs change. Now let's see how we can implement HATEOAS in our Spring Boot application to enhance our API's usability. The code snippet begins with the necessary import statement for the Spring HATEOAS library, which provides functionality for building hypermedia links. Next, we define a method to handle GET requests for a specific user by their ID, using the @getMapping annotation. Inside the method, we first retrieve the user object from the service layer based on the provided ID. Then we create an entity model user instance, wrapping the retrieved user entity. This model not only represents the user, but also allows us to enrich the response with additional hypermedia links. We add a self-reference link using linkTo and methodon, which links back to the same resource, allowing the client to access the specific user again easily. Additionally, we include a link to the list of all users, directing clients to a related resource. By returning this enriched response, we guide clients on possible actions they can take next, showcasing the power of HATOAS in providing a more navigable and informative API experience. Now let's implement a key feature for user authentication using JSON Web Tokens, JWT, in our Spring Boot application. The code utilizes the @REST controller annotation to define an authentication controller that handles requests related to user login. Here, we set up a post endpoint at /API/auth/login, which accepts a login request object containing the username and password submitted by the user. When a user attempts to log in, the authenticate user method is called. This method leverages Authentication Manager to validate the user's credentials. If the authentication is successful, the security context is updated to reflect the current user's authentication status. This is done through the security context holder, which helps manage security contexts in a stateless manner. Upon successful authentication, the JWT provider generates a token based on the authenticated user. This token acts as a temporary, secure method of authorization that the user can include in the header of future requests, allowing access to protected resources without needing to maintain continuous server-side session states. Thus, the API remains stateless while ensuring secure access and streamlined user interactions. Now let's implement a global exception handler to manage error responses uniformly across our Spring Boot application. We begin by using the @controller_advice annotation, which allows us to handle exceptions thrown by any controller in one centralized location. This is particularly beneficial for providing a consistent error response structure. Next, we define a method with the @exception_handler annotation that specifically targets resource-not-found exception. When this exception is triggered, our handle_resource-not-found method will be invoked. It captures the exception object and constructs an error response instance, which includes essential information such as the HTTP status code, the error message provided by the exception, and the current timestamp. Returning a new response entity object wraps this error response, ensuring that clients receive a structured format for any errors encountered. Implementing this global handler enhances the user experience by guiding developers in understanding what went wrong during their API interactions. It simplifies debugging while maintaining clarity and consistency in error reporting, which are pivotal for building robust and user-friendly APIs. Now let's implement a crucial security feature using Spring Security to control access to sensitive parts of our API. In this snippet, we utilize the @preauthorize annotation to enforce role-based access control, ensuring that only users with the admin role can access the getAdminData method. This method is mapped to the endpoint admin data through the getMapping annotation, indicating that it responds to GET requests. Within the method, we call the admin data service getAllData service to retrieve a list of admin data. The retrieved data is then returned wrapped in a response entity with an HTTP 200 OK status, indicating a successful response. This level of granularity in permission management is essential when developing APIs, as it protects sensitive information and operations from unauthorized access. Overall, by integrating such security measures into our RESTful API, we enhance the application's security posture, ensuring that privileged operations are executed only by users with the appropriate permissions. This is a vital aspect of maintaining user trust and data integrity in an API-driven application. Now let's implement Swagger for seamless API documentation in our Spring Boot application. To do this, we need to add a dependency to our POM XML file. The dependency for Swagger is defined with a group ID of EO SpringFox and artifact ID SpringFox Boot Starter, and we will use version 3.0.0. By including this dependency, we enable the integration of Swagger into our application, which provides a robust platform for generating interactive API documentation. Once this dependency is added, we can start utilizing annotations in our controllers to provide metadata about our endpoints. For example, we can annotate our API methods with details about the expected input, output, and various response statuses. Swagger will then automatically generate a comprehensive documentation page from this information, making it easy for developers to explore and utilize our API. This automated documentation not only enhances the usability of our API, but also facilitates better testing and integration efforts, as consumers can easily understand how to interact with different endpoints, parameters, and responses. This is a significant improvement in managing API transparency and promoting effective communication between developers and users. Now let's implement a test for our user controller using JUnit and Mockito. This code demonstrates how to set up a test class that will verify the behavior of the API endpoint responsible for fetching users. We begin by annotating the class with @run with Spring Runner class to enable Spring's testing support. Next, we use @Spring Boot test to specify that we want to run the test in the context of the complete Spring application. Inside our test class, we first auto-wire mock MVC, which allows us to simulate HTTP requests and assert responses without needing to spin up a server. Additionally, we define a @mockBean for the user service, which will allow us to mock its behavior as needed. In the test method, we'll simulate a scenario where the user service getAllUsers method is called. Instead of hitting the actual service, it will return a predefined list of users. Next, we utilize mock MVC, perform, to simulate an HTTP GET request to the /API/v1/users endpoint. Following this request, we assert that the response status is OK 200 and that the return JSON structure contains exactly 2 users. This approach encapsulates the essence of unit testing by isolating the controller's behavior from the underlying service logic, ensuring that our API behaves as expected under test conditions. As we wrap up, remember that building a robust API requires more than just functionality. It takes careful planning and consideration of versioning, error management, security, documentation, and testing. Applying these principles and techniques in your Spring Boot RESTful API design will greatly enhance both its performance and user experience. In this lesson, we covered advanced techniques including API versioning, HATEOAS, statelessness with JWT, structured error handling, security with Spring Security, API documentation with Swagger, and importance of testing. Now you're equipped with a set of tools and strategies to ensure your API not only meets current needs, but is also prepared for future expansions. With these skills, you're on track to design APIs that are not just functional, but exceptional. To ensure API security in complex environments, we need to focus on controlling response codes effectively from our code. This is foundational for creating a secure and user-friendly API experience. Today, we will explore how we can reinforce security measures and respond appropriately to different scenarios in our applications. So far, we learned about advanced techniques for API design, focusing on optimizing RESTful APIs. We covered the importance of performance optimization, versioning, HATEOAS, statelessness, structured error handling, security, and API documentation. These techniques ensure better user experiences, robust functionality, and future-proofing for API expansions. Now, we will go deeper and cover how to ensure security in API design by managing response codes and understanding their implications. Now let's see how we can implement a global exception handler in our Spring Boot application to manage unauthorized access effectively. The @controller advice annotation allows us to define a centralized exception handler for all controllers. In this case, we are specifically handling instances of unauthorized access exception. When such an exception is thrown, the method annotated with @exceptionHandler is executed. Within this method, we create an error response object that encapsulates important information. It includes the HTTP status code, a descriptive message from the exception, and a timestamp indicating when the error occurred. This structured response ensures that clients receive clear and meaningful feedback about what went wrong during their request, which not only aids in debugging, but also enhances the overall user experience. Finally, we return a response entity containing our error response object along with an appropriate HTTP status code of 401 unauthorized. This comprehensive approach to error handling strengthens the API's resilience against unauthorized access attempts and improves clarity in communication with API consumers. The bar chart titled Distribution of API Response Codes displays counts for 6 response categories: 200 OK, 1200, 400 bad request, 300, 401 unauthorized, 150, 403 forbidden, 100, 404 not found, 200, and 500 internal server error, 50. Key patterns are immediately visible. Successful responses, 200 OK, dominate the traffic, representing the vast majority of requests. client error codes, the 4XX group, collectively account for a significant minority of requests, with 400 and 404 being the largest contributors among them. Authentication and authorization-related codes 401 and 403 show non-trivial counts, indicating repeated unauthorized access attempts or permission issues. Server errors 500 are rare in this snapshot. From these data, we can conclude several actionable points. Prioritize maintaining low server error rates. The 500 count is low, but should be monitored for spikes. Investigate and reduce the 400 and 404 occurrences through better input validation and improved API documentation or routing, and strengthen authentication authorization flows to address the 401 and 403 incidents. The labeled bars in the y-axis number of requests make it straightforward to quantify each category, and to use this distribution to tune error handling, monitoring alerts, and security controls such as stricter auth checks or targeted rate limits for suspicious 4XX patterns. Now let's implement the following controller method to handle user retrieval securely. In this snippet, we define a REST controller named userController that responds to HTTP GET requests at the /API/users/ID endpoint. The method getUser takes a user ID as a path variable and attempts to retrieve the corresponding user from the user service. First, we check if the user exists by calling user service, find by ID. If the user is not found, we throw a resource not found exception, ensuring that the API communicates clearly about the absence of the requested resource. This approach not only adheres to REST-default principles, but also aids in debugging by providing specific feedback on the request's outcome. Next, we verify the user's authentication status with user services authenticated. If the user is not authenticated, we throw an unauthorized access exception. This implementation ensures that we explicitly signal unauthorized access, thus enhancing the API's security posture. Finally, once the checks pass, we return the authenticated user wrapped in a response entity, signifying a successful operation. This flow provides clear, meaningful response codes throughout the user retrieval process, aligning with our goal of effective API design. Now let's implement a rate-limiting filter to enhance API security by preventing excessive request rates from clients. This filter, defined as a Spring component, tracks the number of requests made by each client based on their IP address. It maintains two maps, one for counting requests and another to track the timestamps of the first request within a 1-minute window. When the doFilter method is invoked, it first retrieves the client's IP address and checks if there is a timestamp recorded for that IP. If the timestamp has expired, i.e., the last recorded request was more than 1 minute ago, the filter resets the count to 1 request. If the IP address is already recorded within the time frame, it increments the count by 1. If a client exceeds the configured threshold of 100 requests within a minute, the filter responds with a 429 too many requests status, effectively blocking further requests until the next time window. This mechanism not only protects the API from potential DDoS attacks, but also ensures fair access for all users, making it a vital feature in maintaining the overall health of the service. Now let's take a look at how we handle user registration using a Spring Boot REST controller. In this setup, we define a registration controller class with a mapping to the /API/register endpoint, which is responsible for processing user registration requests. When a POST request is made to this endpoint, the registeruser method is invoked, taking a user registration request object as input, which is annotated with @valid. This annotation ensures that the incoming data adheres to predefined validation rules, triggering validation errors if the input is not compliant. If any validation constraints are violated, Spring Boot will automatically send a 400 bad request response, providing feedback about the specific validation issues. This helps maintain a secure API by preventing invalid data from being processed. In addition to validation, we check if the username already exists by querying the user service. If the username is taken, we throw a user already exists exception, which can be handled globally to return a specific error response. If everything checks out, we proceed to register the new user and return a 201 created response, indicating that the user has been successfully registered. This structured approach not only secures the API, but also enhances communication with clients about the registration process. Now let's implement the following security configuration using Spring Security to protect our API endpoints. In this code snippet, we start by enabling web security with the @enable web security annotation, which tells Spring to configure security settings for our application. We then define a class security config that extends web security configurer adapter, which provides the necessary methods to customize the security settings. Next, we override the configure method where we configure HTTP security. Here, we first disable CSRF cross-site request forgery protection. While this simplifies the authentication process, it's important to be cautious when doing this in a production environment due to potential security implications. We then specify which endpoints are accessible without authentication, specifically any URLs that match /API/public/**. This allows users to interact with public resources freely. Conversely, we define another rule that requires authentication for any endpoints under /API/private/**, thereby safeguarding sensitive data. Finally, we enable HTTP basic authentication, an effective way to protect our private resources and provide a straightforward method for clients to authenticate. This approach facilitates securing access based on user needs while streamlining the management of authentication within our API. Now let's implement the following configuration to set up an OAuth 2 authorization server using Spring Security. In this setup, we start by annotating the class with @configuration to indicate that it provides Spring configuration and @enable authorization server to designate it as an authorization server. We have two important overridden methods. First, in the configure method for authorization server endpoints configurer, we specify the authentication manager. This allows the server to authenticate users appropriately when they try to obtain access tokens. Next, we proceed to the configure method for client details service configurer, where we set up an in-memory client store. Here, we define a client with a given ID and secret, which is represented in a secure format using noop to signify that no encoding is applied to the password. We enable the password grant type, allowing users to obtain tokens using their credentials, and define the scopes available to this client, specifically read and write. This configuration forms the basis for authenticating third-party applications securely, illustrating how OAuth 2 can manage user access in a streamlined and secure manner. Now let's implement a logging mechanism to enhance our API's monitoring capabilities. The logging filter captures incoming requests to provide valuable information for auditing and security compliance. By implementing the logging filter class as a Spring component, it integrates seamlessly into the Spring context. In the doFilter method, we first cast the incoming servlet request to HTTP servlet request to access relevant HTTP details. We log the request method and URI to capture a clear picture of the incoming API calls. This is crucial for tracing client activity and identifying potential issues or breaches. After logging the request, we call chain doFilter request response to pass control to the next filter or the target resource, ensuring the request flows through the filter chain. Once the response is generated, we log the outgoing response status by casting servlet response to HTTP servlet response. This final logging step allows us to verify how our API responds to various requests, completing our monitoring process. By implementing this logging filter, you gain the ability to track and analyze API usage, which is essential for maintaining security and optimizing performance. In conclusion, securing APIs in complex environments is a multifaceted task that requires careful consideration of various factors. From managing HTTP response codes to implementing authentication and logging mechanisms, each layer plays a vital role in building a robust security framework around your applications. By focusing on these aspects, you will not only enhance the security posture of your API, but also improve the overall developer and user experience. By integrating thoughtful practices into your API development process, you will create systems that are resilient to unauthorized access and clear in their communication. In our journey, we have learned how to control response codes to prevent misleading information, handle inputs to safeguard against malicious data, implement rate limiting to protect from abuses, and employ various authentication mechanisms to cater to different client needs. This knowledge arms you with the essential tools to develop secure APIs confidently. The world of API security is as vast as it is fascinating, and with every layer added to your API's architecture, you strengthen its resilience and reliability. Keep applying these techniques and happy coding. In this lesson, we will dive deep into the latest practices for optimizing API performance, focusing on REST-TFL APIs developed with Spring Boot. It's essential to understand how API efficiency plays a critical role in application performance and user satisfaction. So far, we learned about managing HTTP response codes to enhance security and user experience, focusing on exception handling, input validation, rate limiting, and authentication mechanisms. Now we will explore innovative optimizations that can help us improve the performance of our APIs. Now let's see how we can set up caching in a Spring Boot application. We begin by introducing the @Spring Boot application annotation, which serves as the entry point of our application, along with the @Enable caching annotation that activates Spring's caching functionality at the application level. This allows us to utilize caching mechanisms to enhance performance by reducing repeated calls to the database. Next, we move to our user service class, where we define a method to retrieve user details. We use the @Service annotation to mark this class as a Spring Service component, enabling dependency injection. Within the class, the user repository is injected using @AutoWired, which allows us to access database operations conveniently. The most important aspect is the @Cacheable annotation applied to the getUserById method. This annotation tells Spring to cache the result of this method whenever it is called with a specific user ID. If the method is invoked again with the same ID, Spring will return the cached result instead of querying the database, thus significantly improving performance and user experience by minimizing database calls. Now let's see how we can implement effective caching and cache management in our user service with Spring. In this code, we define a user service class, which is marked as a Spring service using the @Service annotation. Within this class, we have a dependency on user repository, which handles the database operations for user data injected via the @AutoWired annotation. The getUserById method illustrates how we utilize the @Cacheable annotation, allowing us to cache user details fetched from the database. When this method is called with a user ID, Spring checks if the data is already cached. If it is, the cached data is returned, avoiding a database call, thus improving performance. Next, we need to ensure that this cached data remains accurate. To do this, we implement the updateUser method with the @CacheEvict annotation. This annotation specifies that when the method is executed, the cache for that specific user ID should be cleared. This is crucial because it ensures that when a user updates their profile, the system removes stale data from the cache, guaranteeing that clients always receive the latest information. Next, we will implement asynchronous processing using the @Async annotation in our Spring Boot application. To enable async operations, we first add the @EnableAsync annotation to our main application class, which allows Spring to process the asynchronous calls throughout the application. Now let's take a look at our notification service class, where we define the asynchronous method sendWelcomeEmail. This method is designed to send a welcome email to users once they register. By annotating this method with @Async, we ensure that when it's called, it runs in a separate thread. This means that the main request won't be held up while the email is being sent. Inside the method, we simulate a delay using thread sleep 5000, which mimics the time it would take to send an actual email. If any interruption occurs while the thread is sleeping, we handle it by restoring the thread's interrupted status. After the delay, a message confirming the email is printed. This setup enhances user experience by allowing immediate responses to registration while processing the email in the background. Now let's see how we can implement pagination within our user service. The user service class is annotated with @Service, indicating that it is a service component in the Spring context, which allows it to be automatically detected and managed by Spring's dependency injection. Inside this service, we use the @AutoWired annotation to inject an instance of the user repository, enabling us to access database operations for the user entity. The method getAllUsers now accepts a pageable parameter. This is crucial as it allows clients to request a specific page of user data along with the number of users per page. By calling user repository findAllPageable, we leverage Spring Data's built-in pagination capabilities. This method returns a pageUser object, which not only contains the list of users for the requested page, but also metadata such as the total number of pages, total users, and the current page number. Next, we'll look at our user repository. By extending JPA repository user long, we inherit a suite of methods designed for data access, including support for pagination without the need to define them manually. This approach streamlines our service layer and promotes cleaner, more maintainable code. Pagination effectively manages large datasets, ensuring efficient performance and improved user experience in our API. Next, we will implement connection pooling using Hikari CP in our Spring Boot application to enhance database interaction efficiency. Connection pooling allows multiple requests to share a limited number of pre-established connections, significantly reducing the overhead associated with establishing a new connection for each request. To set this up, we need to configure our application properties file with several key parameters. First, we specify the database URL, username, and password, enabling our application to connect to the MySQL database hosted on localhost at port 3306, which contains our database named MyDB. Following that, we configure the Hikari CP settings. We set the maximum pool size to 10, allowing for up to 10 simultaneous connections to the database, which is crucial for handling multiple requests efficiently. Additionally, the minimum idle setting is set to 2, ensuring that at least 2 connections are kept idle and ready for use, thereby minimizing wait times for requests that require a database interaction. By implementing these settings, we optimize our API's responsiveness and resource management, leading to better overall performance in our applications. The bar chart titled Performance Optimization Techniques for APIs displays the measured performance gain percent for 6 techniques: caching 34%, connection pooling 30%, asynchronous processing 25%, pagination 20%, HTTP2 15%, and monitoring 10%. The y-axis quantifies percent improvement in requests per second RPS, and each bar is labeled with its exact percentage value, making the relative impact of each technique immediately clear. Key patterns are evident. Caching yields the largest single-step improvement, closely followed by connection pooling, indicating that reducing redundant data access and minimizing connection overhead are the most effective individual levers for increasing throughput. Asynchronous processing and pagination provide moderate gains, showing that non-blocking tasks and limiting payload sizes both contribute meaningfully but less dramatically. HTTP2 gives a smaller uplift, useful for reduced latency in transport but not as impactful on raw RPS as server-side optimizations. Monitoring shows the smallest direct RPS improvement, which reflects that instrumentation itself doesn't directly speed requests, but is essential for identifying where to apply the higher impact techniques. From these values, we can conclude a prioritization strategy. First, invest in caching and efficient connection management, then complement them with async processing and pagination, while using HTTP2 where transport improvements matter and maintaining monitoring to guide and validate all optimizations. Next, we will implement the necessary configurations for enabling HTTP2 in our Spring Boot application. To begin, we need to add a dependency for the HTTP2 connector in our POM XML file. This dependency allows our application to utilize the enhanced features of HTTP2, such as multiplexing and header compression, which contribute to better performance. Now let's see how we configure the Tomcat server settings to support HTTP2. In your application properties, you'll set server HTTP2 enabled equals true, which enables the HTTP2 protocol on the server. This configuration is essential because it allows our application to handle multiple requests over a single connection, significantly reducing latency and improving the load time of resources. By incorporating these configurations, our API is positioned to provide a smoother user experience, particularly in modern web applications where rapid data delivery is crucial. With these changes in place, we can confidently leverage the capabilities of HTTP2 to enhance the performance of our REST-TFL APIs built with Spring Boot. Now let's implement Spring Boot Actuator to enhance our application's monitoring capabilities. First, we need to add the actuator dependency to our POM XML file. This dependency provides built-in features for application monitoring, allowing us to expose various health indicators and metrics related to our API performance. Next, we configure the application properties file to set up which actuator endpoints we want to expose. By including management endpoints, web exposure include ***, we allow all endpoints to be accessible over HTTP. This is useful for gaining comprehensive insights into application metrics. We also configure management endpoint health show details equals always to ensure that detailed health information is available when we access the health endpoint, and we enable metrics with management endpoint metrics enabled equals true. With this configuration in place, we can access the actuator metrics endpoint directly in a browser, providing us with valuable data such as request counts and response times. By visualizing these metrics, we can identify performance bottlenecks and other areas needing attention, helping us to optimize our API effectively over time. In conclusion, optimizing API performance is crucial in providing a seamless user experience and ensuring efficient resource utilization. Today, we covered a range of techniques, from caching and asynchronous processing to pagination, connection pooling, HTTP2, and monitoring. These practices are vital for creating fast, reliable, and scalable APIs that can handle modern application demands. Remember, optimizing your APIs is not a one-time task. It's an ongoing process that requires regular evaluation and adaptation to new practices and technologies. By incorporating these performance optimization techniques into your development workflow, you will enhance your API's responsiveness, efficiency, and overall user satisfaction. Keep experimenting with these methods and let the performance improvements shine in your applications. In this session, we will delve into implementing a Restclient for simplified API consumption. This will enable developers to communicate seamlessly with REST-TFL APIs, enhancing both application functionality and user experience. So far, we've learned about optimizing API performance, focusing on REST-TFL APIs with Spring Boot. We covered essential practices including managing HTTP response codes for security, caching techniques to improve efficiency, and implementing async processing to enhance user experience. Additionally, we discussed pagination to manage large datasets, connection pooling to optimize database interactions, and the benefits of using HTTP2 for better resource utilization. Finally, we emphasized the importance of monitoring API performance using Spring Boot Actuator for ongoing optimizations. Now we will talk about how to create a Spring Boot application that consumes a REST-TFL API using REST template, a key component for API interaction in Spring. Let's start by setting up a new Spring Boot application using Spring Initializr. Head over to the Spring Initializr website and configure the project settings. You can choose the following options. Use Maven as your project type, select Java as the language, and make sure to include the Spring Web dependency. Once you've filled in the group and artifact details, click the Generate button. This will download a zip file containing your new Spring Boot application. Now let's take a look at how we can enhance our application with the Lombok library by adding a dependency in the POM XML file. We will include the Lombok starter, which simplifies data handling in our Java classes, minimizing the boilerplate code that typically accompanies getter and setter methods. This utility will save us time and improve code readability. By incorporating Lombok, we can focus more on the business logic rather than repetitive tasks associated with class properties. Next, we will create a configuration class named appConfig that will define a REST template bean. This configuration ensures that the REST template can be injected into other components of our application. The REST template is central to making HTTP requests and consuming REST-TFL services, which will be crucial throughout our app. Now we will implement an API service class, where we will utilize the REST template to interact with an external API. This service will include methods like getPosts, which will make GET requests and handle the fetch data. Additionally, we'll employ error handling to manage any potential issues during the API calls effectively. This practice helps us create more robust applications capable of dealing with the unpredictability of external services. Lastly, we will set up an API controller that exposes REST-TFL endpoints and connects client requests to our API service. This means users can interact with our application through well-defined paths, calling methods that fetch or manipulate data as needed. With this architecture, we're building a solid foundation for our application, REST-TFL communication. Now let's create a configuration class to define our REST template bean, which is essential for handling API requests in our application. We start by importing necessary classes from the Spring framework, including configuration and bean. The @configuration annotation indicates that this class provides Spring with configuration information, allowing it to manage the defined beans. Within this class, we implement a method annotated with @bean named RestTemplate, which returns a new instance of RestTemplate. This method effectively registers the RestTemplate as a bean in the Spring context, enabling it to be auto-wired and utilized throughout our application wherever needed. By doing this, we ensure that we can leverage the powerful functionalities of RestTemplate for making HTTP requests, simplifying the process of consuming REST-TFL APIs. Next, we will write an API service class where we will auto-wire this REST template to perform our API consumption logic. This management of the REST template bean allows for clean and efficient dependency injection, making our code base modular and easy to maintain. Now let's implement the API service class, which will leverage the REST template for API interactions. In this class, we begin by auto-wiring the REST template bean, making it available for our methods. This is crucial as it enables us to send HTTP requests to external APIs seamlessly. We also define a private final string constant for the API URL, which points to the JSON placeholder's posts endpoint. This URL will be utilized by our methods to fetch data. Next, we need to create the getPosts method within the API service. This method uses the REST template getForObject function to send a GET request to the specified API URL. When the request is executed, the response is mapped directly to a string, allowing us to handle the raw JSON response efficiently. It is important to note that, while using a hard-coded URL is acceptable for learning and demonstration, in production applications, we should typically manage URLs through configuration properties or environment variables to maintain flexibility and adaptability. This practice will make our application more robust and easier to manage as it scales. Next, we will implement the API controller class, which serves as the entry point for our REST API. This class is annotated with @RESTController, indicating that it is a controller that will handle HTTP requests and responses in a REST-TFL manner. Inside API controller, we inject an instance of API service using the @AutoWired annotation, allowing us to leverage the logic we defined earlier for interacting with the external API. We will define a single endpoint using the @getMapping annotation mapped to the posts URL. When this endpoint is accessed through a GET request, it triggers the retrievePosts method. This method invokes the getPosts method from our API service, which retrieves posts from the external API. The data returned from the service is then sent back to the client as an HTTP response. This structure enhances separation of concerns, making our API easier to maintain, and ensuring that the controller only handles HTTP-related functionality while delegating the business logic to the service layer. Now we can test this endpoint by navigating to posts in a web browser or using a tool like Postman to see the fetched posts in action. Now let's implement error handling in our getPosts method within the API service. In this enhanced version of the method, we introduce a try-catch block to gracefully handle possible exceptions that may arise when making a network call using the REST template. If the REST template encounters any issues, such as a timeout or an unreachable server, the Restclient exception will be thrown, which we can catch. When this exception occurs, instead of letting the application crash or return a vague response, we capture the error message and return a user-friendly string indicating that there was an issue fetching the posts. This approach helps in maintaining a better user experience, as it allows us to inform the user about the error while also providing an opportunity to log the error details for further investigation. In production scenarios, you would want to enhance this further by integrating a logging framework like Logback or SLF4J to capture logs at various levels, ensuring that you have more control over how and when error information is recorded. This way, you can debug more efficiently while keeping the system robust and user-friendly. Now let's implement the class that represents our blog post. We will create a model class called Post that contains fields to hold the data we want to send in our post requests. This class will have 4 properties: userid, ID, title, and body. To simplify our code and reduce boilerplate, we will use the Lombok library's data annotation, which automatically generates the necessary getter and setter methods, as well as toString, equals, and hashcode methods. This keeps our model class clean and focused, allowing us to focus on the business logic instead of boilerplate code. Now that we have our post class set up, we can easily create and manipulate post objects. These objects will serve as the payload for our post requests when interacting with the external API. By sending JSON representations of these objects, we can dynamically add new posts to our API, giving users the ability to create content easily. Integrating Lombok streamlines this process further, allowing for more readable and maintainable code. Now let's implement the createPost method in our API service for handling post requests. This method takes a post object as a parameter which contains the details of a new post, such as the user ID, title, and body. When invoked, it uses the REST template to send a post request to the specified API URL. The post4object method serializes the post object into JSON format automatically and sends it to the external API, while also expecting a response of type post. This allows our application to seamlessly integrate the creation of new posts through the API. Next, we'll expose this functionality in the API controller by creating an endpoint for post creation. We will annotate the method with @post mapping /posts, which maps it to the post's root. This method accepts a post object from the request body thanks to the @request body annotation. Upon receiving the request, it calls the createPost method of our API service, passing in the post object. This completes the setup for adding new posts via our Restful API, providing a straightforward way for clients to create and manage posts within our application. Now let's implement the following code for sending a post request to create a new blog post in our API. First, we define a model class called post that represents the structure of a blog post, including attributes such as userid, title, and body. By using the Lombok data annotation, we can automatically generate necessary methods like getters and setters, keeping the code concise and clean. Next, we create a method called createPost within our API service class. This method utilizes the REST template to send a post request to the specified API URL. It accepts a post object, which REST template takes care of serializing into the JSON format expected by the API. This step simplifies our integration process, as we do not need to manually convert the object. To expose our new functionality, we'll need to update the API controller by adding a post endpoint that allows clients to submit new posts. By using the @request body annotation, we indicate that the request payload should be mapped to our post object. When a client sends a JSON representation of a post to this endpoint, the application will create a new post and return the server's response, which includes the assigned ID. This process enhances the interactivity and functionality of our application. Now let's implement the configuration for our REST template to optimize for network interactions. Here, we define a Spring Bean for the REST template that leverages the HTTP Components Client HTTP Request Factory. By using this factory, we can customize the timeout settings for both connection and reading, ensuring that our application doesn't hang indefinitely while waiting for a response from the external API, which can negatively impact user experience. Next, we set a connection timeout of 5,000 milliseconds and a read timeout of 5,000 milliseconds. These settings mean that if the connection cannot be established within 5 seconds, or if the response takes longer than 5 seconds to return, our application will fail gracefully instead of lingering indefinitely. This not only enhances performance by avoiding unnecessary delays, but also allows for better error handling in case of unresponsive external services. Finally, the configured REST template is returned and can be auto-wired into any of our services, providing a robust foundation for making HTTP requests in our Spring Boot application. In today's session, we learned how to implement a Restclient in a Spring Boot application for simplified API consumption, covering both GET and POST requests. We discussed setting up a Spring Boot application using Spring Initializr, creating a service to consume a Restful API, handling errors effectively, and configuring timeouts to enhance performance. Integrating with external APIs is an essential skill for modern developers. REST template allows you to handle HTTP requests and responses conveniently, making your applications more dynamic and engaging. Keep practicing and explore more features of REST template, such as PUT and delete methods, as well as handling different media types and authentication scenarios. Happy coding! In today's lesson, we'll dive into mocking API calls for testing purposes, specifically using WireMock to simulate a remote football service in our Albums application. This technique allows developers to test their applications without relying on real API calls, which can be unreliable or slow during development. So far, we learned about implementing a REST client in a Spring Boot application to facilitate API consumption, focusing on both GET and POST requests. We discussed setting up the project, creating services and controllers, handling errors, and configuring timeouts for a better user experience. The use of REST template simplifies handling HTTP requests and responses, making applications more dynamic. Lastly, we emphasized the importance of integrating with external APIs and encouraged further exploration of REST templates' capabilities. Now, we will cover how to effectively mock API calls for testing, using WireMock to create a reliable and efficient testing environment. Now let's implement the following dependency in our Spring Boot application to integrate WireMock. This dependency is essential for enabling the powerful mocking capabilities that WireMock offers during testing. Notice that in the dependency definition, we specify the group ID, artifact ID, and version for WireMock, ensuring we're using the correct library. The scope is set to test, which is crucial as it prevents this dependency from being included in the production build, keeping the production environment clean and free of unnecessary testing artifacts. By introducing this dependency, we lay the groundwork for simulating API interactions in our tests, allowing us to mock HTTP requests effectively and thereby enhance the reliability of our testing environment. As a result, we can now focus our test scenarios on how our application behaves without needing access to external services, making the whole process more efficient and manageable. Now let's take a look at how to set up a base test class for integrating WireMock with our Spring Boot testing framework. We begin by defining an abstract class named BaseWireMockTest, which will serve as a foundation for all tests that require mocked API interactions. This class utilizes the @run with Spring Runner class annotation to instruct JUnit to use the Spring testing framework. The @Spring Boot test annotation initializes the application context, making a Spring environment available for our tests. Inside this class, we declare a WireMock rule instance annotated with @rule. This rule is responsible for starting a WireMock server on a specified port, in this case, port 8089. By defining the port here, we ensure that our tests can easily access the mocked API without conflicting with our main application's ports. This encapsulated setup allows any test that extends BaseWireMockTest to inherit the WireMock configuration, simplifying the process of mocking API calls in your tests and ensuring that they remain clean and organized. Now let's implement the following test case to validate the functionality of our mocked football service. We begin by creating a new test class, FootballServiceTest, that inherits from our previously established BaseWireMockTest. This inheritance ensures that we have access to the WireMock functionalities we need for effective testing. Next, we use the @AutoWired annotation to inject a REST template instance, which simplifies our HTTP calls to the mocked API. Within this class, we will define a test method, testGetFootballData, where we harness WireMock to simulate a response from the /API/football endpoint. By employing the stub_for method, we set up a scenario where a GET request to this endpoint will return a predefined JSON response representing football data, including leg, team, and points. After specifying our expected response using aResponse, we then invoke REST_template_getForObject to make a request to our mocked server. Finally, we assert that the response we receive matches the mocked data. This approach allows us to effectively test the API's integration without requiring any external dependencies, ensuring our application behaves as expected in a controlled environment. The displayed figure titled Mocking API Calls for Football Service Testing is a pie chart dividing mocked football-related API data into 5 categories: football game data, player statistics, match events, injuries, and team performance. The chart shows that football game data occupies the largest share, about 27.9% of the total mock payload distribution, visually emphasized by an exploded slice, indicating it is the primary focus of mocked responses. Player statistics and match events follow as the next largest segments, approximately 24.6% and 21.3% respectively, which suggests that tests should also prioritize realistic player metrics and sequence of play information. Team performance represents a moderate portion, around 16.4%, showing that aggregate team-level metrics are relevant but less dominant than game and player-level data. Injuries form the smallest slice, about 9.8%, indicating fewer mocked examples for injury data in this testing setup. From this distribution, we can conclude that when designing stubs and test scenarios for the football service, emphasis should be placed on game-level details, player statistics, and match events to cover the majority of expected behaviors, while including representative samples of team performance and injury information to ensure robustness across less frequent but important cases. Now let's implement a test scenario to ensure our application can handle error responses from the Football API. In this next method, we will create a test called testFootballAPI_error, where we simulate an API call that results in a 500 internal server error. This is particularly important because it verifies how our application reacts to unexpected failures from the external service. We start by using wiremock to define the behavior of the mocked endpoint. Specifically, we set up a stub that responds with a status code of 500 whenever a request is made to the /API/football endpoint. This means that when our application attempts to access this endpoint, it will receive an error response instead of normal data. Next, we utilize the REST template to make the actual API call, expecting it to return the string internal server error. Finally, we use an assertion to confirm that the response matches our expectation. By conducting this test, we ensure that our application is resilient and can gracefully handle error scenarios, ultimately making our integration with the API more robust. This approach not only enhances error handling, but also solidifies confidence in the application's overall reliability. Now let's see how to ensure a clean testing environment by resetting the wiremock server between tests. In this section, we will implement setup and teardown methods within our football service test class to achieve this. By utilizing the @before and @after annotations, we define methods that will be executed before and after each test case respectively. First, we implement the setup method annotated with @before. Here, we call the resetAll method, which clears the state of wiremock, ensuring that any mocks or stubs set up in previous tests do not influence subsequent tests. This is essential for maintaining the integrity of our tests, as it helps prevent any false positives or negatives due to leftover mock data. Next, we add the teardown method annotated with @after, where we again call resetAll. This consistency in resetting allows us to verify that each test starts with a fresh slate, minimizing the risk of interference. By implementing both methods, we establish a best practice in unit testing with wiremock, leading to more accurate and reliable test outcomes. Next, we will implement a test for dynamic football data. This test showcases how wiremock can respond differently based on the leg query parameter in our API requests. We start by defining a stub using the stub_for method. This method specifies what kind of HTTP request we are intercepting, in this case, a GET request to the /API/football endpoint. Now let's see how we can set it to respond only when the query parameter matches Premier Leg. When this specific request comes in, wiremock will respond with a JSON body detailing the leg, team, and points for that league, including the HTTP header for content type. After setting up this dynamic response, we call our REST template getForObject method with the corresponding query parameter in the URL. Finally, we assert that the response returned matches our expected output. This illustrates wiremock's flexibility in creating sophisticated testing scenarios and demonstrates how your application can handle various inputs and corresponding responses in a robust manner. Through this technique, we ensure that our APIs are well tested against different potential scenarios. Now let's take a look at how to set up a wiremock server for recording and replaying API scenarios. The first step involves creating an instance of the wiremock server, where you configure essential options. Here, we specify the port for the server to operate on port 8089 in this case. This allows us to run our wiremock server without conflicting with any other services that might be using different ports. Next, we enhance the server configuration by adding a notifier. The SLF4J notifier enables us to receive detailed logging of wiremock's actions, which is incredibly useful for debugging and understanding the behavior during the stubbing process. Additionally, we configure the server to use JAXB for response serialization, which is particularly handy when dealing with XML responses or complex object structures. With this setup, the wiremock server is ready to record real API interactions from your application's requests. By running it in proxy mode, you can capture authentic traffic and automatically generate corresponding stubs, allowing for a highly accurate simulation of the actual API behavior when running your tests. This approach significantly reduces the manual effort required for crafting mock responses while enhancing the overall reliability of your testing environment. In summary, mocking API calls with WireMock is an invaluable technique for testing Spring Boot applications that rely on external services. We've learned how to set up WireMock, create static and dynamic stubs, handle different scenarios, and maintain clean test states. WireMock's ability to simulate various API behaviors enhances your testing capabilities and ensures your application is robust against different conditions it may encounter in production. As we continue learning about Spring Boot and API interactions, consider how WireMock can simplify your testing processes. Being able to focus on application logic without worrying about external dependencies will lead to cleaner, more reliable code. Thank you for joining this lesson on mocking API calls. Happy coding! In this lesson, we will explore how to validate API responses with unit tests, building on the foundation we laid in previous lessons about mocking APIs. This is a crucial aspect of ensuring that your applications function as expected, particularly when they rely on external services. So far, we learned about the importance of mocking API calls for testing using WireMock to simulate a football service in our Albums application. We explored how to set up WireMock by adding it as a dependency in a Spring Boot application, creating test classes, and defining mock responses for different scenarios. Additionally, we emphasized the significance of cleaning up after tests and demonstrated how to manage dynamic responses based on request parameters. Overall, these techniques improve the reliability and effectiveness of testing applications that rely on external APIs. Now we will talk about the importance of validating responses from our RESTful API via unit tests. This includes verifying the structure, content, and accuracy of the responses returned by our API endpoints. Unit testing is all about checking the behavior of individual sections of your code under specific conditions, and validating API responses plays an essential role in that. Now let's take a look at how to set up the necessary dependencies for testing in our Spring Boot application. We include the Spring Boot starter test dependency in our POM XML file. This dependency is crucial as it brings together essential testing libraries such as JUnit, Mockito, and Spring Test, which streamline the process of writing unit tests for our application. By specifying the scope test/scope, we ensure that this dependency is only included during the test phase and not in the final build of the application, keeping the production artifacts clean and efficient. Next, we will implement a simple team controller class that serves as the API endpoint for fetching team information. This class is annotated with @RESTController, indicating that it will handle HTTP requests. The @request mapping annotation specifies a base path for our API, in this case, /API/teams. The controller contains a method called getTeam, annotated with @getMapping, which responds to HTTP GET requests by accepting a team ID as a path variable. Inside this method, we invoke the team service to retrieve the team's data based on the ID. The response entity, OKTeam, return statement ensures that the HTTP response includes a 200 status code along with the team details in JSON format. Now let's take a look at how we can implement a unit test for the getTeam endpoint in our team controller. We start by importing the necessary classes from the Spring framework in JUnit to set up our testing environment. The @run with Spring Runner class annotation indicates that we are using the Spring testing framework, while @web_mvc_test team controller class focuses our test on the team controller, allowing us to isolate it from the rest of the application. Next, we use @AutoWire to inject a mock MVC instance, which is instrumental for simulating HTTP requests. Additionally, we create a mock version of the team service using the @mockbean annotation, enabling us to define the behavior of the service during tests. In the test method, we first define a mock team instance to represent the expected output when we request a team with an ID of 1. We set up the mock service to return this team using Mockito's when, then return syntax. We then simulate a GET request to the /API/team/1 endpoint and validate the response. The assertions confirm that the response status is OK 200 and that the JSON structure holds the expected fields with correct values. This approach ensures that our controller behaves as intended and returns accurate responses. Now let's take a look at how we can implement a test to handle scenarios where a requested team cannot be found. The test getTeamNotFound method is critical for ensuring that our application correctly responds to requests for non-existent resources. In this test, we use Mockito to set up our service call, instructing it to return null when a non-existent team ID, such as 2, is requested. Next, we simulate an HTTP GET request to the /API/team/2 endpoint using mock MVC, which allows us to perform requests to the application without needing to run a server. After the request is executed, we utilize the endExpect method to verify the response status, checking specifically for a 404 not found status code. This asserts that our application behaves properly and informs the client when a requested resource does not exist. By implementing this test, we enhance the robustness of our API, ensuring that it can gracefully handle edge cases and providing clients with clear feedback on their requests. This level of testing reinforces best practices in API development and guarantees that the application meets user expectations effectively. Now let's implement a standardized error response class to handle situations where a requested team is not found. We begin by creating an error response class that has two fields, message and status. The message field will contain a descriptive error message, while the status field will hold the HTTP status code. It's also essential to set up constructors, getters, and setters for these fields, allowing us to instantiate error response objects and access their properties easily. Next, we need to update our team controller to utilize this new error response class. We'll alter the getTeam method to check if the requested team exists by calling the service layer. If the team is not found, instead of returning a null value, we will instantiate an error response object, passing in a message like team not found and the relevant HTTP status code. This structured error response will then be returned to the client with a 404 not found status. By following this approach, we ensure that our API can consistently return well-structured error messages, making it easier for clients to handle error situations correctly. This enhances the overall reliability and user experience of our API. Next, we will write a test to validate the error response structure when a team is not found in our API. This test is crucial to ensure that our application not only returns the correct error code, but also provides a meaningful error message in a structured format. We will use Mockito's method to simulate a scenario where the team service returns null when attempting to find a team with ID 2. Now let's see how we can implement the test using mock MVC to perform a GET request to the endpoint for the non-existent team. We assert that the response status is a 404 not found. Beyond just checking the status code, we also verify that the return JSON matches our expected structure. Specifically, we're looking for fields named message and status, ensuring they contain the values team not found and 404 respectively. This thorough validation process increases the reliability of our API by guaranteeing that clients receive consistent and informative error responses, even when issues arise. Now let's analyze how we can implement a unit test for creating a new team using a post request. In this test, we define a new team instance with its properties, such as ID, name, leg, and points. Utilizing Mockito, we simulate the behavior of the team service, so when the save method is called with any team object, it returns our newly created team. Next, we will make a post request to the /API/teams endpoint using mock MVC, specifying the content type as JSON and providing a correctly formatted JSON string in the request body that matches the team object structure. Once the request is executed, we will validate the response by checking if the HTTP status code returned is 201 created, indicating that the team was successfully added. Additionally, it's crucial to inspect the JSON response to ensure it contains the expected fields. We check that the ID matches 3 and the name is Chelsea. This level of validation not only confirms that our API endpoint works as intended, but also guarantees that it returns the expected data format, setting a solid foundation for interactions with clients consuming our API. Now let's see how we can implement validation testing for team creation requests. In our test case, we're using the mock MVC framework to simulate an API post request to the /API/teams endpoint. We're setting the content type to be JSON, which is essential for the API to interpret the data correctly. In this scenario, we intentionally provide invalid input by leaving the name and league fields empty and assigning a negative value to the points field. This design choice is critical, as it enables us to test how the API handles malformed requests. We expect the API to respond with a 400 bad request status code, indicating that the input was not valid. By asserting this response, we ensure that our API correctly enforces validation rules, reinforcing security and reliability. Properly handling invalid input not only improves user experience by offering clear feedback, but also protects our application from potential vulnerabilities. This testing practice is vital in maintaining the integrity and robustness of the API as part of our development strategy. In summary, validating API responses with unit tests is a fundamental skill in developing robust Spring Boot applications. Today, we've covered a wide array of tests, from validating successful GET requests to handling errors, as well as ensuring our API correctly responds to post requests and enforces validation rules. The importance of testing cannot be overstated, as it helps us build more secure and maintainable applications. As you've seen, unit testing is not just about confirming that your code runs without errors, but it's about ensuring that your application responds appropriately to a variety of scenarios. This comprehensive approach is what separates a good application from a great one. I encourage you to apply these principles consistently in your own projects, as thorough testing will ultimately lead to better software and a more satisfying user experience. Keep coding, keep testing, and remember, a well-tested application is a reliable application. Unit testing is a crucial part of developing reliable software applications, particularly when it comes to RESTful APIs. Today, we're diving into unit testing strategies specifically tailored for RESTful APIs created with Spring Boot. This lesson will focus on writing unit tests for the API we've previously built, ensuring that our endpoints are working as intended and handling both expected and unexpected scenarios gracefully. So far, we learned about validating API responses with unit tests in Spring Boot, focusing on the use of mocking for testing scenarios involving external services. We discussed setting up tests using JUnit and mock MVC, covering both successful and error handling responses, including validation of error structures. We also explored input validation and its importance for maintaining application reliability and security. Overall, the emphasis is on building robust tests to ensure applications behave as expected under various conditions. Now, we will delve into specific unit testing strategies designed for RESTful APIs, emphasizing best practices and hands-on coding examples. Now let's implement a unit test for the user controller to verify user retrieval by ID. We begin by importing necessary classes from Spring and JUnit, including the @web_mvc_test annotation, which allows us to focus solely on the controller without loading the entire application context. We use mock MVC to simulate HTTP requests and assertions. Next, we create a test method named getUserBy. It returns user details. Inside this method, we simulate a GET request to the user's one endpoint, indicating we want to fetch the user with ID 1. Using the accept method, we specify that we expect a JSON response. Following the request, we employ assertions to verify the response. We check that the status is HTTP 200 OK and that the JSON returned contains the expected user's name, John Doe. This straightforward test ensures that the endpoint behaves as intended, confirming that the controller correctly responds with the user's details. By using mocks, we isolate the test from the actual database or external services, focusing entirely on the controller's functionality. Now let's see how we can implement error handling in our unit tests. In this example, we focus on testing a scenario where an invalid user ID is requested. We begin by using Mockito to mock the behavior of our user service, configuring it to throw a user not found exception when the service attempts to retrieve a user with an ID of 99. This simulates a situation where the requested resource does not exist. Next, we perform a mock HTTP GET request to the user's 99 endpoint, setting the expected response to be in JSON format. The test then verifies that the API responds with a 404 not found status, indicating that the user was not found. Additionally, we check the content of the JSON error message, ensuring it returns a specific error message stating, user not found. This practice of effectively testing error scenarios is crucial as it confirms that your API can gracefully handle invalid inputs, ensuring users receive clear and accurate feedback when they encounter issues. By extending our test coverage to include such cases, we bolster our API's robustness and usability. Next, let's explore input validation as part of our unit testing strategy. Ensuring proper user inputs before reaching your controller is vital for maintaining application reliability and security. For this part, we assume our user creation endpoint has certain requirements, such as the user's email address being valid and their password meeting specific criteria. The displayed figure, titled Unit Testing Strategies for Restful Apis, is a bar chart that quantifies the number of tests allocated to 5 categories: validation tests 20, error handling 15, performance tests 25, input validations 10, and complex interactions 30. The x-axis lists the test categories and the y-axis shows the number of tests. Each bar is annotated with its exact value, allowing precise comparison. Key patterns are clear. Complex interactions has the highest coverage, 30 tests, 30% of the total, followed by performance tests, 25 tests, 25%, validation tests, 20 tests, 20%, error handling 15 tests, 15%, and input validations is the smallest slice, 10 tests, 10%. From these values, we can conclude that test efforts are concentrated on higher-level scenarios, particularly complex interactions and performance, while low-level input validation is relatively underrepresented. The distribution suggests prioritizing integration style and performance scenarios in the current test suite, but also highlights a potential gap. The comparatively low number of input validation tests may leave the API vulnerable to malformed input and edge case data errors. In practice, this chart supports a testing strategy that balances coverage by increasing input validation and error handling tests to complement the strong focus on interactions and performance. Now let's implement a test for a scenario where invalid input is provided, specifically focusing on creating a user with an incorrectly formatted email address. In this test, we define a JSON string representing a user with the name Jane Doe, an invalid email not an email, and a password 123. This simulates a POST request directed at the user's endpoint, which is expected to handle user creation. Next, we will use the mock MVC instance to perform this POST request. We'll specify that the content type of the request is JSON and include our invalid user JSON string as the body of the request. The goal is to validate that the API responds appropriately when given invalid input. We will set our expectation that the response status is a 400 bad request, indicating that the server has recognized the error. To ensure that users receive meaningful feedback, we also check that the JSON response includes an error message specifically stating invalid email format. This test plays a crucial role in enforcing business rules at the input layer of our API, safeguarding data integrity, and improving user experience by promptly addressing incorrect submissions. Now let's implement a performance test for our API endpoint that retrieves user data. In this test, we begin by capturing the current time right before making the GET request to the user's endpoint, which allows us to measure how long the request takes to process. After issuing the request using mock MVC, we ensure that the response status is OK, which confirms that our API is functioning as expected. Once the request is complete, we capture the end time and calculate the duration by subtracting the start time from the end time. This duration represents the response time for our request. Next, we include an assertion to validate that the response time is below our specified limit of 200 milliseconds. By doing so, we ensure that our API remains efficient and can handle high traffic effectively without compromising performance. This performance test is crucial as it helps us maintain acceptable response times even as we scale up our application, ensuring that user experience remains optimal. Now let's see how we can implement a unit test for fetching a user and their associated orders in our Restful API. In this test case, we define a method that simulates a request to retrieve a user along with their orders. First, we create a mock user and a list of mock orders to represent the data we expect from the API. Using Mockito, we set up the behavior of the user service to return a userWithOrders object when the getUserWithOrders method is called with a specific user ID. This is crucial for isolating our test from the actual database, ensuring that we focus solely on the API's response. Next, we perform a GET request to the user's OneOrders endpoint with the appropriate headers to accept JSON responses. The assertions that follow check whether the status of the response is OK and whether the returned JSON contains the correct user name and product information from the orders. This effectively demonstrates how we can use mocking to verify that our API behaves as expected when it needs to collate data from multiple sources, improving the reliability of our application. Now let's implement an integration test for the user registration endpoint, which is crucial for validating the interaction between the API and the database. In this test class, we annotate it with @Spring Boot test and @auto-configure mock MVC to set up the application context and the mock servlet environment for testing. We use the mock MVC instance, which allows us to simulate HTTP requests and verify responses without spinning up a web server. Within the test, we auto-wired a user repository to interact with the actual database, ensuring that we can check if our user creation functionality works as intended. The test method registerUserSuccess prepares a JSON representation of a new user and performs a POST request to the user's register endpoint. The request specifies the content type as JSON and includes the user details. After executing the request, we assert that the HTTP response status is 201 created, confirming that the user was successfully registered. Additionally, we verify that the user count in the repository increases, indicating that our application correctly processes and stores new user data. This integration test provides essential validation that all components of the registration feature interact properly and deliver the expected outcome. To sum up, we've covered essential strategies for unit testing RESTful APIs in Spring Boot. We started by organizing our tests, focusing on successful and error responses, input validation, performance, complex interactions, and integrating unit tests with overall application functionality. Each of these components plays a vital role in maintaining a high-quality RESTful API. Remember, effective unit testing fosters confidence in your code, enabling you to ship features rapidly while ensuring reliability. Regularly running these tests also provides immediate feedback on the health of your application. As we continue forward in our development journey, keep these testing principles in mind. They will serve you well in building robust, reliable applications. Thank you for joining today's session, and happy coding. In this lesson, we'll explore the world of mocking remote services in testing by learning how to use WireMock to mimic the remote football service in our Albums application. Mocking is an essential technique in unit testing that allows us to simulate the behavior of complex external services without actually calling them, which makes our tests faster and more reliable. So far, we have learned about the significance of unit testing for RESTful APIs using Spring Boot, emphasizing strategies to validate API responses, handle errors, and ensure input integrity. We also discussed structuring tests efficiently with annotations like @SpringBootTest and @WebMVCTest while exploring specific test scenarios for both successful requests and error handling. The importance of performance testing and testing complex interactions between services was highlighted, along with the necessity of integration tests to validate the complete functionality of the application. Overall, these practices ensure robust, reliable, and efficient APIs that effectively cater to user needs. Now we will talk about mocking remote services and how we can implement that in our testing strategy using WireMock. Mocking remote services can save your application from being dependent on external systems during unit tests. This way you get to control the data returned by those services and also simulate different scenarios like failures, latency, or different response codes. This not only speeds up your tests, but also makes them more deterministic and isolated. The figure titled Mocking Remote Services in Testing Strategy is a donut chart that breaks down testing focus areas into 5 labeled slices with displayed percentages. Success responses 30%, error handling 25%, delay simulation 20%, timeouts 15%, and custom responses 10%. From these proportions, we can infer priorities for a comprehensive mocking strategy. Successful response scenarios receive the largest share, indicating routine validation of normal flows is essential. Error handling is nearly as prominent, underscoring the need to verify how the application reacts to failures. Delay simulation and timeouts together account for 35%, highlighting that latency and responsiveness should be explicitly tested to ensure resilience under slow or unstable network conditions. Custom responses, while smaller at 10%, remain an important category for edge case and contract-driven tests. Reading the chart as a whole suggests a balanced approach where correctness of happy paths and robust handling of failures and latency are the primary focus. while specialized custom response stubs are included to cover less frequent but critical scenarios. Now let's take a look at how we can set up a test class that integrates WireMock with our testing framework. Here, we define a WireMock rule that will create a WireMock server instance on port 8080. Using the @rule annotation means this server starts up before each test and shuts down afterward, ensuring our tests run in an isolated environment. In the first test method, we demonstrate how to configure a mock response. We use the stub4 method to set up a scenario where a GET request to the football match endpoint returns a successful response with a 200 status, mimicking the behavior of a real service. The mock response is defined with a JSON body, which includes details like matchid, team A, and team B. Next, we implement a second test where we simulate an error scenario. By setting up another stub4, we configure the WireMock server to return a 500 status code, allowing us to verify how our application handles internal server errors without needing the actual football service. Lastly, we explore response delays by adding a fixed delay to our mock response. This powerful feature lets us simulate different network conditions, testing our application's resilience against latency. Altogether, these strategies empower you to create comprehensive tests that reflect various scenarios an actual service might encounter. Now let's take a look at how to set up a test class using WireMock to effectively mock a remote football service in our testing strategy. We begin by importing necessary dependencies, including the WireMock rule from the WireMock library, which allows us to simulate HTTP responses. In our test class annotated with @SpringBootTest and @AutoConfigure mock MVC, we declare a WireMock server instance using the @rule annotation. This server will start before each test and shut down afterward, ensuring a clean testing environment. Next, we will implement a test method that simulates fetching album details while interacting with the mocked football service. Using the stub4 method, we set up a mock response for a specific GET request to football match. In this stub, we define the expected HTTP response, including a 200 status code and a JSON body that simulates the match information. After defining our stub, we use the mock MVC object to perform a GET request to our album's endpoint. By doing so, this request will hit the WireMock server instead of the actual football service, providing us full control over the test scenario without relying on external dependencies. This isolation is fundamental for robust unit testing. Next, we will write a test case that simulates the football service being down by returning a 500 internal server error. In this code snippet, we utilize WireMock's stub4 method to define how the mock server should respond when it receives a GET request to the football match endpoint. Here, we specify that the server should respond with an error status. Following that, we perform a request to our album's service endpoint using mock MVC, which represents our application's interface for testing. By executing the call to albums1, we intend to see how our application deals with this simulated failure. Finally, we leverage the endExpect method to assert that the response from our application is indeed an internal server error. This test plays a crucial role in ensuring that our application can gracefully handle external service failures without crashing, thereby enhancing user experience even when the external dependencies are unreliable. Next, we will implement a test to simulate a delayed response from the mocked football service using WireMock. This is crucial for assessing how our application reacts to latency, which can occur when integrating with real external APIs. We can achieve this by utilizing the withFixedDelay method to introduce a fixed delay before sending back the response. Now let's write the test method, fetchAlbumDetails football service delayed should return delayed response. Within this method, we first configure WireMock to stub a response for the GET request to the football match endpoint, specifying a delay of 2000 milliseconds. We also include a JSON body that simulates the match details, ensuring it has a proper content type. After setting up the stub, we capture the start time just before performing the mock HTTP request to our album's endpoint. This is done by utilizing mock MVC, which will issue the request against the WireMock server instead of the actual football service. Once we get the response, we calculate the elapsed time and print it out. Finally, we assert that the elapsed time is at least 2000 milliseconds, confirming that our application handles this simulated latency appropriately, which is critical for real-world API interactions. Now let's see how we can implement a test that utilizes WireMock to handle custom query parameters effectively. In this example, we focus on fetching album details based on the teams specified in the request. Here, we define a stub using stub4, setting up an endpoint that WireMock will listen to. Specifically, we establish a condition where the mock server checks for a query parameter named team and expects the value to be team A. If this condition is met, WireMock will return a predefined JSON response that simulates the data we would expect from the real football service, including the match ID and associated teams. Next, we use mock MVC to perform a GET request to our application endpoint, appending the query parameter to mirror what a client would do. The expectation is that the call should result in a 200 OK status, confirming that our application handles the response correctly under the given conditions. By structuring it this way, we can easily create numerous stubs for different teams and responses, making our tests comprehensive and robust for various scenarios. This technique enables us to validate our application's behavior without relying on the actual remote service, ensuring that we control the data returned during testing. As we come to the end of this lesson on mocking remote services using WireMock, keep in mind that the real power of mocking and testing lies in how it allows you to simulate an incredibly wide array of scenarios that external services might encounter without ever needing to call those services directly. By leveraging WireMock in your unit tests, you not only speed up your tests, but also gain precision in controlling what data is returned to your application. Mocking remote services helps develop more resilient applications by ensuring that your code can handle all sorts of error states gracefully. So whether external APIs are down for maintenance, slow due to network latency, or return unexpected data formats, you will be ready. So far, we've covered everything from setting up WireMock to creating responses, simulating failures, testing delays, and even handling dynamic query parameters. These strategies will equip you with the knowledge to write robust unit tests that incorporate external service integrations effectively. Thank you for joining me in this lesson on mocking remote services in testing. I hope you found it informative and engaging. Let's continue building resilient APIs, ensuring our applications are robust in any environment. Happy coding! In this lesson, we'll explore how to elevate your REST-TFL API documentation using Openapi, making it more comprehensive and user-friendly. Openapi provides a powerful way to describe the structure and behavior of your API, allowing developers to understand and interact with it with ease. So far, we learned about the importance of mocking remote services in testing using WireMock, which allows us to simulate the behavior of external APIs for more reliable unit tests. We explored how to set up WireMock, create tailored responses, and handle various scenarios such as error responses and delays to ensure our applications remain resilient. We also discussed the significance of controlling test environments without relying on actual external services, leading to faster, more efficient testing workflows. Overall, these practices enhance our ability to write robust tests that validate the interactions between our services and the APIs they depend on. Now we will talk about how to implement Openapi support in our Spring Boot applications and how to consume it effectively. The displayed horizontal bar chart titled Key Concepts in Advanced API Documentation and Testing quantifies 5 prioritized concepts by their importance level. Numeric annotations shown at the end of each bar. Documentation clarity 30, testing efficiency 25, error handling 20, performance monitoring 15, and security management 10. The pattern of descending bar lengths reveals a clear prioritization. Documentation clarity receives the highest emphasis, indicating that making API contracts explicit and easy to understand is foundational. Testing efficiency closely follows, underscoring the practical need to automate and streamline verification, for example, by using mocks like WireMock so that documented behavior can be validated quickly. Error handling occupies the middle position, highlighting that documenting and testing failure modes is important but secondary to clarity and repeatable tests. Performance monitoring and security management, while still present, register lower importance in this representation. This suggests allocating initial effort toward documentation and testing to accelerate developer adoption and confidence, then iterating to strengthen error handling, monitoring, and security as subsequent priorities. The consistent 5-point steps between adjacent items indicate a graded allocation of attention rather than abrupt drop-offs, so a practical takeaway is to sequence improvements accordingly. Start with clear, comprehensive docs, invest in efficient testing workflows, then progressively address robust error descriptions, performance observability, and explicit security requirements. Now let's implement the necessary dependency for Spring.OpenAPI in our project's POM XML file. By adding this dependency, we enable our Spring Boot application to generate OpenAPI documentation automatically, which is crucial for creating accessible API documentation. The specified group ID, artifact ID, and version ensure that we're utilizing the correct library to achieve this functionality. This dependency pulls in all the required components to integrate OpenAPI support seamlessly into our application. Next, we will configure our application to provide a user-friendly interface for our API documentation. Once the dependency is added and the application is up and running, we'll be able to access the OpenAPI UI by navigating to http://localhost 8080/swaggerui HTML. This interface not only visualizes the structure of our API, but also allows other developers to easily understand and interact with our endpoints. Through this integration, we enhance the usability of our API documentation, making it more comprehensive for users and stakeholders alike. Now let's see how we can document our API methods using OpenAPI annotations effectively. We start by importing the necessary classes from the OpenAPI library and Spring framework. The album controller class is created as a REST controller that handles HTTP requests related to albums. Next, we use the @operation annotation to provide a summary and description of the getAllAlbums method. This is crucial as it informs users about the purpose of the endpoint, which in this case is to retrieve a list of all available albums. Following that API responses annotation is employed to specify the potential responses from the API. It indicates that a successful call returns a 200 status code along with a description of the response, while also detailing a 500 status code for internal server errors, ensuring that any developer interacting with the API understands the expected outcomes. Finally, the method is mapped to the albums endpoint using the @getMapping annotation, allowing it to handle HTTP GET requests. This structured approach to documenting the API not only enhances clarity, but also supports the growth and maintenance of your API as it evolves. Now let's see how we can enhance our API documentation by incorporating detailed parameters using the @parameter annotation. This annotation is particularly useful when our API endpoints expect specific query parameters, providing clarity to clients on how to interact with the API. In our example, we're modifying the existing endpoint for retrieving albums to allow users to filter the results by genre. The method now accepts a string parameter called genre, which is annotated with @parameter. This annotation includes a description that specifies the purpose of the parameter, clearly indicating to users that they can use it to filter albums based on their genre. Moreover, we set the required attribute of the @requestParam annotation to false, which informs clients that providing a genre is optional. This enhancement not only improves the usability of our API by making the available options explicit, but also enriches the generated documentation. As a result, developers integrating with our API will have a clearer understanding of how to formulate their requests, ultimately leading to a more intuitive and user-friendly experience. Now let's see how we can implement the functionality to create a new album in our API. In the provided code snippet, we define a post endpoint @albums that allows clients to send an album object as part of the request body. We utilize the @postMapping annotation to specify this endpoint's HTTP method and path. To ensure clarity in our API documentation, we incorporate the @parameter annotation, which describes the purpose of the incoming request body. Additionally, by integrating the @requestBody annotation, we directly indicate that the album object being passed must be serialized from the JSON structure specified by the client. The @schema annotation is particularly helpful, as it allows us to define the expected structure of the album class within the OpenAPI documentation, making it clear to developers what properties are necessary to create a new album. By providing this detailed documentation, we enhance the usability of our API, ensuring that users understand exactly what data they need to send when calling this endpoint. Finally, within the method, we would include the logic for saving the album, ensuring the application can process the incoming data correctly. Next, let's take a look at how to manage versioning in your Openapi documentation, which is essential as your API evolves. We begin by defining two separate classes for different versions of the album API. Each class is annotated with @OpenAPI_definition, where we specify relevant information like the title, version, and description for each version. For instance, album v1 controller represents version 1 of the API, while album v2 controller corresponds to the enhanced version 2. By structuring your API in this way, changes and improvements can be implemented independently for each version, ensuring that existing clients continue to function without breaking. This pattern allows users to choose which API version they want to utilize, making the documentation clearer and more user-friendly. The automatically generated documentation will reflect these distinctions, providing developers with a comprehensive view of what each API version offers. This approach not only enhances clarity, but also significantly improves the user experience when interacting with your API, facilitating smoother transitions for clients when upgrading to newer versions. Now let's take a look at how to integrate security into our Openapi documentation by using an API key. In this example, we begin by importing the necessary annotations from the Swagger library. The @security scheme annotation is used to define the type of security we're implementing, which in this case is an API key. We specify essential parameters such as the name of the security scheme, API key, the name of the parameter that will hold the key, API key, and that the key should be included in the request header. Next, we create a controller class named SecureAlbumController, which is annotated with @RestController to mark it as a Spring REST controller. Inside this class, we define an endpoint for retrieving secure albums. The @security requirement annotation indicates that this endpoint requires authentication using the specified API key. This setup not only secures the endpoint, but also ensures that the generated Openapi documentation clearly communicates to users how to authenticate their requests. This integration is crucial for building trust and securing access to sensitive resources in your API. Let's circle back and discuss how to consume the Openapi-generated documentation. Once your API is documented using Openapi annotations, you can leverage various tools for testing and client generation. For instance, tools like Postman or Insomnia can import Openapi specifications, allowing developers to test endpoints without manually creating requests. Additionally, code generators can create client SDKs in multiple programming languages based on your Openapi spec, saving time and effort. To export your API documentation as an Openapi specification file, typically in JSON or YAML format, you could use the endpoint provided by your Openapi library. With Spring.Openapi, you can navigate to http://localhost 8080/v3/API docs to get a JSON representation of your API documentation. This makes it easier for developers to integrate with your service. As we wrap up, let's review what we've covered. We started by adding Openapi support to our Spring Boot application, enhancing it using various annotations like @operation, @API response, and @parameter. We went on to document request bodies and learned how to effectively manage API versioning and security using Openapi. Finally, we discussed ways to consume your Openapi documentation and how it can enhance the developer experience. Openapi not only enriches your API documentation, but also serves as a communication tool between various stakeholders in a software project. With such comprehensive documentation, you're not only showcasing your API, but also promoting collaboration and clearer understanding among developers, stakeholders, and clients. Thank you for joining this discussion on advanced API documentation with Openapi. Let's continue to improve our development practices and provide exceptional experiences for our users. Happy coding! In this final section, we will do a project challenge to apply what we have learned so far. Your task is to create a football card management system using Spring Boot, where you'll develop a RESTful API that allows users to manage football players, teams, and cards. This project will require you to implement essential CRUD operations, integrate a PostgreSQL database for data persistence, and ensure proper exception handling with appropriate HTTP responses. You will begin by setting up your project environment using Spring Initializr, defining entity classes for player, team, and card, and creating repository interfaces. Then, you'll build a service layer to encapsulate your business logic, followed by a REST controller to expose your API endpoints. Remember to focus on clean code and best practices throughout this process. Don't forget to test your API using tools like Postman or curl, and finally provide a README file with instructions on how to run your application. You can find the final project details in the GitHub repository linked in the description, so get ready to showcase your skills and bring your vision to life.